All right. Well, good morning, everybody. My name is Ty Van Daan. I'm with the EOH Alumni Board, and welcome to our after 2 years break. Welcome back to our season technical symposium. Today's topic, dealing with wildfire, is relevant and it's something that's not going to go away. Before we start, I'd like to say thank you to a couple of people that help us make this happen. Dr. Katherine McNamara, she was very instrumental in getting all our speakers lined up. Bob Falkenstein, Marty Silsner, Jack Assuran, Tony Luca, Arlene Feinstein, and Robert Montgomery, who helped us get our CEUs approved for this event. Also, I'd like to thank our speakers for sharing their expertise with us. And last but not least, Jenny Daniels-Fries from Alumni Relations. She pretty much put all this, was instrumental in making this event happening via Zoom. Hopefully next year, we'll plan to be back on campus like we have done over years past. One last thing, today's proceeds will be used to, will be donated back to the EOH department to help our professors and help our students during the classroom time. So now I'd like to pass it over to Bob Falkenstein, who has a special announcement to make.
Good morning, everyone, and welcome from the East Coast. One of the nice things about having a Zoom meeting is being able to join in from far away. I wanted to take just a couple of moments here, just a brief time, to recognize one of our alumni, and it will become apparent why as I tell you the story about Tom and his wife, Nancy. I met Tom 45 years ago. Yes, it's been that long, when I was a grad student at CSUN, and we've been friends ever since. Tom could not join us today. I know he wanted to say a few words, but on behalf of Tom and Nancy, I've got a few notes I'd like to go over with you. Tom's days as a student at CSUN gave him more than a great education and springboard for a successful career. It provided a place where community mattered and fostered a desire to give back to an institution he feels has rewarded him handsomely over the years. In addition to earning his degrees at CSUN, Tom has his bachelor's and master's degrees there, and he's been a part-time teacher for 30 years. And Tom would always tell me that whenever he and Nancy went out, it was hard to have a quiet dinner because people were always coming up to him, saying hi, and how much we all enjoyed the program over the years. And most importantly, Tom and his wife, Nancy, have generously donated $50,000 to the College of Health and Human Development's Department of EOH. And he hopes his actions will have a ripple effect, encouraging other alumni to donate too. You know, whether it be a donation in time, money, a matching gift. Tom appreciates what CSUN and EOH have done for him over the years and his successful career. And he's hoping that others will recognize that there's ways that you can give back to the university and make a difference with EOH because it's made a difference in your life. The donation will allow for equipment purchases and student training in the EOH department. And Tom and his wife, Nancy, who is an attorney, wanted to give a gift that was beneficial for the students and the faculty. His spirit of generosity has extended to non-monetary giving also. Tom has volunteered in many things during his life, beach cleanups, volunteering to help with things at CSUN. And again, he's hoping that volunteering and giving will become a part of your life too. In reflecting on his meaningful life with CSUN and the connections, he wants to thank the program, the people, the professors, the alumni, and the students too, that enabled him to have a great career. And he hopes that his generous donation will alleviate some stress in certain areas to make people happier, even if it's just for a day. So again, I just wanted to thank Tom and Nancy on behalf of Alumni Relations, EOH, and CSUN. We can't thank him enough for his generous gift. And again, he's hoping this will spill over into you considering volunteering, either with CSUN, the EOH department, the alumni group, gift matching, or in some way helping to contribute and give back to the university. So thank you, Tom and Nancy. And at this point, I'd like to turn it over to Robert Montgomery, who is going to speak about your CEUs for the day. Robert?
Thank you, Bob. Good morning. I'm Robert Montgomery of Montgomery Investigations. We're the accrediting agency for the state for this symposium and have been for the last several years, which will be coming up on the screen shortly, are the requirements for, and I'm speaking to the REHSs in the audience specifically, because that's who the CEUs are accredited to. The state of California Department of Public Health, the REH group, has put special requirements, certain requirements on this symposium. One is that the attendees, in order to receive the CEU continuing education contact hours, has to attend all the presentations all day. There are no partial units. At the end, we'll be able to award 8 contact hours. The 2 forms on the screen are, the certificate will be sent once 2 other conditions are met in addition to attending. One is to complete and submit the online PDF symposium evaluation, completely filled out. And secondly, following the symposium, you'll be emailed the document on the left of the screen, which is you need to fill out, give your REHS number, address, etc., and signature, and then email back the Alumni Association on for the email. And then you will be sent, you'll keep that, plus you'll be sent a certificate of attendance. And those 2 will be, you'll hold on to in the event that the department requires you to submit documentation for your renewal registration. Any questions can be sent directly to me at rbm@montgomeryinvestigations.com if you have any questions in regard to it. And I will send this back to, I believe, Ty. Thank you for your time and enjoy the symposium, excuse me.
Thank you, Bob and Robert. We cannot thank the Baxwells for their generous donation. We can't thank them enough for that. Before I turn it over to Dr. McNamara, Jen, is there any other logistics the audience needs to know as far as the format for this event?
Good morning. The audience can use the Q&A format to ask questions, and the speakers will be able to either answer them live or they'll type their answers back to you. I think that's everything. This event is being recorded, so there will be a chance for you to review the event in the coming weeks.
Thank you. All right, now I'm going to turn it over to Dr. McNamara, seasoned EOH professor, and she'll walk us through today's event.
Thanks, Ty, and thanks, Robert. I had a couple of slides I was going to share. Whoops, that's not it. All right. Let's try that again. All right. So welcome, everybody. We're so glad to be able to offer this program again. This is our 15th technical symposium, and it's our first virtual symposium. So bear with us while we adjust to this new format. We actually made the decision to go virtual in January during the Omicron surge. And so it's a little unfortunate that the world is opening up again, and we're not meeting in person, but there are benefits to this, and it seemed like the most reasonable projection at the time. So as Jenny mentioned, you'll be able to view the recordings later. The links to the videos will be sent out in an email, I believe, and it's going to take about a week to process all of those. So you can take advantage of the recordings if you have a conflict during the day-to-day. I know this is a big sort of alumni reunion for many of us, and so we really hope that we'll be meeting in person again next year and enjoying the delicious lunch that Ty arranges for us together. Yeah, and so we actually planned this topic 2 years ago. It was a pretty punishing wildfire season for the last few years at that time, but the topic is still relevant today. And I think the most recent wildfire seasons have been a little more favorable here in the South, but they've been disastrous in Northern California. The Dixie Fire burned almost 1 million acres over a 3-month time period in the Feather River area last summer. And then we saw the Caldor Fire in the Sierras actually jumping the summit of the Sierra Nevada and going over all the granite rock face and tearing into the Tahoe Basin so rapidly that they weren't able to control it. So the previous summer, if you recall, let's see, we had in August 2020, we had those dry lightning storms that set off numerous of those lightning complex fires throughout Northern California, including what they called the August lightning complex up in the Mendocino-Humboldt area that burned over 1 million acres, and the SCU complex fires that affected 6 Bay Area counties and required evacuations of major urban areas. And also, this is 1 month later. In September 2020, we saw air quality at hazardous levels in the Bay Area for weeks at a time, almost a month. So as you're probably aware, even though we did have some early rainfall in the state and a couple of wet winters on the books, we're still in severe drought conditions here in the Southwest. Despite the fact that we've had occasional rain, I saw this interesting article in the LA Times describing how our intermittent rainstorms this winter have been accompanied by these periods of desiccating Santa Ana winds, which are the perfect recipe for desiccating fire fuel. And so if you want to read more about this, it's pretty interesting, but there's a high pressure system off the coast that is responsible for driving the dry winds from the Great Basin area in Nevada. And so with all of this, unpredictable weather changes, dry winters, and these warm, windy conditions, we can expect that wildfires are going to continue to increase in severity and duration. And so the focus of the program today is really to better understand how this affects public health and environmental quality. We're going to learn more about the composition of wildfire pollutants and how people are minimizing their exposures. We're going to learn about the occupational impacts to firefighters later in the afternoon. Let's take a look at our agenda here. And and then look at some of the environmental impacts as well. So we're going to start off hearing about the wildfire smoke composition and the health effects associated with that exposure from Michael Kleinman from UC Irvine. Then we're going to hear from Nico Schulte from our local air quality management district, talking about the air quality index and the health advisories coming out of their division. Scott Hauswirth from the CSUN Department of Geology will be presenting some of his research on water quality impacts from the Woolsey fire. Then we'll hear from Marisol Cira, who's a UCLA doctoral student, and she collaborated with Heal the Bay looking at coastal water quality impacts. Then I'm going to be presenting a student research project after lunch, where we looked at the feasibility of shelter-in-place recommendations in partnership with the AQMD. And then we'll hear from Shelley DuTeaux about some fascinating air monitoring she did during the campfire cleanup up north. Derek Urwin, who recently received his PhD from UCLA, will be talking about the firefighter cancer cohort. And then Kathleen Navarro from NIOSH will be presenting work she's been doing in partnership with the Forest Service on firefighter exposures. And then we'll hear from Joe Saul, who is also with the Forest Service, who's done a lot of work on heat stress and exertional fatigue. So it should be a full program and an interesting day. I do have, on the note of alumni giving, I do have another announcement I would like to share. So we're very pleased to announce a new scholarship, relatively new, that's been generously supported by Amgen, who, as many of you know, they not only do they offer a internship opportunity that is generously has provide kind of a pathway for professional development and employment at their organization. But they've created a new scholarship for our students in the memory of their colleague, Matt Wynn. So Matt was a CSUN alum, and he, after working kind of in various roles in mostly industrial hygiene and EH&S throughout Southern California, he joined the Amgen team in their environment, health, safety, and sustainability department. Sadly, he passed away suddenly 2 years ago from a heart attack and left behind a wife and 2 sons. And so Amgen, in his memory, has generously established a scholarship for our students. And so we have been offering this the last 2 years. We just wanted to let the students who are joining us today know that they're encouraged to apply. And there's an evaluation of, there's an application process where they're evaluated based on their goals, or their professional goals, their desire to impact the field. And also there's a big emphasis on community and campus service, and also diversity and financial need. So just want to recognize a couple of the recipients. Ruby Cornejo, a 4th-year EOH major with interests in toxicology, sustainability, and environmental compliance. Griselda Gonzalez, a 4th-year student in EOH. Her interests are in hazardous waste management and industrial hygiene. And Yared Amanios, who's a fourth-year student in EOH, interested in sustainability, hazardous waste management, and occupational health. So I just wanted to congratulate the scholarship recipients and let the students know about this opportunity. You have to be a continuing student to apply. And to thank Amgen for their generosity. They've been supporters of our program for many years, and we really value the partnership with them. Okay. I don't see any questions. So, Michael, are you ready to go?
I am.
Okay, great. I'm gonna introduce you briefly. Let's see, I'm still on camera. Okay. So yeah, we're very pleased to welcome Dr. Michael Kleinman. He's an adjunct professor of occupational and environmental medicine in the medical school at Irvine. And he has a joint appointment in their public health program. He has previous experience at the U.S. Atomic Energy Commission, and he directed aerosol exposure and an analytical laboratory at the Rancho Los Amigos Hospital in Downey. Dr. Kleinman is a toxicologist, and he's been studying the health effects of exposures to environmental contaminants for 40 years. He has a master's in chemistry from the Polytechnic Institute of Brooklyn and a PhD in environmental health sciences from New York University. And he's the co-director of the Air Pollution Health Effects Lab at UC Irvine. He's published numerous articles in peer-reviewed journals, and he's considered an expert in particulate exposures. And so we're very pleased that he could join us. He's going to provide background on the air pollution effects of wildfire.
Well, thank you very much for that introduction. And I will be sharing my screen, which should work. And I think I want to let's see. There we go. It's a problem when you have the header thing. Okay, so I'm going to just briefly mention that my studies and my work is funded by a whole bunch of different sources, and it's a joint effort of a lot of people that provide the backup and the expertise that makes a lot of our work possible. I'm going to go through very briefly some implications of climate change and health, and how climate change and wildfires are interactive, and then get into we'll look at cardiopulmonary actually effects of wildfire smoke. And the question I would like to drive towards is, how does the difference in chemical composition of wildfire smoke make those particles different, or does that make particles different than our ambient particle exposures from non-smoke air pollution? And then I want to link this back to how climate change not only affects wildfires and a number of other things, but actually may have an implication on the actual toxicity of the particles that we're breathing. So exposure to health hazards related to climate change affects different people in different communities to a different degree. So our health outcomes are really a product of a lot of different influences, including social and behavioral aspects like race and ethnicity, poverty, the kind of housing and infrastructure you have. Also on the environmental context, how the land is used and who's living where. All of these things change our exposure pathways. And the extreme heat and poor air quality, reduced food and water, even changes in infectious agents will interact and change the health outcomes. So my health outcome may be different than your health outcome because all of these other factors are different, and they change my susceptibility and my vulnerability to air pollution. But the outcomes can be quite serious, and cardiopulmonary illness is definitely one of the things that are associated with the exposure to wildfires. This is just an example, and how the changing weather patterns will affect the levels and location of outdoor pollutants. And in this case, I found some data on ozone, which I thought was really very to the point. And what you can see is a map here showing change in daily maximum temperature. And as parts of the country have been affected by changes over several years now, we find that there are areas that are more vulnerable to getting warmer, and even some that have lower temperature. So we have a variety of areas where you have hotspots, literally. It turns out when you look at the formation of ozone, which is a secondary pollutant and driven by reactions with photochemicals generated from sunlight and from pollutants that are generated and mixed, like nitrogen oxides and VOCs, volatile organic compounds. You can see that the ozone levels have increased, and you can see that there's a really strong correlation with where hotspots are and where the ozone increases. And then when you look at deaths that can be attributable to excess amounts of ozone exposure, you can see that there is a really strong correlation with that. So these are associations, and don't necessarily mean that you can't really say for sure that there's a causal relationship, but these associations are statistically significant and strong, and they certainly provide the evidence that makes us concerned that as we move along, we're going to have increasing levels of pollutant driven health effects. Another consequence of climate change is that our incidence and frequency of wildfires is very likely driven by climate change. And as you can see here, this gray shaded area, this is the scale for the number of acres burned in a year, and you can see that it has ramped up from about from 1991 up to, let's say, an average of 8, and peaks to 10. And in terms of acres burned, millions of acres burned. So you can see that there's an increasing number of acres, and that was in 2020. I don't know that this is going to necessarily level out after this. But what are the consequences? So down below here, we have a 24, this is hourly PM 2.5 concentrations. And you can see we normally have spikes. Now, the 24-hour standard for PM 2.5 is 35 at the moment. And you can see that would be a little bit above where that red line is. And you can see the influence. There were significant wildfires here, and smoking incursions into the South Coast Air Basin from wildfires in 2019. Just as a reference point, this is July 4th, and this is the fireworks, and just shooting off of rockets, etc. So that particular day, you do have a very notable spike. But what we have here is clear evidence that on a short-term basis, we have exposures that are extremely high, and in some cases up to 3 times what the 24-hour standard is. So what does that mean? We have a fire, and this is from a fire of the crown of trees burning off. And I just want to point out what is produced, and this varies with the type of fire, the circumstances. And so this is just an example from what happens when you have a crown burning, but you do get a large amount of PM 2.5, and this is in the number of grams per kilogram of biomass burned, just to give you an emission factor. So you get 18 grams per kilogram of PM 2.5. You get elemental carbon, which is the black sooty stuff. You get organic carbon. And the organic carbon, you can see, is present in a lot higher concentration than the elemental. And this organic carbon coats the ash and other particles that are formed by either secondary formation processes or directly emitted. And so what you have is a particle that's kind of candy coated. And these organic compounds that coat the particle contain a lot of toxic, various toxic compounds. So you get organic carbon, elemental carbon. You also get a lot of inorganic compounds. And some of these are, when inhaled, can have effects on the respiratory tract as well, because these can generate free radicals when dissolved in the fluids of your lung. There are lots of volatile emissions, volatile organic carbon VOCs, and among them acetone, benzene, toluene. And then you have a whole slew of compounds that are in the ketone type compounds, which have active oxygens on them. And a lot of these acetonitrile and styrene and other compounds that have these oxygen compounds sticking off are often very irritating. And then you have naphthalene, butadiene, and other compounds that have additional health effects. So there are a lot of compounds in wildfire smoke that are very irritating and are known to induce adverse effects on the lungs and the heart. This is just a cartoon of some of the possible pathways by which inhaled pollutants can actually drive effects in the heart, because obviously the stuff is coming into your lungs. The particles are irritating and also cause inflammation. The irritating particles trigger pulmonary reflexes. There's nerve endings that run from the lung into the brain and then down to control the heart and the way your heart beats. And so these pulmonary reflexes, when triggered, can affect your heart rhythm and in extreme cases lead to arrhythmias and abnormal heartbeats. And eventually this can be life-threatening. The inflammation can generate oxidative stress. The oxidants can damage the inner lining of your arteries and veins and cause the endothelial cells that line the inside of the arteries to dysfunction, and also activate the white blood cells and platelets. And these can actually, these can promote formation of blood clots. And the blood clots, if they block vital arteries, either in the heart or the brain, can lead to a heart attack. It also leads to the development of atherosclerotic plaque and building up of plaques inside of the arteries. And then those plaques can be disrupted, and the little bits of plaque that get out can get into the bloodstream and block some of the microvessels in the brain or the heart, and again lead to a stroke or to a myocardial infarction or heart attack. So these are just a brief way of looking at it. And so in our studies, we're looking at some of these changes in heart rhythm as an indicator of potential adverse effects. Now, there's very good evidence that exposure to wildfire smoke can have a real effect. And I want to show you two ways of looking at this. So this is a study on cardiovascular outcomes after wildfire smoke exposure in California. And Wetstein and Associates looked at emergency department visits during the entire wildfire season, which in that year were from May to September, through September. And it included 8 of the counties. And you can see not the exposures were different from county to county, which is what we'd expect. And you can see there's a pretty strong range from light at about, in the light yellow areas, so this is light smoke exposure, to heavy smoke exposure over a range of 6 in terms of concentration value. So this top panel shows the effects on people, and it's broken out by age group. So this is the relative risk of showing up at the emergency room for cardiovascular, all causes of cardiovascular problems, all causes of cerebrovascular, so in the head, and all causes of respiratory. And the red ones are young adults, 45 to 64. The blue is adults 65 plus. And the green is the average. So let's just look at the average. As you go from light to medium to dense smoke exposure, you see that there is a real progression for all-cause cardiovascular, all-cause respiratory, and for cerebrovascular, it's a lot noisier. There are a lot fewer incidences of strokes, but you can see the overall pattern on the average is there. Young people and older people respond differently. So in the older population, you can see a clear trend, but very noisy. And the average, follows that same sort of trend. So with the smoke exposure, the light, medium, and dense, this has a very early on effect. So this is emergency room visits, on the day of smoke exposure. You come down here, and here what we're looking at on the y-axis is relative risk. So the risk of having one of these health outcomes. At the bottom is when did the effect occur? And so this is data looked at on the day of the exposure. The 1 represents 1 day later, 2 days later, 3 days later, 4 days later. So what do we see? For all-cause mortality, you can see that there is a significant increase. And again, we're looking at the smoke density. So the light, medium, and heavy density. And you can see that there's a clear increase on the immediately. And then there are still more people showing up 1 day later, 2 days later, 3 days later with effects. It appears to drift off by 5 days after the event. There are fewer people coming in. So this is all-cause cardiovascular. This is for heart attacks. And the heart attacks show a very strong response as a function of smoke density. This shows ischemic heart disease. So this is chest pains and also arrhythmias. The bottom line is that there are very clear patterns of effect due to the smoke exposure. And this is really phenomenal data in that this is looking at the whole state of California, or at least 8 of the 15 air basins in California. So a very large database and a large number of total individual records. And you definitely can see this has an effect. Now, I pointed out the chemistry of the particles. So ordinary air pollution, we have aldehydes and ketones and elemental carbon, organic carbon come out of the tailpipes of cars and trucks, power generation, all these other sources have the same thing, but the mix is quite different. And wildfire smoke is very irritating. I'm sure almost everybody's had the experience of being near a campfire and having the smoke blow in your face, and it's choking, partially because of the large amount of particles, but also because of these organic irritants that are attached to the particles. So the Florio Baker did a really interesting study. They looked at days, and they went over data for adults greater than 65 years of age in US counties where there were wildfires, and they segregated out the people who were living within 200 kilometers of 123 different wildfires that occurred during the period 2008-2010. And they associated, they looked at health outcomes on days with smoke and days without smoke. And they had some very good ways of segregating out those days. So they did a very good job statistically to do this. And so they looked at respiratory outcomes. They looked at cardiovascular disease, and we're looking as an outcome. This is hospitalizations for any respiratory outcome, hospitalization for any cardiovascular related disease, and hospitalization specifically for asthma, bronchitis, or wheezing. And the black dots represent the actual smoke days. So these are the days when there was exposure to wildfire smoke. These 3 different measurements are different ways of estimating the exposure. So the circles are exposure estimates based on models, the CMAC exposure, exposure model. The triangle is the CMAQ data and then augmented where it was possible with measured data. And the squares are just the monitored data alone. So this is a lot more scattered. There are a lot fewer data points here. And so the error bars involved are bigger. And then the white symbols are non-smoke days, and the black symbols are smoke days. So what you can see, and then the x-axis are the lags again. So immediate, 1 day later, 2 days later, 3 days later. And you can see that respiratory outcomes, there is an immediate effect, and even going out for a couple of days, you can see significant responses. Cardiovascular and differences between the smoke and non-smoke days sort of peters out after a day or two. For cardiovascular disease, there was not a clear change. So smoke days and non-smoke days, when you look at the percent difference in numbers of hospitalizations, normalized at 10 micrograms per cubic meter of PM 2.5. So they all represent the same sort of dose level that we're looking at. But you can see that the cardiovascular is not terribly different between the smoke days and the non-smoke days. It would be hard to tease out a real difference here. So statistically, we can't say that the cardiovascular impact of wildfire smoke is significantly different from that of air pollution for the same exposure level. However, for effects like asthma, bronchitis, and wheezing, there is a pretty clear separation. And at least for the immediate and 1 day lag, that significance is very, it is clear that the wildfire smoke tends to have a real effect. Again, because this is the monitored data, and you have a lot less of the monitored data, there does not seem to be this doesn't show up as well. But when you use the augment that data with modeled measurements, the differences are pretty clear. So on smoke and non-smoke days, there is a higher risk for asthma-related hospitalizations, including and also more bronchitis and more wheezing. So wildfire smoke may not be different, and I think these effects on the respiratory tract are very consistent with the irritating characteristics of the aldehydes and ketones associated with the wildfire smoke that are there more prevalently than in ambient air pollution. So we just heard a little bit about Santa Ana conditions. So I wanted to, this is a really interesting example of some of the toxicology work we're doing and how this all plays out. But this is a period from about 5 years ago when there were wildfires going on And you can see here, there were Santa Ana conditions. And you can see the smoke from a variety of hotspots blowing out over the ocean. And the Santa Ana conditions lasted for about a week. And you can see the intensity and the smoke started to build up. But as the Santa Ana conditions began to break down, you can see the smoke beginning to accumulate and age out over the ocean. And then as time progressed over the period of the week, you started to see the smoke beginning to swing back and go inland. And at the end of the week, the Santa Ana conditions had broken down, and now you had a mixture of this aged smoke and the fresh smoke coming back and exposing this whole area in Southern California. And as it happened, this particular wildfire occurred in the middle of one of my experiments. And in my experiments, I had been looking at the long-term health effects of air pollution on rats. And I had two different kinds of rat. Some of the rats were hypertensive, so they had high blood pressure. And I had a control population of animals that had normal blood pressure. And my hypothesis was air pollution would affect the high blood pressure guys more stringently. So these rats had miniature electrocardiographs implanted in their body. And we were able to monitor their electrocardiographs, their ECGs, and their blood pressure remotely using telemetry. So each of these guys had a little chip that broadcast their blood pressure and heart rate. We racked them up in these exposure chambers and brought them out to a site in Riverside and exposed them for 4 days a week, 5 hours a day. And the study was for a 4-month study. So over the course of the study, we were monitoring their blood pressure and their heart rate. And we also measured something called heart rate variability. Your heart doesn't beat at a constant rate. It goes up and goes down depending on what you're doing. You move around a little bit, your heart rate goes up a little bit. You breathe faster, your heart rate goes up. The heart responds automatically through the autonomic nervous system. So your heart rate is controlled by the pacemaker, which is in turn controlled by inputs from the parasympathetic and sympathetic neural pathways. So these are nerve pathways that go through your body and actually trigger a whole variety of things. But most notably, the response to things that get you excited, that create the release of adrenaline. And adrenaline is the flight or fight hormone that your body produces, and that causes your heart rate to go up and also can trigger your blood pressure to change. So the adrenergic, the adrenaline type effect is counterbalanced by a parasympathetic or a sympathetic pathway that slows it down. So we try to stay in balance So we have sympathetic and parasympathetic influences that keep our heart rate at the appropriate level. When your balance goes out of whack, your blood pressure and heart rate don't respond the way they're supposed to. And things like air pollution can cause imbalances in these things. So as we were looking at our, excuse me, at heart rate and blood pressure, so on this side of the panel, the SHR are spontaneously hypertensive animals. And you can see their blood pressure down here is a lot higher than the control animals. So a big difference in their baseline blood pressure. And you can see that on the red days, which are the days with air pollution, this is the animals were exposed to PM 2.5, concentrated PM 2.5 actually. And the blue lines are the animals that are exposed to air. So we exposed air and air animals simultaneously with our particle exposed animals. And you can see that the heart rate, as the animals got older, tended to go down a little bit. There's a lot of physiological reasons for this, but this is a normal tendency that we'd expect. But we also see that the heart rate suddenly started to change away from this pattern right around here. And at the same time, we saw changes in blood pressure, nominally about the same time. We didn't see as big an effect in the normal animals, but the normal animals were showing an increase in blood pressure due to the particle exposure over time. And we saw very strange shifts in our heart rate variability measure.
Michael, you have about 10 minutes left.
Thank you. Okay, so the pink circle shows you where the wildfire smoke actually showed up in the middle of my experiment. And you can see it is right at the time when our heart rates and blood pressures changed. And we found that change actually matched up with when the ultrafine particles smaller than 200 nanometers were really hitting our site. And this was the effect of the smoke, which is a mix of aged and normal smoke. So what does aging do? One of the things that change in the chemical composition of the smoke is the relationship between oxygen and carbon. So you can measure the oxygen to carbon ratio in smoke. And what you can see is as you age the smoke, and this is from a whole variety of wildfire events, and so they're not all the same incident. But you can see over the time, there is this pattern that the O to C ratio drops. Well, in our experiments, we looked at, does O to C ratio change this measure of heart rate variability? And in heart rate variability, your heart rate is supposed to respond to what you are doing, your activities. And when heart rate variability decreases, it means you've lost some of that capability to respond normally. And what we found in our experiments are that as the oxygen to carbon ratio drops, heart rate variability also drops. So there's, if we, and again, this is just a correlation, but age smoke changes the O to C ratio, it goes down. And we'd expect that particles with a lower O to C ratio to be more detrimental to your heart's ability to respond properly. And we also looked at how does the aldehydes and ketones that we seen are in wildfire smoke, how does that affect this whole thing? And again, when we have higher levels of aldehydes and ketones, we also have lower heart rate variability. So again, a potentially adverse effect is related to those aldehydes and ketones that are present in wildfire smoke to a greater extent than in normal air pollution. And then circling back to climate change, and this was something that came out of our data, but we looked at heart rate variability as a function of temperature on the ambient temperature on the days when we were doing our exposures. Now, the important thing to keep in mind is that our animals are being exposed at a constant temperature. They don't see the ambient temperature at all. This is the temperature at which the particles in the outside world that we expose them to were created. And so as the particles increase in or are formed at higher and higher temperatures, and this is just the normal range of temperatures over the days that we're doing our exposures, you see there's a pretty clear pattern that heart rate variability decreases from particles, more from particles that are generated on warmer days. This is interesting because these are the same days, but we strip that organic coating off of the particles. And you can see that there is no effect of temperature from the core particles themselves. So this is really probably related to changes in the organic components of the particles when they're formed. So I think this is a fascinating thing that tells us that climate change may actually change the nature of the exposures and worsen our potential heart-related effects. So to conclude, both wildfire smoke and ambient PM exposures are associated with cardiopulmonary sickness and death. Acute effects like asthma are more strongly elicited by wildfire smoke than by non-smoke particulate matter. On a day-to-day basis, days with increased temperature may be more associated with a decrease in heart rate variability, which may be a good measure of adverse effects. And we know that climate warming is going to increase the number and severity of wildfires. And so this is going to lead to, this is something we need to really drive our attempts to improve our climate change picture. So I want to thank you, and I'm open for questions.
Michael, you have a few questions in the chat, or I'm sorry, in the Q&A. Can you see those?
I am, okay, so here we go. Maybe I have to go to the Q&A. Okay. How how many people have had a heart attack due to wildfire exposures. And I really can't give you a number. What we were, I was looking at was an increase in relative risk. But there are a substantial number of people who showed up in emergency departments. So that's the best I can do on that answer. Department of Health, Public Health, can probably give you a more quantitative answer. How were healthy individuals with no underlying disease affected by the wildfire exposures? The healthier you are, the less likely you are going to have a serious effect. And the studies I looked at did not separate out entirely the individuals with underlying disease. However, the study of heart failure, where we were looking at in a study of heart failure, where they did clear that out, there was a substantial effect of PM exposure. So healthy people do have an effect. In patients with asthma, should we be recommending portable indoor air quality or other filtration devices? Again, this is, it seems that reducing your exposure to smoke and particulate matter is important. And there are some very good air filter units that can help clear that out, reduce your exposure. I think, especially for people who are sensitive. I'm not a physician, so I don't want to make a medical level determination, but just from my industrial hygiene experience and workplace exposures, reducing exposure using an engineering control is always preferable to other types of control. So I think it would be prudent for people who have respiratory illness, especially when there are extreme exposures, to avoid the exposures as much as possible. All right, any studies showing chronic exposure to wildfire smoke and an increase in cancer risk? There are some studies certainly showing that wildfire smoke contains carcinogens. Cancer, it takes a long time to show up. And so we are in the middle of an experiment now where we're all participants, because the wildfire smoke exposures are much more broadly affecting populations. And I just showed you some, this is just pure wildfire smoke data that I looked at here. When the wildfires start burning structures, the chemistry of that is much worse in terms of the amount of carcinogens. So I think the best place to look for these, the answer to this is going to be in the occupational health data. And I believe that the occupational exposure of firefighters will really inform that. And I believe the answer is that there are associations with increased risks of certain forms of cancer. Hi, Suzanne. Suzanne Paulson asks whether we control the mass concentration of PM your animals are exposed to. Yes, we do. Well, it's an ambient exposure. What we do is we concentrate the particles using a particle concentrator and then bring that into the animal's breathing space. So we measure it, but it's a real world experiment. So the concentration fluctuates from day to day. I've only got another minute, I think, on my time. So I'm going to, I'll just answer this one question from Tara. Have we studied how types of PPEs, N95 mask affect exposure and health effects versus no protection? And I have not done that, but just from knowing, again, going back to industrial hygiene experience, PPE does provide a major protection against respiratory insults. One last one I'll answer really quickly. Are other organs affected? Yes, your brain, your heart, your lungs, your liver, everybody's in there. So I will stop here, and I want to thank you all for the great questions and the attention.
Thank you so much, Dr. Kleinman. Okay, that was a great introduction to some of the toxicology. So our next speaker is Nico Schulte. He's with our local air quality management district, and he's going to be talking about health advisories during wildfire events. So this is a great segue. And also the use of the air quality index as a advisory tool during wildfires. So Dr. Schulte is an air quality specialist in the Planning, Rural Development, and Area Sources Division of the South Coast Air Quality Management District. His role has included forecasting the air quality index and developing air pollution advisories. Before joining SCACMUD, that's how I refer to it, he worked as an air pollution specialist in the research division for the California Air Resource Board. He's conducted research on the dispersion of traffic emitted pollutants, the measurement of pollutant concentrations in neighborhoods, and the application of dispersion models to interpret concentration measurements. Dr. Schulte has a Bachelor's of Science in Mechanical Engineering from Riverside and a PhD as well in Mechanical Engineering from UC Riverside. So welcome, Dr. Schulte.
Hi, good morning. Thank you so much for hosting this symposium. I'm very happy to be here. I think, let me share my slides.
Just a reminder for the people in the audience. Any questions, please put them in the Q&A. Don't put them in the chat because the presenter may not be able to see it on the chat. So please use the Q&A tab.
All right, so yeah, so I think this is a very important topic. Some of the highest PM 2.5 measurements that we see in the South Coast Air Basin occur on days with wildfires. And so this is very important work. So today I wanted to share some of the work we do to inform the public about the current air quality index. So this is particularly useful during wildfires because of the high PM 2.5 concentrations. And we think that this helps people to reduce their exposures to wildfire smoke. So this work is going to focus on the current AQI index map. So we updated this map in late 2020. So the updates that we made, they kind of improved the way that we can communicate the current air quality index to the public. The updates, with the updates, we actually incorporated consumer grade sensor data. Right now we're using only purple air data, but we're also planning to incorporate other data. And this makes the map more responsive to events like wildfires. I'll go over how we test the accuracy of the updated map. And then I'm going to go over some of the forecasting and advisories, the work we do for that. And finally, how you can use these tools, or how the public can use these tools to minimize exposure. So just a little background. The South Coast AQMD is the government agency responsible for regulating stationary sources in the 4-county area in Southern California. The jurisdiction includes 17 million residents, 3 air basins. So we have significant air quality problems. In portions of the jurisdiction, we don't attain PM 2.5 ozone and PM 10 standards. The ozone is particularly bad, mainly because of ozone. We exceed federal standards on over 150 days in a year. So this AQI data, I mean, it's very important throughout the year, not just during days with wildfires. So next I'm going to go over the real-time AQI map. Just a little background for the AQI. So this is a number that indicates how polluted the air is. As you can see in this table, it's divided into 6 categories at progressively higher concentrations and AQI level, from good through hazardous. And there's also associated health recommendations with each category. And so this is kind of based on essentially 24-hour aggregated concentrations, or like for ozone 8-hour averages or daily maximum concentrations. And this focuses on health effects that someone might experience within like hours or days after breathing in the polluted air. And the level of AQI of 100 is set at the federal standards. So above the AQI of 100, you start seeing more stringent sort of health recommendations to reduce exposures. Okay, so first of all, what is our AQI map? So in the past, there's been different sort of ways of displaying real-time air quality data. So essentially the map is like a snapshot of the essentially hourly data at that time. And so these figures are kind of different ways that various organizations use to display those AQI maps. So on the left is what we call the proxy method. And so this is what we use before the AQI map updates. And so what this is we assign a regulatory monitor to each of these polygons that you see on the map. And then that monitor drives the AQI within that polygon. In the middle, you can see what's used on Air Now, and this uses inverse distance weighting interpolation of the monitor data. And on the right is an example. This is from the Purple Air map. But essentially, there's different ways. One way to display the data is to show, the measurements at the locations where they're made. And so there's a few limitations that we kind of identified with these methods. The first one, you can't monitor everywhere. And so for like the proxy method and the Air Now method, sometimes it's not very clear to people where these measurements are made, like where they're coming from. And if the concentration that's in their area is actually driven by the measurement, or if it's coming from an adjacent area. For inverse distance weighting, it doesn't account for complex terrain. With maps like the Purple Air map, sometimes it can be hard to interpret the data. So there's a lot of kind of processing you need to do for that type of data to really interpret it in terms of an AQI. Which comes with those health recommendations. And so it's very hard for the public to interpret that data appropriately. And so for the proxy method also, sometimes the areas can be very large. And so you can imagine during like a wildfire, it can't really show where, like very accurately where those highest AQI impacts are occurring. And again, also for the purple air data, one important thing to keep in mind is that, this is only for PM 2.5. The AQI should really be based on all pollutant concentrations. So if you're just showing the measurement data at a point, it can be confusing to the public because, ozone concentrations may be in unhealthy AQI categories, but the public wouldn't be aware of this on the purple air map because it only incorporates PM 2.5 data. So our AQI map updates kind of address some of these issues. This slide gives a schematic overview of how the updated AQI map works. And so essentially what we do is we take gridded chemical transport model data, and we combine that with our regulatory monitor measurements and the consumer grade sensor data, like the purple air data. And the way we combine these is we essentially allow those measurements to sort of push on that gridded model data surface to shape the concentrations. And we do this in such a way that at the measurement locations, at the regulatory monitor measurement locations, the AQI is equal to those measurements. And this gives us a sort of gridded AQI map like you see on the right. So this is how it works for PM 2.5 and ozone. For the model data that we use is the National Air Quality Forecast Capability Model. So this is a twice daily forecast that also blends in measurements into that into the forecast, and this makes it essentially unbiased. And it's kind of the most accurate, one of the most accurate grid forecasts for our area. For NO2 and CO, we just use a mathematical interpolation of the regulatory monitor data. And for PM10, we use a mathematical interpolation of PM coarse, which is the difference of PM10 minus PM 2.5. And then we add that to our estimated PM 2.5 field. So this is an example of kind of the result that we get with this updated map. You can access the map at the website on the top, or you can go to our the mobile app, the South Coast AQMD mobile app. So on the map, you can see, it's broken into these grid cells. You see the South Coast AQMD jurisdiction, and the AQI is overlaid on top with the AQI colors. And so again, the green and yellow here is sort of below the AQI of 100, below the federal standards, and then the other colors are at higher AQI categories. And the AQI and the color that you see here is the maximum of the AQI from all of the pollutants. So again, we use ozone, PM 2.5, PM10, nitrogen dioxide, and carbon monoxide. So the AQI is the highest of those pollutants. So this is kind of a zoomed in shot. You can see the grid cells that we use or places have a 5x5 kilometer resolution. And then we also show the locations where the regulatory monitors are as circles on the map. And we think that this helps people understand better that, where the sort of the high quality measurements are actually made, and then in between them where the data is actually estimated using these mathematical techniques that blend in other data as well. And this map is updated on an hourly basis. If a user clicks on the map, they can see the name of the place, the grid cell that they're clicking on. They see the AQI category. They also see the dominant pollutant, so in this case, ozone. And then there's a table underneath where it shows the AQIs for each of the pollutants in that area. And you can see which of those AQIs is actually based on the regulatory measurements in that area and which ones are calculated. And at the bottom, there's a link that people can click on to take them to the health recommendations for each AQI level. So they don't have to sort of dig into what the AQI is to figure out what they should do if the AQI is high. So the AQI I mentioned is sort of based on essentially 24-hour sort of data. So the way that these sort of hourly updating maps are made is based on an algorithm called a nowcast. And so I'll go into this next. So for ozone, the AQI is based on an 8-hour rolling average or the 1-hour daily max, and PM2.5, it's 24 hours. So in order to make the map more sort of responsive, or the current AQI more responsive to current conditions, this EPA developed this algorithm called the nowcast. And essentially what this does is that if the air quality is variable in the past few hours, then the nowcast effectively uses a shorter averaging time. So if you have like very spiky concentration, then the PM2.5 that you see, for example, is sort of equivalent to like a 3-hour average. If you have sort of steady concentrations, then it becomes more like a 12-hour average. And so there's sort of like a kind of continuum between those. And for ozone, there's actually an update to this. It uses like a partial least squares regression to predict 8-hour ozone. And so actually the AQI map was updated to use that partial least squares nowcast. But the idea is the same, to be sort of more responsive if the air quality is variable at the time. So we think that this map is one of the most accurate sources of data for the current AQI. And one of the reasons is that we incorporate, the model data, but also the PM2.5 sensor data from the purple layers. So I'm going to go into, in the next few slides, I'm going to go over how we use that data and kind of things to be aware of when you're using this type of data. Okay, so kind of by way of background, this is a snapshot of the purple air from the purple air website of the purple air map. And so each of these points on here is a sensor that measures PM2.5 concentrations. So there's on the order of like about 700 in 2021, there are about 700 sensors in the South Coast AQMD area. So this is kind of a great spatial coverage and much higher than the amount of regulatory monitors that we can deploy. And on the right, you can see a snapshot of one of these purple air sensors. You can see they're kind of very small, they're easy to deploy. So they're very easy to use, and that's one of the reasons why they're so popular. So one of the reasons that our new map is kind of more accurate is because we use this data to fill in the gaps in between the regulatory monitors. In the future, we're planning to add other types of low-cost sensors, but so far this is the only one we use. So we're having plans to deploy and to integrate some air quality AQI sensors, and we're working with the Air Quality Sensor Performance Evaluation Group at South Coast AQMD, sort of find hosts for those sensors and to develop algorithms for how we incorporate those into the AQI. Okay, so we think this data is very useful to estimate the current AQI. There's a few issues that need to be sort of resolved with the data first. One of the main ones is that the air quality measurements really need to be placed so that they're representative of what you're trying to measure. And so the AQI map is supposed to represent essentially the general AQI within each of those 5 by 5 kilometer grid cells. A purple air sensor, if it's going to be used in the map, shouldn't really be placed, next to your fireplace exhaust or next to a barbecue or something like that, because that would, it would essentially bias those AQIs because it's a very hyper-local kind of source. Next, the data also needs to be calibrated or corrected to ensure that it's sort of accurately reporting the AQI. And I'll go over that in the next slides. The data also needs to be reliable. So you can imagine that the lower cost sensors, they're deployed by the general public. There's not really quality control or sort of as much maintenance going on with these sensors. And so they could break or get clogged or something go wrong with them. So those types of sensors, if they're not working, they need to be removed from the data set. so that they don't bias the AQI. And you can see on the right of this slide, there's like a snapshot from the AQI map, and most of these sensors are reading, about the same concentrations, but then there's one sensor that's much higher than the others. And so this sensor is broken. That's the reason it's measuring this high value. And this could be very confusing if you're not aware that this could be an issue with the data. And finally, the data needs to be averaged correctly. Usually the lower cost sensors can provide high time resolution data, like you can, for example, get 10-minute or a few minute data. But the AQI, it's sort of designed for, it's based on essentially the 1 hour averages and the use of the nowcast algorithm to combine those 1 hour averages and calculate the AQI. So that needs to be done with this data to really interpret it in terms of the AQI. And the AQMD AQI map handles these issues. All right, so there's essentially 3 major steps that we take to use this data. The first, if you look at the box on the top left, is that we quality control the data. So there's a picture there you can see inside of each purple air, there's these 2 sort of identical OEM sensor elements within the housing. And so what we do is we compare the 2 simultaneous measurements from those 2 channels, and we apply some statistical criteria to remove poorly performing sensors. So the way we do this is we look at a 2-week window of, so the latest 2 weeks of data for each sensor, and we compare the data in that window to determine if there's any potential problems with the data. And then if we identify that, then those are removed. Second, on the bottom left, is we calibrate the data. So the AQ Spec group at South Coast AQMD has done a lot of work to do analysis of the quality of the data from these sensors. So they co-located many sensors with regulatory monitors. And so we used that co-location data to develop a sort of empirical algorithm that we use to adjust the purple air measurements to make them essentially unbiased relative to the regulatory monitors. And this also incorporates correction for the influence of relative humidity on the readings. And then finally, on the right side, you can see sort of a snapshot of a 3x3 section of the map. And so what I want to illustrate is that, and I mentioned this before, if an individual sensor is located next to your fireplace, it's just going to read high values every time you turn on the fireplace. And so we don't see where these sensors are located and what sources may be nearby them. And so the way that we deal with this issue is that we only trust sensors sort of in a group. So what we do for the map is that we combine all the sensors within each of these grid cells together. We average their data together and we look at the variance of the data. And so if there's a lot of variance in the data, then it's not going to be weighted very highly in our calculations. And I'll go over that in the next slide. And we also require that there's at least 3 sensors to sort of trust that average. And on the picture, you can see, some of the sensors are in blue and those ones are used for the calculations in the AQI map, and some are in red. Those ones are not used for the calculations. And so some of those may not be used because there's too few sensors in the grid cell. There needs to be at least 3. And some of them may not be used because they don't pass the quality control checks for the step 1. We're also deploying a handful of purple air sensors and the aeroqual AQI sensors. For sensors that we deploy, we make sure that they're sited appropriately. And so we don't use the step 3 for those types of sensors. Oh, before I forget, we're working on some updates to the AQI map. on the slide before, you may have seen the map that showed the number of purple air sensors in the South Coast AQMD jurisdiction. You can see that they're actually much more heavily distributed sort of in the coastal areas, around central LA, and there's much lower density sort of in inland areas. And so this is actually kind of a problem for this step 3 because it needs a sort of minimum density of sensors for them to really be used in the calculations. And this poses some problems for us. We really do want to use those sensors because it helps to improve the accuracy of the map. So what we're working on is a way to sort of use an adaptive neighborhood size for this step 3. So instead of requiring 3 sensors per grid cell, we're also allowing sort of an expanded area around each sensor. So we're looking at progressively larger areas and looking at the purple air data within those areas to see if we can find sort of consistent measurements around each sensor, and then we'll include them in the map. So this is sort of an update that we're working on, and this will really help us incorporate more of the sensor data in inland areas. Okay, so we made these updates in 2020, and so the sensor data wasn't really used widely for these kind of applications at the time. So we needed to check how accurate the data is, and if it makes sense to use it for this application. So in the next few slides, I'm going to go over some of the analysis we did for looking at the calibration algorithms that we developed, and then also the accuracy of the map with the data incorporated. And so on this slide, what you can see is on the left figure is the differences between the regulatory monitor measurements of PM2.5 and the purple air sensor measurements of PM2.5 from the co-located measurements that the AQ-SPEC and other groups have done. And on the right is the same data set, except the purple air measurements have been adjusted based on this sort of calibration and correction algorithm that we developed. On the x-axis is each of the sites where we used co-located data. So you can see there was 6 different sites in or near our jurisdiction that we took data from. And again, this is all hourly data. So this is data that, it passes the QC checks and has been hourly averaged, and then it goes into the sort of calibration steps. Okay, and so the major sort of thing to see here is that there's sort of a site-by-site sort of bias in the sensor data. The sensors tend to overestimate the concentrations. These box plots are showing you sort of the median concentration in the center line, and then the 25th and 75th percentiles. And then also the whiskers are showing the 5th and 95th percentiles of the data. So you can see there tends to be overestimation, and there's a side-by-side sort of difference in the amount of bias of the data from the sensors. And on the right, once we apply the calibration algorithms, that amount of bias is reduced, and the side-by-side sort of variation of the bias is also reduced. And so this indicates to us that the algorithm is doing a good job of correcting the data. One major source of measurement bias in the sensor data is that they're affected by relative humidity. So at higher relative humidities, they tend to overestimate more. And so these plots show similar data as the previous plots from the previous slides, except on the x-axis, we've binned the data into different relative humidity bins. And you can see, between 90 and 100% RH, there's a large overestimation from the sensors. But when we apply the calibration and correction, that sort of overestimation at high RH is reduced significantly. And so the boxes are more like flat around the x-axis line. And so this indicates that the relative humidity correction is working well to adjust the data. And on the bottom are just the scatter plots showing the hourly data, which we used to develop this correction algorithm. And this just shows to us that the algorithms are working well. We've also looked at like more data during wildfires and other sites sort of more recently. I haven't included the slides here, but the algorithms seem to be actually performing well on that new data set. I would say they're about equivalent to sort of the algorithms that the US EPA developed and that they use to correct this purple air data. Okay, so one important thing to keep in mind is, so this is still sort of low consumer grade sort of measurement data. And it's still not a good idea to sort of trust the data 100%. So like when we put a regulatory monitor, we do a lot of work to make sure that data is accurate and valid and cited correctly. So even with all the work that we do to use the purple air data, we still don't have as much sort of trust in that data as we do for the regulatory monitor data. So for us, it's not, we think it's not useful to sort of force the AQI map to show whatever the purple airs are reading, because it may not be accurate, or it may not be as accurate as the regulatory monitors. So this slide it's kind of a complex slide, but it kind of goes into how we use that data and incorporate it into the AQI map. So in this slide, you can see it's a schematic. On the x-axis is sort of representative of your spatial position. So you can imagine this to be like west to east location within the South Coast Air Basin or something like that. And on the y-axis is the concentration, the PM2.5 concentration on the map. And so just focusing on the left figure right now, imagine these blue dots are regulatory monitor measurements. And so the way that when we combine the regulatory monitor with the model data, we do this in such a way that we're essentially pushing on that model data surface of PM2.5, and we push it to be equal to the measurements at the regulatory monitors, wherever those regulatory monitors are. And so it's essentially an interpolation of the regulatory monitor data with the help of the model data to kind of fill in the gaps. When we incorporate, so now focus on the figure on the right. When we incorporate the sensor data, the PM2.5 data, we do the same thing, except for grid cells that have sensors, we allow that data to sort of push on that concentration surface, but we don't force the data to necessarily be equal to the measured PM2.5 from the sensors. And the amount of deviation, so you can see in this box, these orange squares are representative of sensor measurements. They push the data towards the measurement, but there's some deviation of that sort of smooth line, the interpolated line. And so the amount of deviation between those two data is proportional to our estimate of kind of the uncertainty of that purple air data. If there's a lot of sensors in a grid cell, we allow less deviation. If there's only a handful of sensors in a grid cell, we allow more deviation of the map from those purple air data, because we trust that data less. And so this way, we're essentially weighting the sensor data relative to our estimate of its uncertainty.
Nico, you have about 8 minutes remaining, and you have some questions in the chat.
Okay, thank you. So we've done some extensive analysis of the performance of the new AQI map. And so on the left side of this figure, you can see kind of the primary method we used was leave one out cross-validation. The way this works is you essentially take out one monitor from your data set at a time. You use the AQI map to interpolate at that location, and this gives you an estimate of the interpolation error, and you can calculate the root mean squared error from that. The table on the right shows the root mean squared error for each of the pollutants, and you can see the updated AQI map tends to have a lower root mean squared error for all the pollutants. So we think this shows that the data is accurate. Additionally, we find that this excels during wildfires. So this shows like a movie of the Woolsey fire back in 2018 and how the map would have looked during that time. And you can see that there's the EQI map is sort of capturing sort of the spatial variation of the plume. And especially at the coastal areas where there's a lot of purple areas, you can kind of see where that data is kind of helping to drive the AQI. And here on this map, the regulatory monitors are where all the circles are on the map. And we also calculated the RMSE during days with wildfires and found it was also lower than the other methods. Additionally, this helps us to blend in, temporary monitors that we deploy. So we use EBAMs to kind of help shape the AQI map during wildfires. And this way we just put the lat long of the EBAM into the map and it automatically gets incorporated in the calculations. All right, so I wanted to shift gears a little bit. I'll go over this sort of quickly. Some other tools that you can use or that the public can use to kind of understand the current AQI. So we do forecasts of the AQI. So we also do forecasts during wildfires. So this slide just kind of shows some of the data we look at when we're forecasting. We use webcam data, satellite data, and smoke models, mostly from HER smoke and blue sky. And we build this into our forecasting to try to estimate what the, try to forecast the PM 2.5. This gives kind of an overview of how we do this. I think I'll skip this slide for now in the interest of time. We also developed something called the cleanest time of day, which is kind of, if you go to our website to look at the forecast, you can see we have this kind of recommendation for the cleanest time of day. And this is based on the NOAA NAQFC model predictions. And we try to help people to understand, when AQI might be the lowest during the day, when they could, when might be the best time to do outdoor activities, for example. And we also provide like hourly forecasts based on that model data. This is based on PM 2.5 and ozone only. And actually during wildfires, we won't show this kind of data. It's less reliable during wildfires. So during wildfires, we mostly focus on the forecasting and of the 24-hour AQI and also on the advisories. Okay, so how do you use these tools, like to try to minimize exposure, or how can the public use these tools? So, I mean, you can check the current AQI on the AQI map. You can also, if you click on the grid cells, as I mentioned before, you can see if the measurement, if a regulatory monitor is actually at that location and has measured PM 2.5. So the map is more accurate if the measurement is at that location. So this can help you understand, where that data is coming from, and how to trust that data. If you smell smoke at your location, even if the AQI map is not showing a higher AQI, it's important to reduce your exposure because the map only updates every hour, and if the wildfire plume, for example, doesn't hit a monitor or purple air sensors, then it won't show up on the map. So it's important to keep in mind when you're looking at the AQI map, kind of where that data is coming from. I think one of the most important resources is our advisories. So you can go to this link to see the advisories. And we try to give a prediction for the next day where you might see smoke impacts. And we also give a map showing where we expect smoke impacts. All right, and so what do you do if you're seeing advisories or higher AQI in your area? So, I mean, sign up for alerts to see those. And then these are some of the recommendations, that the public could take to sort of reduce their exposures. So essentially stay indoors, run your ECG on recirculation, don't do vigorous activity outside, don't, turn on your fireplace or candles inside, only use, the like respirators, like N95s or P100s. Smaller particles from smoke won't really be filtered out by like dust masks very effectively. Yeah, so we think this these tools will help the public reduce exposures and reduce this kind of misunderstandings of the AQI. And you can find these at our website and in our mobile app. So let me just take a look at some of the questions. Oh, there's a lot of questions here. So I'll just try to go over some of these.
And Nico, you can also type answers to the questions as well.
Yeah. Yeah, so I can go over some of these like in the next, I'll definitely go through these and try to type some answers.
Nico, you have 10 minutes for Q&A.
Oh, I see. Okay.
Yeah, we just wanted to allow time for Q&A, so we wanted to give you a heads up.
Sorry, I thought your time warning was including the Q&A. Is that including right now, or is that at the end of this?
No, I'm sorry. Yeah, we should, so that's my mistake. So Scott is on in 10 minutes and we should allow time for a break. So is there one or two questions that you think would be most helpful to the group?
Yeah, so I mean, equipment that we use, so we use beta attenuation monitors. I mean, it's probably possible to schedule a visit. I mean, we have a contact form on our website. You can contact us there. Our group actually answers a lot of public inquiries, so yeah, just send us an email. We don't have any plan to use data from clarity sensors at the moment. Right now, we're using purple air data and AQI data. I'm not really familiar with the clarity sensors. So as as more sensors are deployed, we look at them once we start seeing a lot of sensors in our area, or we see a lot of kind of use of those. Yeah, I guess I should have gone more into the purple airs. Maybe I'll type an answer there. Well, I think I'm out of time, so I'll go over these and I'll try to type some answers.
Thank you, Nico. All right, so let's reconvene in 10 minutes because I think we need to allow everyone a minute to get up. So we'll see you at 10:40 and we'll hear from Scott Hauswirth at that time. Thanks again, Nico. All right. So it's 10:40. So we're going to get started again. So I'm going to introduce Scott Hauswirth, who's one of our own CSUN faculty in the Department of Geological Sciences, where he's an assistant professor. So after obtaining his bachelor's degree in Earth and Environmental Science, can you guys hear me?
Yes, we can hear you, Katie.
Okay, did you hear my introduction so far?
Yes.
All of a sudden, I couldn't remember if I'd hit the unmute. Okay, so his bachelor's degree in Earth and Environmental Science from Wesleyan. He worked for a number of years in the environmental consulting industry, conducting investigations and cleanup activities at contaminated sites, and then returned to academia, getting his PhD in environmental sciences and engineering from University of North Carolina, Chapel Hill. So he continued on there at UNC as a postdoctoral researcher before he joined the CSUN faculty in 2016. And his research focuses on improving the understanding of complex non-aqueous phase liquid, or NaPl, NaPl contaminants, in developing and testing methods for contaminant remediation and investigating the behavior of non-Newtonian fluids in porous materials and investigating the fate and transport of contaminants in surface water systems. All right, so welcome, Scott.
Great, thank you for the introduction. Let me get my slides up and running. So I'm going to shift gears a little bit, get us out of the air realm for a minute here and into the aquatic, and let's get my thing set up here, into the aquatic and terrestrial realm, and going to be talking about a project that we've been working on for several years, looking at the effect of the Woolsey fire on water quality in the Malibu Creek watershed. I wanted to first acknowledge a few people, my co-PI, Priya Ganguly, who've been working with really closely on this project for the duration of the project, as well as the numerous students who have helped out, especially Michael Kushner and Christian Hoover, who really took the lead on a lot of the field sampling and analysis that I'll be talking about. Before I get into that project in particular, I want to mention how I got into this. As Katherine mentioned in my introduction, my background is actually in groundwater remediation primarily. Wildfires and even surface water issues are relatively new to me. And I got into this thanks to a geography student at CSUN, Louis de Vera, who was working on a geomorphology project in the Carpinteria Lagoon. And he'd been working there for a while, looking at sort of sand dune changes and so forth, and came out there one day and his site was drastically changed. Play this quick little pan video here. The lagoon was filled with all this debris from the Thomas fire. There'd actually been some debris flows that brought this material down. He was sort of investigating this and saw on this far right picture all of this charred material that had made its way into the lagoon. And he sort of sought me out and asked, is there contamination associated with this? That my site's totally different. In fact, his sand dunes, I think, were washed away. So he was looking for a new direction in his project. And my answer was, I'm not sure. Let's look into this a little bit. And I said, go ahead and collect some samples. I'm familiar with compounds called PEHs that I've worked with from a groundwater perspective, and thought they might be relevant to wildfire water quality issues. So he collected these samples. I was sort of set up to analyze them. We were sort of developing methods on the fly. But before I get into that, just want to sort of pause and talk about what these compounds are, these PEHs. It stands for polycyclic aromatic hydrocarbons. It's a class of compounds that are basically made of these fused benzene rings, if you're not familiar. So all sorts of different configurations. These images show the 16 EPA priority PEH pollutants. But there's many more. There's hundreds of individual species, really thousands. And part of the reason I thought these might be relevant is they're formed during any sort of incomplete combustion of organic material. So that would include wildfires. They're also present in all sorts of other sources. They're in crude oil. They show up in auto exhaust, especially diesel exhaust. They're in particulate matter in atmospheric sources. They're in road runoff. And the reason they're of interest is that they have some nasty properties. Many of these compounds, especially the larger compounds down sort of the bottom two rows, are cancer-causing, carcinogenic. They can have negative reproductive effects, and they can be quite toxic to aquatic organisms as well. A couple other properties worth mentioning that are going to be relevant to this study. They're not very water soluble, so they're hydrophobic, which means that they end up sorbing to soil particles, to particulate matter in the water, to organic material that may be in the sediment. We do know they can bioaccumulate in lower trophic level organisms. It seems that they don't really biomagnify up the food chain, but they're at least at sort of accumulated levels in some lower organisms. Another thing to note is that they can stick around in the environment for a while, especially if they end up somewhere in the dark without a lot of oxygen. They can stick around for literally millions of years. In fact, I've done some work looking at pHs in paleosols, so fossilized soils that are 15, 20 million years old. We're still able to detect them in those materials. So they're hanging around for a while and could potentially be a sort of long-term source of environmental concern in sediments. So with our sort of makeshift methods, we did analyze Lewis's samples. The results weren't too exciting. We found 15 of the 16 compounds we were looking for at mostly low concentrations. But there's a couple compounds that were approaching levels where there could be some effects on aquatic life. As I mentioned, we were sort of making these methods on the fly, so this got me interested, but this was sort of just a start, we'll say. And so after this, I started going out and collecting soil samples from various burn areas throughout Southern California. I was interested in looking at how much of these pHs are generated during a wildfire, how much is building up in the soil, and then how long does it stick around in the soil? Is that something that's going to stay there for years, or is it gone fairly quickly? So I collected over 50 soil samples. Actually, I think I'm up over 150 now, from a number of fires, and I collected sort of immediately after the fire in some locations and up to 20 years later. So I was looking at old fire burn maps and sort of correlating age to sort of years past the fire. And sort of when I was in the midst of this, the 2018 wildfire season hit, and we had the Woolsey fire, which hit really close to home for us at CSUN. It was about 10 miles from us, and I live even closer to it. I could actually see the fire from where I live. So that really shifted my attention, and it shifted it partially because I knew, being familiar with the area, that this was a significant watershed that burned in this process. So just to orient where we are here, this is Malibu down in the bottom. Santa Monica would be about 10 miles to the east. CSUN's 10 miles to the east up this way. Ventura would be 20 miles or so to the west. And the black outline shows the extent of the Malibu Creek watershed, and the red area is the extent of the Woolsey fire. So about 2/3 of the watershed actually burned in the fire. It is a fairly ecologically sensitive watershed. There's numerous endangered and threatened species that live there, including numerous aquatic species. And it's also somewhat of an interesting study site in that there's a lot of variation in terms of the land use. There's areas like Westlake Village and Thousand Oaks that are pretty heavily developed. There's also lots of pretty much undeveloped land. There's different terrains, there's different vegetation types, and the burn intensity varied significantly over the burn area. So the sort of northeast part was relatively low burn intensity, where we had much higher burn intensity in the southwest. So we started with a very generalized question of how did this fire affect the water quality in the watershed? To give some background on the types of things that could be affected, we sort of did some basic research. At the point we started this study, there was actually relatively little published on the effects of wildfire on water quality. It's ramped up a lot just in the last few years. But in a general sense, the types of things that would be interested in are things like increased sediment loads. So getting a lot more sediment into the watershed, into the water system. Might see increased metals concentrations, might see increased nutrients like nitrate and phosphate. And then again, the pHs, like I mentioned, we may expect to see higher concentrations of those as well. So why would we see these changes? Well, when we burn vegetation in the fire, first of all, that's releasing all the metals and nutrients that are sort of trapped in the vegetation, and that's concentrated ash. Some of it also goes off atmospherically. We're directly producing pHs in the burning process. And then we're also reducing the land cover, burning roots. So we're sort of taking away some of the stability and sort of protection for the soil. The heat of the fire is also directly changing the physical and chemical properties of the soil. And we also get something really interesting happening in wildfires. We get the formation of these hydrophobic coatings on soil. And essentially what happens is organic material in the soil heats up, gets vaporized, and cools on soil and creates this kind of like waxy coating. And the images here are showing this hydrophobicity in action. This was in an area burned by the Thomas Fire. You can see one little drop of water on this chunk of soil and then this larger drop in the foreground. And it's a little hard to tell from the picture, but these are like beaded up like it would be on a freshly waxed car. And it stayed that way. We watched this for 10, 15 minutes and it just stayed beaded up on the soil. So what do these things actually do? Well, it drives increased erosion. We have increased risk of debris flows like we saw in Montecito after the Thomas Fire, like we saw in Carpinteria. And so that's going to bring a lot of material into the watersheds. There's been reports of erosion rates of up to over 30 times normal in the first year after a fire. So huge increases in the amount of material. And besides actually generating and concentrating our contaminants, the PEHs and metals, they're also, these compounds are also tend to be particle associated. So they're sticking to these soil particles that are making their way into the watershed. So we're going to get more just by mobilizing more of this material. So we developed a more well-defined project after looking into this some, and we essentially want to better understand how we generate PHs and other compounds, how we mobilize pH and metals into watersheds, where they get deposited, and how long they're going to stay around in the system. So specific things we're looking at is how these concentrations change over time in the watershed. We're also interested in specifically the longer term effects. How long do they stick around? How long do the effects stick around, I should say. And also sort of, I mentioned that the Malibu Creek watershed has various land uses and terrain types. Can we sort of get any information about how those will affect the water quality effects? So we set out pretty quickly after the fire itself to start sampling the area. We identified 11 sampling sites shown here as the numbers 1 through 11. We managed to find locations on all the main tributaries. So the main trunk of Malibu Creek, where it heads off to the west, Medea Creek, Las Virgenes Creek up to the north. And then sort of our background site is Cold Creek, which had no fire at all within the drainage area. So it was kind of a nice comparison site. And we were really focused on capturing rain events. So getting samples when we had major rains. So this plot is showing precipitation in black. The blue X's represent where we collected a sample, when we collected a sample. And so we got many of the large rain events. We also sampled periodically during the dry season. We did run into some logistical issues, like we missed this major rainstorm because it was on Christmas Day. We also had to sort of stop sampling during COVID, so we missed a couple of major rainstorms then. But overall, we've captured many, at least, of the major rains since the fire. So we were collecting water samples at all 10 of those sites. We were also collecting soil samples at 2 of the sites. We sampled during each of our sampling events. And then we also periodically over the course of the 3 years did sort of a wider geographical area of sampling. We had some fun, in quotation marks, going out sampling. So just some quick pictures of our adventures, lots of getting soaking wet. And bushwhacking through various brushy conditions to get our samples. Some more photos of a rain event shortly after the fire. And wanted to point out for anyone who's not familiar, there's big differences in these streams between when there's rain and when there's not. So the picture on the left shows a section of stream that is we're sampling during a rain event, and you can see how high the water is. The right picture is that same stream during dry time. It's a tiny little creek that's inches deep. So it's a very flashy system. A little bit of rain really brings the water up, and sort of huge differences in the character of the stream depending on whether it's raining or not. So we set out to sort of set a broad net, I guess you could say, to look at the different water quality impacts. To date, we've analyzed all the samples for PEHs. We've measured the suspended particulate material, or SPM, in the water samples. We've done field parameters and anions. We have some other analyses pending. So things like mercury and trace metals. Due to the pandemic, we had delays in getting our instrumentation up and running. So we have our samples preserved, and we'll be running those soon, the next few months, hopefully. As far as the pH analyses, these were actually run in-house. So we extracted all of our soil and water samples. We concentrated those extracts and then analyzed them by GCMS, which is shown here on the right. And if you're not familiar with gas chromatography, mass spectrometry, basically what it's doing is separating out all of the chemicals. We can see on the right a typical chromatogram of burned soil. And essentially each of these peaks represents an individual chemical compound. And using standards, we can quantify the concentration of those in our samples. So we've come a long way since those early analyses. We're now analyzing over 200 different compounds, mostly PEHs, as well as some alkanes and other compounds. And to sort of fast forward to the results here, looking first at the soil concentrations, it's sort of an interesting thing. We see a pretty significant increases in those concentrations after the fire, as we'd expect. So we'd happen to have collected some background samples within the Woolsey burn area before the fire, just coincidentally. And those are the black X's here. So we do have some low levels just as sort of background, but nothing like we see right after the fire. We're in the several thousand microgram per kilogram range for total PEHs. But we do see a really rapid decrease in those concentrations in the months after the fire. So really within 5 or 6 months after the fire, we're essentially approaching background levels. There is sort of a strange effect where we see what appears to be a slight increase in later years. I'll come back to that in a second. And also just wanted to note that this is what we've seen from the Woolsey fire is really consistent with what we've seen from other fires. Again, within about a year at most, we're approaching sort of our background levels of PEHs in the soil. So the little bit of a caveat here is that we're losing lots of the overall pH mass from the soil, but that's not evenly distributed over all the compounds we're looking at. So if we look at the figure on the right, the blue lines represent immediately after the fire. And you can see the concentrations are dominated by these smaller 2 and 3 ring PEH compounds. Those are almost entirely lost. We're losing 80 to 90% of those compounds in the first year. So the green bars represent a year after the fire. And then we're continuing to lose a little more into the second year, shown in red. But if we look at the higher molecular weight compounds, the 5 and 6 ring especially, we're losing very little of what we started with, and in fact seem to be actually increasing in those 6 ring compounds. Why is this important? Because these higher molecular weight compounds are the ones that are the toxic and carcinogenic compounds. So we're losing sort of the compounds we aren't as concerned about, and all the more toxic compounds are sticking around. Wanted to just quickly mention that there's multiple mechanisms that could contribute to the losses of these compounds. The fact that we're primarily losing 2 and 3 ring compounds suggests that a lot of this is volatilization. So we're just evaporating off some of these compounds. But we do also have photodegradation, at least for compounds right on the soil surface that are going to be degraded. These can be biodegraded. And of course, we also have erosion of soils that will move away these compounds. Shifting gears to the water side of things, this is showing the results of all of our water analyses. I want to point out that our y-axis here is a log scale, so big changes as we move up and down. And our first rainy season, we see huge spikes in our pH concentrations in the water. And each symbol here represents a different sampling site. And that pretty rapidly drops down, similar to our soil samples in that late first rainy season into the dry season. But we do see spikes again the second rainy season. So we had 2 main rain events that were captured, 3 actually, where we see spikes, nothing near what we saw, about an order of magnitude lower than we saw the first year. But we continue having those spikes, at least at some of our sites, into the second and third year after the fire. So we're seeing at least some persistence to these pHs in the system. As far as the sort of toxicological and environmental impacts of these, worth mentioning, first of all, that we don't exceed maximum contaminant levels for drinking water in any of these samples. In fact, we're well below those. But if we look at more stringent criteria like EPA's human health criteria for ambient waters, we're regularly exceeding these, at least in those spikes that we saw. And in fact, in some cases, in the case of benzoate pyrene, we were up over 1,000 times those criteria in some of our samples. We did also look at some other criteria, things like the California Public Health Goal for benzoate pyrene. Canada has a somewhat better, I guess we could say, set of guidelines. So we did compare to those, even though we're not in Canada, and we did have many exceedances of those values. And sort of just wanted to quickly show how many exceedances we had and how that changed over time. So we're, as I said, regularly exceeding those criteria in the early first rainy season, and then it really declines. We do see some exceedances in later years. Interestingly, our sample just this past December is the most we've seen since our first year, which is kind of interesting. I did also want to point out, this isn't a complete picture of the toxicity. Those are sort of where we have criteria. I mentioned that there's thousands of different pH compounds in the system, and many of them have not been studied as far as their toxicity. We sort of assume that the drivers are the ones we have standards for, but there's increasing evidence that that's not the case. Specifically, things like these alkylated pHs, which would be a pH with basically methyl groups or ethyl groups attached to it. There's evidence that they may actually be the drivers for toxicity, and yet no one's really sort of looking at them very closely. I shouldn't say no one, but they're not as well studied. Interestingly, there's also a lot of research out there that suggests that as the pHs start to photodegrade, they actually become more toxic. You're forming quinones and other oxygenated compounds that are actually more toxic than the pHs we started with. And there's also the idea that if you have increased concentrations of metals, they're actually synergistic with the pHs and can lead to sort of higher levels of toxicity than you'd otherwise expect. As I mentioned, we don't have pH data yet, but something that we want to keep in mind. So what's happening in the system? Well, as I mentioned, we're seeing these spikes in pHs when we have rain events, and we're seeing other things correspond to that as well. So here we're again seeing the precipitation in black, and the orange symbols are the suspended particulate matter concentrations during our sample events. And the trend is really, really similar to what we saw for the pHs. Really high concentrations. Again, we're on a log scale here of particulate matter in the water in our first rainy season, steadily declining into the dry season, and then spikes, but smaller than our first year and our second and third years. Still need to update with our latest samples. So why do we see these spikes? Well, first of all, rain events are when we are going to expect rain to erode in soil from the system. So we're going to have more sort of source material making its way in. We're also going to have higher discharge in the stream, which means we're going to resuspend more sediment. And in fact, we find a pretty good relationship between pH concentrations and the suspended particulate matter concentrations, especially during the first year, which is shown with the black plus symbols. We get a good power law fit for that year. When we go into the second and third seasons, we still see some trends, especially in 2019. It gets sort of more dispersed. We get more differences between sites and less good of a fit as we get into the second and third rainy season. We also know we do have a lower slope, which suggests that that's showing our lower soil pH concentrations. Essentially, we have less pHs per amount of sediment that's getting suspended. We do, and I'll come back to this as well, but we do also have evidence that we're seeing less erosion as well, which we'd sort of expect as we move away from the fire and the system, the watershed starts to recover. We did notice another change in the hydrology of the system. This is a little bit qualitative here, but I've plotted the stream flow in red over top of the precipitation data. And we noticed something sort of interesting in this first rainy season. We have really high stream flows, and that's even comparing similar size rain events between years. You can see that for about a 6.5 centimeter rainfall event, we're in the range of 35 to 40 cubic meters per second stream flow. Whereas in our second year, we have similar and even larger rainfall events that are much, much lower, half that, and even less than that, a quarter of the stream flow. Again, this is really a superficial analysis at this point, but it does seem like something's happening, and this does make some sense in terms of recovery of the watershed. Vegetation's coming back, so more water is being drawn out, less sort of direct flow into the stream system as well. And as I mentioned, we do have at least some evidence that we're getting less sediment as well, and that's a partial driver for the lower pH concentrations in later years. This plot is showing the amount of SPM essentially per unit of precipitation. It's not a real clear trend, but we can definitely see that our highest values are soon after the fire. As we move forward, we do have a generally decreasing trend in the amount of suspended particulate matter we're getting per sort of amount of rainfall. There's one other aspect of this that we've spent a lot of effort looking at. I mentioned that pHs come from a variety of sources. They can be from fires, they can be from petroleum combustion, so diesel exhaust especially, and they're naturally found in petroleum. So researchers for decades now have looked at various ways of sort of sorting out what the source of a mixture of pHs is. There's a number of different diagnostic ratios, looking at ratios of different pH compounds. I'm just going to look at one here, and this is a simple and probably the oldest one of these, where we're looking at the ratio of anthracene to anthracene plus phenanthrene versus fluoranthene plus pyrene. So just looking at concentration ratios of these compounds. And researchers have worked out where a pH mixture is likely from based on the ratios of these different concentrations. So we can see on the left and lower part of the graph, if it plots in here, we expect it to probably be petroleum based. This little wedge in the middle, petroleum combustion, and then the far right is the wood coal combustion. So if we start to look at some of our data, this is a little bit of a busy plot, but we first plotted the soil samples, and they didn't neatly fit within the biomass combustion zone, but they're close, and they were fairly well clustered down in this black oval at the bottom. And when we get to our water samples, our first rainy season events plotted very, very close to this. So we're getting really similar signature, and those are the dark blue dots here. Really similar signature in our water sample as what we see in the soil, which really suggests the pHs we're seeing are definitely coming from soil from the burned area that's getting mobilized into the watershed. As we moved into sort of later first year rainy season events, we start to see a shift in these sort of blue dots, lighter blue dots out to the left and upward, suggesting more of a petroleum source or a petroleum combustion source. And then when we get into the dry season, we do see lots of scatter. So these are the green empty circles, but definitely a trend towards shifting into that petroleum region. When we return to the next rainy season, shown by the red X's, November 27th, 2019, many of our sites returned right back to that same sort of burned soil signature. So you can see we have about 5 or 6 of our samples there, whereas several did not. We had several samples that sort of did not return to that signature. Going forward to 2020, we see this difference between different sites sort of extend. So we see now this sort of one group that is continuing to show up into 2020 in that same burned soil region, and then a whole nother group of samples that are way out in the petroleum region. In the dry season with the green triangles, we continue to see more of that petroleum signal. And then into 2021, we've at this point pretty much lost that soil signal. We have, even during our major rain events, we have maybe 1 or 2 samples that are down in that range. Most of our sites are outside of that range, where we're really not seeing that sign that we're really mobilizing burn soil into the system. Again, our dry season in green squares is much more in that petroleum region, as we've seen in the past. I did want to point out, sort of interestingly, we had also collected some samples of road runoff, so just water running along the gutter within this region. These were actually collected, I think, almost 3 years apart at similar locations. We got really, really similar results. And it's sort of plotting where we're seeing many of these dry season petroleum-like signals that we see in the green. So how do we explain what's happening here? Well, as I mentioned, in that first rainy season, we really expect that we're getting lots of erosion. We're mobilizing lots of this soil into the watershed. And it seems like that is our primary source of pHs in the water. As we move into the later rainy season, we're seeing a little bit less erosion. We've probably also mobilized a not insignificant amount of that easily mobilizable soil. So what's sort of left is going to tend to stay there. And so what we're seeing in that shift up and to the left is more of a mixed signal. So we're getting maybe a little bit of the burn soil signal combined with some petroleum, and it's going to fall somewhere along most likely one of these lines. These lines represent different mixing models depending on what we chose as an end member. And notably, they're not linear. So even though it's a 2 end member mixing model, because the concentrations of the 4 compounds can independently vary, we get sort of these non-linear trends. And I'm only showing sort of one of the years of data here, but they seem to match reasonably well with what we're seeing. We're seeing the same pattern of movement, which would represent mixing of some remaining soil plus some petroleum impacts, likely from road runoff, combining to give us the signal. During the dry season, what we're thinking is that we're seeing this more petroleum type of signal because any pHs that are making their way into the system, and concentrations are really low typically in the dry season, are likely coming from over irrigation, where we're having sprinklers spread on the road, mobilize some road runoff that gets flushed into the water system. And again, we're not seeing soil being mobilized in the summer because there's no rain to do that. I mentioned that.
Sorry
Yes.
to interrupt you. You have about 10 minutes left and
Okay.
5 minutes for Q&A.
Great, thank you.
Thank you.
I did want to point out that we did see some differences between sites, as I mentioned. So I wanted to just sort of quickly highlight 2 of these sites. So we're focusing on Site 3 and Site 5. Site 3 is located right here in Las Virgenes Creek. Site 5 is here on Medea Creek. And in our early rainy season, our first rainy season, our trends were really similar between the 2 sites. They very, very closely matched really through the whole first year in terms of pH concentrations. And that also holds for our sort of signal for the soil. So we really see a very similar wildfire signal for both sites early on. When we come to our second rainy season, though, we have one of our sites where we see these spikes in concentrations also continue to show that wildfire signal, whereas our other site where we don't see those same spikes now is showing up as more of an oil or petrogenic signal. So why do we have these differences between sites? Well, we've done some thinking about that. We don't have a clear answer. I suspect, though, that one of the reasons is if we look at the upstream section from these locations, Site 5, which is the red line here, has much less upstream area that has actually burned. So a relatively short area upstream of here that's burned versus Site 3, the whole extent of Las Virgenes Creek has burned. So sort of a much larger drainage area that's burned that will have soil that can be mobilized into the system. There's some other possibilities here. There are differences in bird intensity. There's differences in sort of the local landscape in some of these areas. So we haven't totally sorted that out, but in any case, there's clearly differences that we're seeing in different locations. So just some conclusions here. We are definitely seeing pHs generated by the fire, which is supported by both the soil and water analyses. Those do get transported into the water system, especially during rain events. We see, as I mentioned, rapid decreases in the soil pH concentrations. But as I mentioned, we're mostly losing compounds that we're less concerned about, and the more toxic and carcinogenic compounds are tending to stick around longer. They're still there at least the same concentrations 2 and 3 years after the fire. As far as the absolute concentrations we're seeing, we're not exceeding any water quality criteria, which is good news, but we do exceed some of these more ecologically focused water quality criteria that are more sensitive, more stringent. And we're continuing to exceed those 3 years after the fire. We think that we're seeing these decreases in concentrations in the water largely due to the degradation and loss from the soil. So we have less source material making its way in, less SPM, less sediment actually making its way and being eroded into the water system during those rain events, largely due to recovery of vegetation and things. And also seeing lower stream flows, which means not only less material making its way in, but also less sediment being suspended in the water column. We're really interested in these pH ratios because not only for use at this site, but we're thinking there may be additional uses. Can we use this for tracking wildfires? Can we use this for identifying if we have sediments in locations? Can we identify what's from fire systems versus what is non-fire years? So we're still looking into some of those issues. We are continuing to sample at least a little bit, at least for the rain events. We want to see what baseline is. As I mentioned, our December sample just from this past year was one of the highest concentrations we've seen. So we want to see if that is actually background, and those are coming from other sources. We're continuing to analyze for metals, mercury, and other things. And lastly, we're looking into sort of other source differentiation approaches. I showed a very simple one, but there's lots of them, and they get sort of more complicated. So we're applying some other diagnostic ratios, including looking at compound-specific isotope ratios and things like that. And we're also looking at applying this or similar methods to looking at sort of fire history. We've already analyzed some paleosols from Argentina and looked at pH ratios. We've actually been able to identify different biomes based on some of these pH biomarkers. We've looked for increases in fire regimes in different timeframes, and we're sort of continuing to advance that side of thing as well. So I will finish there. I want to again thank everybody who's worked on this, which is quite a few people, especially Priya and all the students. And I'll end there and leave it for questions. Okay, let's see if there's some in the Q&A. So will this impact vegetables, fruits, grapes for wine because it's in the soil? That's a really interesting question. There was actually a report that suggested that possibly is the answer. Definitely plants can uptake pHs. Most likely at the concentrations we're seeing, it's not something that's going to be a huge effect on, you're not going to have like toxic vegetables, and plants also have ways of sort of degrading pHs. So will it really affect them? Probably not in any real significant way, but definitely something that probably needs some more research. I have heard that the fires affects wine grapes because not so much the pHs, but other compounds, the sort of smoky smell compounds actually get taken up and end up in the wine. But I'm not an expert on that. Do pHs or pHs come from burning petroleum fuel as well? Is there a background level from auto and truck traffic that confounds the amount in some areas around highways? Yeah, and so that's something we're looking into, and part of the reason we collected those road runoff samples. They're definitely there. It's something we're continuing to sample. We're sort of collecting additional background samples and things to get an idea of what levels those are. And it's also part of the reason we're continuing to sample, now three years after the fire, to see if we can see what background in the watershed itself is. So yes, definitely true. That said, our big spikes that we're seeing are almost definitely from the fire. Some of the smaller spikes may have contribution from the from things like that, road runoff and exhaust from highways. All right, what are PHs? So PHs are the polycyclic aromatic hydrocarbons. So this class of compounds formed during primarily incomplete combustion. How long do the remains of the wildfire stay in the environment? That is what part of what we're trying to figure out. And at least as far as the pH side of things, it's looking like months to maybe a couple years is about how long they seem to be staying in the watershed. Other things we're still looking at, how long do things like metals stick around at higher higher concentrations, that we're still working on. Can any of the chemicals detected be contributed back to fire retardants used to fight the fires? That's actually an interesting question. So I'm not analyzing those, although back when I started the initial work with the soils, I was actually seeing some of the fire retardant, I think triphosphate style compounds at fairly high concentrations. I don't know a whole lot about them, but definitely are detectable for sure. And my understanding is those aren't, at least that realm is not particularly hazardous, that class of fire retardants. I have heard, the PFAS have also been detected in other places. What are quinones? So quinones are basically, if you took a PEH molecule and added on some oxygens as double bonded oxygens. And so they're basically generally formed from photooxidation of these compounds, and they're more water soluble and potentially more toxic. So that's sort of why we're concerned about them. And I think this is the last one. Are the petroleum pHs the ones that last longer over time? Good question. They most likely last the same amount of time. The reason we're continuing to see them sort of regularly is that they're constantly replenished in the system by all of the vehicles on the road leaking oil. The roadway surface itself has some pHs that would be petroleum based. So it's not that the individual compounds are sticking around longer, it's more that there's a continuous source for them, whereas wildfires are sort of a one-time source that's degrading over time. And I think I've answered everything.
Thank you so much. That was fascinating.
Thank you.
And it's, I'm feeling some Matador pride right now. So much hard work collecting all that data. All right. Great. So so keeping with this theme, we're gonna move on now to talk a little bit about impacts to coastal water quality. So we're going to be hearing from Marisol Cira about work that she's been collaborating with Heal the Bay on. Marisol is a PhD candidate in civil and environmental engineering at UCLA in the lab of Jennifer Jay, who's been doing water quality work locally for years. Marisol is also an intern at the NASA Jet Propulsion Laboratory, and her research interests are at the nexus of public and environmental health. At UCLA, her work addresses antibiotic resistance in the environment. So this is a side project that she's been working on. And at JPL, she uses satellites to detect water quality changes from wildfires. Marisol obtained her bachelor's in science and a master's in science in civil and environmental engineering. So welcome, Marisol.
Hello, share screen now then.
Sure.
Hello, everyone. As Katherine stated, I am Marisol Cira. I'm a PhD candidate in civil engineering at UCLA, and I'm also an intern at NASA Jet Propulsion Laboratory. So it is my pleasure to be presenting today turbidity and fecal indicator bacteria in recreational marine waters increase following the 2018 Woolsey fire. This was a collaborative effort between folks at UCLA, JPL, and Kiel Bay. I'll be giving some background on wildfire activity and wildfire impacts on water quality, and then I will introduce our study and walk through our methods, results, and conclusions. So for some background, wildfire activity is expected to surge in the second half of the 21st century for all projected climate scenarios, regardless of anthropogenic interference, which you can see here in this fire activity time series. More specifically, in the Western United States, wildfire activity will increase in frequency, duration, and season length. However, as wildfire activity increases, soil hydrology will increasingly become affected. Wildfire increases soil erosion during and immediately after fire and at the onset of rainfall, which in turn increases runoff and sediments that transport contaminants to downstream ecosystems, which you can see here on this diagram, where you see the sediments and the runoff downstream. Wildfires have been shown to alter the physical and chemical water quality of receiving streams. For example, Stein et al. Evaluated post-fire stormwater runoff from 5 wildfires in 2003 to 2009 and found greater concentrations of total suspended solids, total phosphorus, and total zinc, among other constituents in post-fire runoff. However, there remain several knowledge gaps. Wildfire impacts on microbial water quality remain elusive. To our knowledge, only one study has evaluated the microbial quality of surface water and subsurface soil after a wildfire. Belenka et al. Used wildfire residues to conduct batch reactor and column experiments. The receiving oceans have also been largely overlooked. Only Kramer et al. Has evaluated the phytoplankton community composition in the Santa Barbara Channel during the Thomas Fire, and Tang et al. Evaluated phytoplankton blooms in the Southern Ocean triggered by the 2019 to 2020 Australian wildfires. And studies have reported that sparse sampling has hindered broad spatial and temporal observations. Which brings me to our study. The Woolsey Fire burned from November 8th to November 21st of 2018. It burned nearly 100,000 acres and destroyed over 1,600 structures in the Ventura and Los Angeles counties. Following the Woolsey Fire, officials warned of debris flows washing into the ocean, and our partner at Hilda Bay also reported impacts to beach water quality, which caught the attention of the public. Therefore, the objectives of our study were to determine whether the Woolsey Fire impacted the coastal water quality, whether the impacts were short-term or long-term, whether the beaches draining the burn area were more impacted, and whether satellite remote sensing can be used to resolve gaps in spatial and temporal sampling. This is a map of our study area, where the burned area is shown with a red line, and the watersheds are shown in black lines, and streams are shown in blue lines. To answer the objectives, we divided our study area into 3 regions, where the inside region in red drained burned watersheds, the adjacent region in yellow drained unburned watersheds, but adjacent to burned watersheds, and the outside region in green drained unburned watersheds. To assess the physical water quality, we obtained Sentinel-2 satellite imagery from 2016 to 2020 from USGS We use Sentinel-2 because it utilizes 2 identical satellites to provide a high revisit time, and because Sentinel-2 does image coastal areas with a wide swath, high resolution multispectral imager. We derived the turbidity for each image using the Dogliati algorithm in Alkalite. Alkalite is an open source software that atmospherically corrects and processes Sentinel-2 imagery for aquatic applications. We applied a turbidity threshold of 4.6 FNU to each image, which was previously determined from plume and non-plume Gaussian distributions. This means that each pixel above 4.6 FNU was assigned a value of 1, otherwise a value of 0. We counted the number of pixels with a value of 1 and converted it to plume surface area, and we calculated plume surface area monthly means for each region. And to better understand the impacts of post-fire rainstorms, we also obtained precipitation data from 2008 to 2020 from NOAA. To assess the microbial water quality, we utilized fecal indicator bacteria from 2008 to 2020 from the State Water Resources Control Board. As you can see on the map here, for the study area, measurements were taken at 26 sites in the inside region, 10 sites in the adjacent region, and 8 sites in the outside region. We also utilized the precipitation data from NOAA to distinguish between all weather, dry weather, and wet weather data, and calculated FIB monthly means for each region. We used the FIB data because although FIB are not typically harmful themselves, FIB are used as pathogen indicators since fecal matter may contain a myriad of disease-causing organisms. In addition, studies have demonstrated that rainstorms increase FIB levels in seawater, and that seawater exposure after a rainstorm increases incidence rates of swimming-associated illnesses. Here you can see the 2018 to 2019 images of the study area pre-fire, during fire, and post-fire. Here is the image during the fire, and here are the 2 images post-fire rain events, which show increases in turbidity intensity and plume extent. And when we compared the 2 post-fire rain events to similar rain events from 2016 to 2017, we see that a rain event of 2.94 inches produced a smaller plume than a post-fire rain event of 1.49 inches. In addition, while images of previous rain events indicated that regions closest to urban areas were normally more impacted, as you can see in this region here, post-fire rain events indicated that the region below the Woolsey fire was more impacted, which you can see in this area here. Plume surface area monthly means from 2016 to 2020 revealed that in 2018 to 2019 fire year, the inside region was more impacted by the first post-fire rain event in November, and it was the only region impacted by the second post-fire rain event in January. They also revealed that the inside region's 2018 to 2019 plumes were up to 10 times and 9 times greater than the 2016 to 2017 and 2017 to 2018 plumes, respectively. Further, we performed linear regressions of 3-day precipitation totals and plume surface area by region and fire and non-fire years. Here, data for the inside region is indicated in red, and data for the fire year is indicated with the triangles or the solid line. Linear regressions then showed that the 3-day precipitation produced bigger plumes during the 2018 to 2019 fire year that were more substantial in the inside region, as you can see with this red solid line. FIB monthly means showed that the inside region experienced elevated total coliform levels from December to March. More specifically, the inside region's 2018 to 2019 total coliform levels were up to 9 times greater than the 2008 to 2018 levels. Similarly, the inside region experienced elevated enterococcus levels from December to May, and the inside region's 2018 to 2019 enterococcus levels were up to 53 times greater than the 2008 to 2018 levels. Increases in enterococcus, which were above the State Water Resources Control Board standards, are of particular concern here, given that the enterococcus is highly associated with gastrointestinal illnesses in marine waters. The dry weather 2018 to 2019 FIB monthly means were more aligned with the 2018 to 2019 all-weather FIB monthly means, which I previously showed. More importantly, the inside region's wet weather 2018 to 2019 total coliform and enterococcus monthly means were up to 14 and 54 times greater than the 2008 to 2018 monthly means. Further, Arnold et al. Reported wet weather ENT means of approximately up to 300 CFU per 100 milliliters in beaches receiving urban discharges. However, the current study here is showing wet weather enterococcus monthly means of up to 4,500 MPN over 100 milliliters in beaches receiving runoff from sediments discharges from burned areas. So to conclude, following the Woolsey fire, we observed short-term coastal water quality impacts at levels relevant to public and environmental health. Elevated turbidity levels persisted for 3 months, and elevated FIB levels above the State Water Resources Control Board standards persisted for 6 months. Impacts were most pronounced in the inside region, which drained the burn area, and satellite remote sensing can be used to help evaluate coastal conditions following wildfire events. Results from the study can inform future wildfire response. For example, results could guide monitoring and public health agencies in sampling and treatment efforts, as well as beach closures. That is all for me today. Thank you for your attention, and I'm happy to answer any questions.
Marisol, can you see the Q&A?
Yes.
Okay.
So the first question, did you take water samples by chance? We did not take water samples. The PICO indicator data was from the State Water Resources Control Board, and they did take water samples. However, we personally didn't take those samples. We didn't show this here, but we also obtained data from LA Sanitation to make sure that they were also seeing similar observations, which you can find more information about in our article if you're interested. Should I continue answering the questions, or do you want more information on that?
That's probably good.
Okay, I'll move on. What is the inside region? So that is just what we defined as a region that was draining runoff or sediments from the burned area. Does that answer the question?
I think so. Can I ask a question? I can't add to the chat or the Q&A. Maybe you covered this, but I was just, so what's the proposed mechanism for the amplification of those pathogens?
So we're thinking that the sediments protect the FIB from like UV radiation, and they may provide some nutrients for the FIB. So that's what we're proposing as maybe why we're seeing the greater abundances of the FIB. Also, in marine waters, Enterococcus has been shown to last longer given the salt water content. So that could be why the Enterococcus just lasts longer than the total coliform.
Interesting. And then what's creating those satellite images? Is it just suspended solids or?
So the satellite images collect data, and then the algorithm can extract like turbidity, harmful algal blooms, and other constituents. And so in this particular instance, we got the turbidity. Yeah, but there are also future ways to extend this research by also extracting the other constituents or using other satellite sensors like Landsat. Yeah.
Marisol, we have a question in the chat. What could be causing the high fecal count?
Yeah, I think that primarily the runoff and the sediments that are coming down from the burned area, although we didn't see here in this instance for Woolsey fire, but I did note that in other studies there are sometimes the sediments like constrict the transportation flow, and so they might move those sediments to beaches. And that might also cause a spike in the FIB in the coastal water quality. There might also be the wildfire disturbs for example, in the area of Malibu, they have septic tanks, and so wildfire may disrupt those systems and may be polluting the soils. Although from my understanding, this also did not happen for the Woolsey fire, but for other fires, there is a potential that wildfires can destroy wastewater treatment plants, which can also discharge these fecal indicator bacteria into the ocean.
Okay. If there's no further questions, thank you so much. That was interesting. Question?
No, there's one last question that came up, but it disappeared from the screen.
I think she kind of addressed it in her final comment.
Okay.
Did you see that, Marisol?
I don't think, other than why the FIB are.
I was asking about sewage infrastructure, and I think you were talking about that in the septic discussion.
Yeah.
Okay, great. So I think now we're going to take a break for lunch. We're going to reconvene at 1 o'clock. And we're looking forward to hearing our afternoon presenters. Ty, do you have anything you want to add?
No, I'm good for now. Thank you.
Okay, great. So we'll see everyone at 1 o'clock.
Is everybody back, I'm presuming? Robert Montgomery again. Just to clarify in terms of the continuing education for REHSs, everybody's attending the presentations, that's good. The form on the left will be sent out and needs to be completed. You can see where it has name, last name, first name, address, email, signature. That's pretty self-explanatory. The other item that needs to come in is the course evaluation, the symposium evaluation. And that needs to be done. It's a PDF form. Once we receive the continuing education documentation form, the evaluation form, then the certificate will be cut and sent out. Somebody had said CPS for the units. My email is info, info @montgomeryinvestigations.com if you want to contact me directly. But I think that should answer everybody's question. These are not my requirements. These are the Department of Public Health up in Sacramento that I have to have this documentation behind it. So again, we need full attendance, the continuing education documentation. Please put on that documentation the name, first name, last name that you want to appear on your certificate. Sign it, send it in, and then along with the evaluation form, and we should be good to go. I see a lot of REHS in that, so thank you for your time.
Thank you, Robert. And the course evaluation will be emailed out by Alumni Relations. So Katie, it's all yours.
Thanks, guys. All right. I'm going to present a student research project that I worked on in collaboration with the South Coast AQMD. And it was a couple of years ago, but it's relevant to our symposium. And I thought, because this is primarily an alumni event, it'd be nice for the alumni to see some of the student work. So this is a project that was developed as part of our research design and methodology course, which is a year-long course that master's students take in their second year. And I took over the course when I began with the department in 2018. Because I've been introducing all the speakers, I'll just let you know briefly. I've been in the department since 2018. I completed my PhD at UCLA in environmental health sciences. And before that, I worked in the private and public sectors as a consultant and in the health department in San Francisco. And did other things. So that's a little bit about my background, but I took over the research methods class, and I had an interest in doing applied research projects with community partners. And so this is an example of one of those projects. The idea was developed with Joe K. Gosh and with some input from Scott Epstein at the South Coast AQMD. And it was a group project. So the students' names are listed here: Derek Jaramillo, Kathleen Gonzalez, Jonathan Kubota, Neil Benetti, Mark Sutton, Raymond Chigani, and me as the advisor. Hang on, I got to get my controls. Okay. Again, the scope of the time frame for this project was academic year 2018-2019. And so this is a summary of some of the major wildfires for the previous 2 wildfire seasons. There's a list of the fires we were targeting in our research and their time frame. So there have been many severe fires since then, but this is what we were focusing on. So at the time, it was alarming to see the season extending into December, which is normally our wet season, and to see hundreds of thousands of acres burned. And this aerial photo is from November 2018, where you see smoke plumes from the Camp Fire and the Woolsey and Hill fires in Northern and Southern California. This is a table that the students put together looking at the severity of smoke exposures during this season. So what they did was they took burn maps and identified a monitoring station in proximity to these fires. And then they looked at the number of days that exceeded state and federal standards for PM 2.5 and PM 10. So the availability of the data kind of varied based on whether or not there were monitoring stations in proximity to these fires. But you can see how for various fires, there was a range of kind of severity of smoke, of the PM concentrations, and also in duration, where you see the car fire with 27 days in excess of the federal PM 2.5 standard. And I just want to acknowledge Scott Epstein was helpful in assisting the students with the acquisition of the monitoring data. And then one of the students actually demonstrated this to our exposure assessment class. So they kind of translated the learning on. So the idea for this project came from Jo K. Gosh, who was the health effects officer at the AQMD at the time. And she had this concern that they were making these shelter-in-place recommendations, but not really understanding whether or not that was practical for people. So in digging around, it was impossible to determine how prevalent residential air conditioning is or was. We looked at SoCal Edison and the State Energy Commission records to try to find a useful source for this kind of information, but it just doesn't really exist. And so without that, the shelter-in-place recommendations are problematic. So other questions Jo K had were what sources of health information the public utilized, and what kinds of protective measures people were taking in addition to the shelter-in-place recommendation. And so we developed these goals for the project to assess the prevalence of filtered and conditioned air in private residences, to identify sources of information for air quality and health advisories during the wildfire events, and then to investigate people's experiences in terms of health symptoms and exposure, and then also their use of protective measures. So this included shelter in place, but also things like portable HEPA units and respirators. And the students developed an online questionnaire. It had about 20 questions. Some had multiple parts. We reviewed it with Jo K. and Scott, and we pilot tested it with the students. The students had to take IRB training, and we used informed consent procedures. Respondents had to be 18 years old. And then they sent it out just through personal contacts. So this is called the snowball method of recruitment. So you send it to people you know and ask them to forward it on. And the survey was live for about a month in January 2019. So surprisingly, we got 200 responses. About 183 of those were completed surveys, which is substantial considering this was just done through word of mouth. So this is the demographic questions that we collected information on. As you can see, participants tended to be younger. That makes sense considering this word of mouth communication. We did have a extended tail into some elderly respondents. For the most part, people had some college education. Nearly half had their bachelor's degree. We didn't ask about grad school, which is unfortunate. And then as a proxy for income, we asked about the kind of dwelling. So single family home, apartment, condos, mobile home, and other. And the majority of people are living in single family homes. which was also a little surprising. Okay. So the question was, during periods of smoke impact, did you experience any of the following? This was a check all that apply. So you can see a high frequency of and severity, I would say, of smoke and smoke odors and even ash on outdoor surfaces. And then some of these other more severe conditions, the white bars here are people that didn't experience those at all. So these are kind of ordered along the axis here in sort of severity. But you can see the majority of the respondents experienced air quality impacts. And we asked how many days they were affected, and it ranged from 1 to 90. So an average of almost 13 days of this kind of air quality condition, with a substantial portion of people experiencing that for the entire duration. We asked about the frequency of health symptoms. Did you or anyone in your household experience any of the following symptoms? So you can see, again, the white bars are people that did not experience these. And these are also ordered sort of in order of severity. But in terms of what you might call these nuisance symptoms, but as we learned from Dr. Kleinman's talk this morning, that those could be problematic in terms of aggravating more serious health conditions, respiratory illness later. We had just widespread prevalence of some of these health symptoms. Eye irritation, nearly 80% experienced it at least some of the time. Cough and respiratory irritation 2/3 of the time, and headache more than half the time. So substantial discomfort and recognizable symptoms associated with smoke exposure. Shortness of breath and chest pain were the least frequently mentioned. We had a separate question asking if they had pre-existing conditions that were aggravated, they thought, by the smoke. And so 49 people indicated yes, and about half of those were aggravating existing asthma. We also saw allergies and migraine headaches, some sinus infections and tonsillitis. And then here we get down into more serious health conditions, heart conditions, autoimmune disorders, and mental health and COPD. Also, 10% of these sought medical care and 2% were hospitalized. Okay, so the vast majority of people had some unavoidable exposure to smoke. 83% spent some time outside during the smoke exposure periods, with an average hours a day of over 3 hours a day. So that surprised me. We asked about their level of activity during these time frames and characterized those as mild, moderate, or strenuous. So you can see that these are conceivably the people that are really trying to stay indoors and going outside incidentally, and then other people that are walking the dog or running errands or picking up their kids or whatever are averaging over 4 hours a day. Then it looks like the strenuous activity group is also because their hours of exposure, their exposure duration is approaching 8 hours a day. It's likely that they're working out of doors and doing physical work when they're out of doors, strenuous physical work. So that's an indication of a more vulnerable subpopulation among the respondents. And these groups were had statistically significant differences. Sorry. Okay, so the prevalence of air conditioning. So surprisingly, about 84% of the respondents had some type of air conditioning. So that bodes well for the shelter in place recommendation. Nearly 3/4 had central AC. And so those are more likely to have filters, and filters you can upgrade. About 20% had window units, and then 6% portables. So a small fraction had swamp coolers, which Nico mentioned as well as not being recommended for a shelter in place because there's no filtration mechanism. So other good news here, about half of the survey respondents, used their AC during periods that they were affected by smoke. And nearly half of them reported that they thought it was helpful, okay? And so we had a 5-point Likert scale with most of the positives here. About 40% weren't sure if it was helpful, but a majority positive feedback on that. And then surprisingly, 30% were proactive about changing their filter either before or during the smoke exposure period. And we did not find that the prevalence of central AC varied by housing type, which again was our proximity for our proxy for income. Okay. So less than 20% of the respondents had a portable HEPA filter, but there was rave reviews on the use of the HEPA filters to reduce smoke exposure and improve people's symptoms. So really good compliance with that, 93% using it, and more than 80% thinking that it helped them. Using possession of a portable HEPA unit also did not vary by housing type. Okay. And then the frequency of following the shelter in place recommendations. So 88% of the respondents sheltered in place for at least some of the time. And of those that did not, the majority reason for not doing it was they didn't even know what it meant. They didn't know where to get that kind of recommendation, or they didn't think it applied to them. So there was some confusion that was acknowledged among the negative responses. There was also a small group of people that didn't follow it because they didn't have air conditioning. So this was identified as a subgroup in the data set. The hard to ignore people specified in comments that they were working out of doors. Some of them were working on the fire response. And that's why you saw some people were spending well over 12 hours outdoors during the fire events because they were involved in response. One respondent was evacuating animals. But here you see pretty good compliance about half the time or most of the time and always. So about 55% are actually following the recommendations more often than not. Okay, respirator use. So about 1/3 of the respondents wore a respirator. The majority of those were disposables. So N95s were the most popular, followed by surgical masks and dust masks. And a small 8% used an actual half-face air purifying respirator with HEPA cartridges. But the majority didn't have any training on how to use a respirator. Now that we've lived through the pandemic, everybody's an expert on respirators and face coverings now. But, you know, we saw that, you know, every day, people using even disposable dust masks improperly during the pandemic. So I think there's an opportunity to improve people's understanding about how to get the best use out of their respirators. And the majority of people felt that the respirators helped improve their symptoms.
Katie, you have about 10 minutes left.
Okay, thanks. So we looked at what were some of the associations among respirator users. So as the severity of smoke conditions increased, respirator use increased, and that was for all of the smoke conditions. But only a handful of increasing severity of health symptoms were associated with respirator use, and those included cough, shortness of breath, and headache. Shelter-in-place advisories were associated with respirator use, and pre-existing medical conditions were associated with respirator use. And respirator users tended to be about 5 years older, and almost one Likert scale point more educated than non-respirator users. We didn't see any associations between the duration of exposure, seeking medical care, or using other controls or housing. And then this is where people got their information on air quality. This is grouped by our age bins. And you can see blue are the younger respondents. You can see that they are more likely to use, this is probably the smartphone apps, which I hope is getting the best quality AQI index. That was one of my questions for Nico, but hopefully the map AQI data is being communicated to the cell phone apps. But obviously social media trends younger, but a surprising number of young people using the Air District's websites, and then Air Now and Purple Air were a little less popular. So interestingly, this older group, 100% of their responses were in the I am not checking for air quality information. So I think that's an opportunity there as well, how to reach that vulnerable population. Okay, and then you can see this is just showing the results of some statistical differences. So Purple Air and Air Now tended to be older and more highly educated, and they were significantly different from social media, those using social media or not using anything. And also the group that wasn't seeking out information was the youngest and the least educated. Okay. This was also a check all that applies. So more than half of the study population was only making use of one source of information. And then 1/3 were using 2 sources, and about 10% were using 3. And similar trends with the health advisory information. So these are the sources we asked about for health advisories: the air alerts, the Air District websites, the AQI or the weather app, social media, and other. A lot of people filled in the blank there. They were looking at local news. But again, these are kind of ordered by age and education level. You see a lot of the same trends there. Older people are going for these more specific agency communications, and those people tended to have a higher level of education. Okay, so we asked about whether or not they experienced a disruption in their access to information. So, and that was true for about 18% of the respondents. They lost either power, or they had to evacuate, or they lost Wi-Fi or cell service. So the majority of these respondents had lost multiple modes of communication at one time. Okay, so just to summarize, we saw widespread exposures and reported health symptoms and some severe health complications for a smaller proportion, but still asthma was the leading condition there that was complicated by smoke exposure. We saw, it surprised me, the widespread prevalence of air conditioning. So I don't know if that is a bias in our sample or how representative that is. It did not seem to vary by our proxy for income. And AC seemed to be used about half the time, and people were changing their filters. And they were, good compliance with shelter in place was associated with air conditioning. HEPA filters seemed very effective, but they weren't in widespread use. Maybe there's an opportunity there to improve access to that somehow. It seemed like there was a subpopulation that had unavoidable smoke exposures, and they were doing the most physically demanding work outside for the longest periods of time. And then we had about less than a third of the people using respirators, but it was uncommon for them to have any training. And, you know, obviously the disposable dust masks and N95s were the most common. I would imagine we'd be seeing a lot more of that now post-COVID. We saw the trends in information sources by age and education, and that communication modes were vulnerable during these events. So I just want to acknowledge the hard work of the students. This is them presenting their poster at the C Symposium, a student research competition. And it was also, the students really benefited from the collaboration with the scientists at the AQMD. So learning outcomes from the project and the group in general were learning to do survey design and administration, learning the ethics of human test subject research, preparing and submitting a conference abstract, writing a data analysis plan, conducting the analysis, and managing the project for a year. So I think there were a lot of positives. We had 3 other projects that year doing GIS analysis on other air quality and environmental justice issues, doing field surveys and some environmental sampling. So this course is kind of a work in progress, but we're interested in collaborations with community partners. And so, you know, I'm happy to share this as an example of this applied research course. And I'll give you my contact info here if anyone is interested in scoping a project for next year or maybe the following year. We would appreciate hearing from you. So let's take a look at the, whoops.
Katie, you have a few questions in Q&A, but I don't know if you want to type the responses.
Okay. We're running into our next speaker. I'm going to go ahead and type responses to these. So I can do that as soon as I introduce our next speaker, because I'd like to try to keep on schedule if possible. Hi, Shelley.
Hi, good afternoon.
Okay, so thanks for your questions, everyone, and let me get back to you when I have a moment. Oh, Shelley. Okay. Switching gears. So Shelley DuTeaux is joining us. She's the Chief of Human Health Assessment Branch. She's actually in the California Department of Pesticide Regulation, but she played an instrumental role in this examination of community exposures during the campfire, which is what she's going to talk to us today about. So Dr. DuTeaux provides oversight and guidance on the evaluation of human health effects of pesticides and the scientific basis for their use, regulation, and mitigation. She supervises a staff of 35 scientists that do toxicity evaluation and risk assessment and exposure analysis. Prior to joining the Department of Pesticide Regulation, Dr. DuTeaux worked for 15 years in emergency preparedness and response in the State Health Department and the Air Resource Board and OEHA. So she's a subject matter expert on acute and high concentration exposures, toxic air releases, and public health impacts of wildfires, train derailments, industrial explosions, and fires. Sounds super interesting. So welcome, Dr. DuTeaux. Thank you for joining us.
You, Dr. McNamara. I'm going to go ahead and share my screen and get that all set up. Get all my windows configured so you guys can see everything. So let me start that and switch. Okay, I trust that you can see the presentation slides and not the notes, if that's true.
Correct.
Okay, awesome, thank you. Great, so I just, before I get started, I want to thank Dr. McNamara, Katie, for the invitation, which I got over 2.5 years ago. It was October 2019 when the invitation came in for a March 2020 symposium. So we've been all hanging in there, anxiously waiting for this to get off the ground, and I'm so excited to be here. Appreciate the opportunity to talk about California's efforts in debris removal following wildfires with urban interface. And 217 participants is amazing. You know, at first I thought it was going to be 100. So this is a great turnout. I'm so happy to be invited for this CSU Northridge alumni event. So I'll get on with my presentation. Just a quick disclaimer that the views expressed here are my own and do not necessarily represent those of the California Environmental Protection Agency or the state of California. And the title of my talk is Controlling Worker and Community Exposures During the Campfire Debris Removal. And as Katie mentioned, my day job is with the Department of Pesticide Regulation, where I'm the chief over human health assessment for the department. We are under the umbrella of the California Environmental Protection Agency. But during the campfire, just shortly after the campfire, the Secretary for the Environment at the time, Matt Rodriguez, asked everyone within the agency if they had a previous emergency response experience or not, to step up to the challenge of helping these communities recover. So I left my job for about a year and focused specifically on being the state air monitoring liaison during the removal operations, which is not unusual for me because I have done emergency response and preparedness under the Cal EPA umbrella for the previous 15 years. So jumping right into this, just taking us back to the start of the campfire that actually started the same day as the Woolsey fire, which Scott and Marisol were talking about this morning, but it started early in the morning of November 8th, 2018. As we know now, it's a downed power line. There was a wind event in the Sierra foothills and a PG&E power line went down and ignited a very, very dry forest, which led to the kind of scenes that we are so familiar with now in the Western United States. Just, you know, intense fires, crown fires, obliterating the entire wilderness. For those of you who don't know where Paradise is, it's directly east of Chico in the Sierra foothill, and it's about 130 miles due north or so of the state capital, Sacramento. So this was a picture that afternoon. And again, typical crown fire explosion where you just see nothing but smoke and fire. The evacuation stories, I know many of you remember hearing those, and it was just an absolutely horrific scene. I didn't get up there until a couple of weeks later, but I know many of you watched this on the news. When we have fires in communities that are built in forests or next to forests, this is what you see. This is nothing different than any of the fires that we saw, like on New Year's Eve, this past New Year's Eve in Boulder County, Colorado, or the city of Talent, Oregon. So you have beautiful landscape homes that are destroyed. It doesn't matter, you know, how rich the people were, how poor they were, if they lived in a mobile home park like this, or if they had just a trailer out in the forest, or if they were trying to sell their home prior to the fire. It just hit indiscriminately. Businesses, this is a business right in the middle of the town of Paradise. This was a school. This is just what you see. And this is what we saw throughout the town of Paradise, Magalia, and Concow. Here's a playground. And with all of this destruction, you think, okay, if this fire was hot enough to melt aluminum from a car and destroy entire blocks, what is in that ash? And if these workers, these are actually folks that are looking for human remains, if they're completely in PPE and community members aren't, what is the exposure? So what are we dealing with when we're looking at debris from wildfires with the urban interface? Well, basically, it's the remnants of everything from residential living, building materials, and of course, you look at the age of the housing stock, it could contain asbestos and lead if older, home and garden chemicals, appliances and electronics, furniture, insulation, vehicles, all sorts of propane and gas cylinders. So this is really, really typical for the fires we see in California. And what is in the ash? In conjunction with Cal Recycle, Cal EPA has tested ash in about 7 of the major wildfires that have happened over the last 15 years. And the contaminants are basically the same. It comes down to metals, asbestos, and sometimes unspent chemicals. And for the fires that we see in California, heavy metals are the largest contributor by mass after carbon, bar none. It's heavy metals in the ash. Asbestos, as I said before, varies if the fibers are still in the ash, depending on the age of the home, the materials, and really according to the temperature of the fire. And any chemicals in the ash are dependent on the type of property, what it was used for, and again, the temperature of the fire. Overall, all of the sampling leads us to 6 bad actors, which are the highest contaminants of concern, including arsenic, cadmium, copper, lead, nickel, and zinc. And then semi-volatiles, if they're maybe some VOCs or semi-volatiles, PVOCs, they're usually in the parts per trillion to very, very low parts per billion range, not really high in the ash. And then for the first time ever, we tested ash from the campfire for PBDs and PFAS, and those were below the limit of detection. But all of these you look at and you go, oh my gosh, the ash is hazardous. And actually, it can be classified as a California hazardous waste under California's own code of regulation. It doesn't rise to the level as we figure it as a RCRA hazardous waste, but we do treat it like it is something that we don't want people to get around. And so as it's removed from properties, it is wrapped twice and put in a land section of solid waste landfills so that there's definitely no intrusion to groundwater. And so that, this will never get back out into the environment again, just because of the stuff that we found in it. And so if you look at this burned footprint of a property, we don't want this stuff to get into the soil. We don't want it to migrate into the soil to groundwater or go to surface water, much like Scott and Marisol were talking about this morning. And my biggest concern was we don't want to get it into the air. So this is where the state of California is so different from the rest of the states in the country. You probably have heard about recovery from hurricanes and tornadoes, and you'll see crews going in and using bulldozers and moving down trees and things like that. But a fire is altogether different because the material that's there is now completely different than what it was when it was standing. And about 2007, when the Angora fire broke out in Lake Tahoe, all the agencies you see listed here got together to develop a comprehensive recovery strategy for wildfires, because we don't want that stuff to get into soil, into the air, or into water. And we've helped consult with other states about how to do it as well, but we think that we've developed the best practices on how to do it and how to do it safely. So for my purposes, when we're looking at that ash footprint and we're trying to move this stuff off and get it into a landfill, what we do to help reduce risks of inhalation exposures to both the workers on site and also any community members is we add water. Not enough water to make it run off anywhere, but enough to make it so that as a dust mitigation strategy to keep it down on the ground and not re-entrain any of the stuff that's on that property into the air. And that's how we prevent anything from getting up into the air. Well, how do we know if that's working? Well, we have a multi-level approach to air monitoring during debris removal, which includes personnel monitoring, perimeter monitoring, community-based monitoring and sampling. And for the campfire, we did something called fixed facility monitoring and sampling. Oh, and has someone measured urine for heavy metals in California for exposed and unexposed population? There is, under the California Biomonitoring Program, I think they've done some firefighter analyses. So firefighters been exposed. So you might check out the California Biomonitoring Program for that. So I'll talk about each one of these blocks in a little bit more detail. And first, talking about community air monitoring and sampling. And I say monitoring and sampling, and for those of you nerds out there, you'll know that I know that there's a difference of the two. But this is exactly why we do this. We have homeowners who might not have their property destroyed right next to a destroyed property. Again, fires come out and they might burn indiscriminately throughout a neighborhood, and there might be one standing home and then 6 destroyed homes. If a home is rehabitable, if someone could move back in and live there, we don't want them being exposed to anything in the air while this debris removal is happening. Plus, there might be people who still work in the community, even if they live, miles away, or if they have to be in a hotel room or whatever it is. So community air monitoring and sampling, what that does is it quantifies the control measures, dust mitigation control measures. And what we're monitoring and sampling for in the air mirrors exactly that in the ash, because that's what we're trying to make sure doesn't go up in the air. So it's metals, asbestos, and particulate matter. And the monitoring locations in the community are based on where the location of the current residents live, any community concerns, like if they have a daycare center that's still open, or a community clinic or a senior home, if they want to have monitors placed there, those are the places that we might want to consider putting air monitoring and sampling equipment. And then, of course, it also comes down to power. Is there land power? You remember these places have probably destroyed utility infrastructure, so getting power is sometimes an iffy situation. But also security. We don't want to have the equipment vandalized. And then there's best practices for placing these types of equipment, like making sure it's enough away from a building or under the footprint of a tree, so that the sample and quality of the data that we're collecting is the best we can. And all of this is memorialized in an incident-specific air monitoring and sampling plan. So back to Paradise. This red outline shows you in the Sierra foothills the fire footprint of the campfire. All of the yellow dots inside are where we placed community air monitoring and sampling equipment. The green dot notes where our meteorological data collection system was placed. So it kind of was in the center of where all the monitoring equipment was. And why these yellow dots are clustered in the center is because that's where the population center is. And we want to make sure that we're capturing data that reflects kind of what people are being exposed to on a regular basis. So this is just a sample of some of the places where we put up equipment. So you'll see in the center at Paradise Adventist Academy, there's only one piece of equipment. This is a particulate monitor on a tripod. It has both PM 2.5 and PM 10 abilities, but it's run on a battery. So crews could go out once a day, change the battery, do a QA/QC check, make sure there weren't any bugs stuck in it, and close it up and set it to run again. Sometimes you can get solar panels to help with power source. And then the two on the other side at the Paradise Alliance Church and Feather River Adventist Hospital, there's a trifecta of machines there. The center tripod, which collects the particulate matter. And then you'll see one that's kind of a box with a long pole. That's the asbestos sampler. It has one of the cartridges, an asbestos cartridge at the end of that tube. And then the thing that looks like a tall, skinny birdhouse, that's the metal impact sampler. And those were placed in almost all locations we could do unless they had power, because those two samplers, sampling equipment, had to have line power. They could not run on batteries. So we set up throughout the community at the park, the town hall, the Unified School District offices, fire station number 35, another school, and an assisted living facility. What were we doing in the community? What were we looking for? Well, we were monitoring and sampling for 24 hours a day, 7 days a week, except for holidays. So full on sampling. We were looking at PM 2.5, which was monitored in real time with telemetry, and then asbestos and metals. And those were 24-hour samples that were collected daily. The metals came on a filter that was then sent off to an analytical laboratory once a day. And then the asbestos was, again, those common cartridges that we know about. And that was also sent off to an analytical lab for processing once a day. This is the chart of the community's public health screening levels that I put in place for the campfire recovery. These are all based on public health levels, things like the OEHA acute RELs or ATSDR MRLs. And where there was not a public health level, then I used a NIOSH REL, and I added either a and they had a dedicated web page that was for the campfire, and they had reports that I would post up there once a month or more often that had consolidated or summary data, but they also had a link to a page that we set up, which is a GIS map. And each one of the blue dots on here represents those air monitors. They're blue because they were offline at the time I took the screenshot. And you could actually zero in, hover over the dot, and get the real-time PM 2.5 level for that particular location. Plus, it listed the latest analytics for either the asbestos or the highest 6 metals. So this was a way that the Air District and recovery ops kept the community informed with what was happening on a real-time basis. You might see the triangles that are kind of off to the south and west and due south. Those are fixed facilities where we also had monitors. And again, people could zero in, hover over those triangles, and get the latest information of the immediate air quality for PM. So air monitoring and sampling at fixed facilities. Now, you might say, well, what the heck is a fixed facility? We hadn't done this before in wildfire recovery in California history, but this was a really important thing we were asked to do, because the campfire was up in Paradise, Magalia, Concow. But where the stuff was being hauled off was in other communities. And some of these communities, including Orland and Oroville, are EJ communities, which are used to having heavy industry, lots of gravel crushing operations, bunch of interstates or highways going through, lots of truck traffic. And some even had a solid waste facility where stuff was being hauled to. So we were really sensitive to the fact that these people around these areas where this stuff was happening might also want to know, not just in the immediate fire footprint, but the communities that were surrounding the area. And the fixed facilities were places where all of the metal that was being taken out of the ash piles and concrete, where this was taken so it could be eventually recycled and reused and kept out of the landfill. And that's one of the goals, of course, of both Cal Recycle and Cal EPA, is to reduce the impact to solid waste landfills. So a ton of metal was being recycled, and a ton of concrete, and all of this stuff was being processed in these facilities. So we monitored them during operational hours for PM10 and metals and asbestos. So again, just a really important cog in the piece, in the whole machine of public health and safety. So what about occupational safety? The interesting thing about all of these debris removal operations is that it's a complete mix of employees. There's state employees like myself, there's consultants, and there's contractors, and sometimes a lot of subcontractors. So there's a range of people that have a range of bosses and a range of employers. But we have to make sure that there are certain best management practices for occupational health and safety throughout the debris removal. So some of those things include a site-specific health and safety plan, daily safety briefings, required training like HAZWOPER, a respiratory protection program, including the physicals that were done on site before people did their fit testing. Other required PPE, whether it was level D or level C or above. And of course, shared stop work criteria, like if there was an accident, high wind or storms, and how the information about a stop work would travel from one location through the other locations that were being worked on at the same time. One of the pictures I showed, there were several people taking samples. What kind of PPE were they wearing? Probably just level D. If it was working on one of our air monitors, there was no air monitor needed, or sorry, any PPE needed. But there's probably some other pictures coming up that you might see the differences in what people were wearing. So this is a safety briefing, and people just have their Visi vests. So this is level D, safety toe, Visi vests. And then regardless of the employee type, we wanted to make sure that best management practices were throughout, whether you're a contractor, consultant, or state employee. And the safety briefings in the morning got so big, we actually had to move from an outside location with a bullhorn to inside Paradise Alliance Church, whose auditorium fits 2,000 people. So that's how many people were getting these daily safety briefings at 6 o'clock in the morning, 6 days a week. So just reminding you what kind of environment we're working in. This is at a school. This is an asbestos abatement prior to the rest of the debris removal happening at one of the elementary schools in Paradise. You can see the hot zone is clearly delineated back behind there's the decontamination tent and then the bin. And then these workers are outside in the warm zone. And we don't expect any asbestos to come beyond the level where the stanchions are marked back here behind the truck. And here's some asbestos workers. So they're wearing a full Tyvek hard hat. They have a long sleeve shirt and pants underneath, safety toed boots, gloves with duct tape around sleeves. They're doing double bagging of asbestos containing material that's been identified by a certified asbestos contractor. Fire ash able to incorporate concrete like fly ash. No, I don't think that would be a good idea to recycle fire ash, just because the inhalation exposures. So, and again, here's a person she's in level C. And she's watering down a pile before the dozer picks up some more another scoop, making sure it's properly wetted so that there's no reentrainment of any of these particles getting into the air. And you can see standing buildings next to this perimeter. So again, this is a destroyed property right next to a standing property. Here's what I'm talking about, the burrito, we call it burrito wrapping of the fire waste. So inside of this a 10-ton or 15-ton truck, there's a plastic impermeable barrier. Then the front end loader or the dozer takes the scoops full of stuff after it's wetted, dumps it into there, and after they have a certain amount, they put 2 layers of plastic over it. And so it becomes basically a burrito. And then there's a cover that goes over the top of that, along with a mesh barrier, so that before the truck can hit the highway, it is completely wrapped inside and covered. And so that there's no dust. You're not going to see these trucks drive down the highway with any dust coming off the back. That was incredibly important because we don't want anything leaving the sites, whether it's on highway, off-site migration of any kind. So what do we do with the ashes? Those burrito wraps of ash and debris, where the metal and the concrete has all been taken out, they go to a lined pit in a certified solid waste landfill, which is designated and certified for accepting that kind of waste. So it doesn't have to go to a RCRA level 1 landfill, hazardous waste landfill. It can go to a solid waste landfill, so long as the part that it's going to is lined, and so long as the waste itself is burrito wrapped. So you'll see these end dumps, and you'll see them tip up. And when they tip up, this like burrito of waste just goes out and goes right into the cell, the lined cell. So nothing gets airborne at all. It's a really fantastic system. And you can see the person who is pulling the plastic TIF tarp over the truck is wearing his personal protective equipment, including respirator. So how do we make sure that the workers are not exposed? Because I mentioned that there are people who work for different companies and the state, we don't necessarily require everyone to have personal monitoring, but we put it in the contracts that they are required to monitor a certain amount of their employees on any given day. So this is not a picture from the campfire. I give credit to the person who I ripped this picture off, but it's pretty typical. You see the dust monitor pump hanging on the belt. You have the tube in the breathing zone. And then if asbestos was being sampled as well, you'd see the asbestos cartridge on another tube. So this is pretty typical about how you monitor someone during their 8-hour, 12-hour day. Sometimes people who are doing the debris removal were operating up to 14 hours a day. So it's pretty typical. And a cyclone pump is a type of pump which actually makes the dust particles, the metal particles come out of the air and land on the filter. So it has to do with fluid dynamics of the air. When the air is captured, it actually makes a cyclone, and it makes it easier to impregnate the filter paper with the metal particles so you can count them easily. So personnel monitoring is one of the things that is required, but only of a sample of people. But the most important thing we do is something called perimeter air monitoring and sampling. So as a property is being cleaned up, there is, of course, a fence and a perimeter set up around that property. And then we set up triplicate sets of samplers over in 3 different places at 20 to 25% of the property is being cleared on any given day. And that triplicate set of monitors has the PM, the asbestos, and the metals. And one is set up, you get the MET data, meteorological data. One is set up upwind and 2 are set up downwind. But anytime during the day, the conditions might change, but you have a good sense of having kind of a clean set of samples and maybe a quote unquote dirty set of samples. But again, there should be nothing except for maybe a little bit of dust if they're not keeping the roads watered and street sweepers going and the ash itself watered. But again, it's PM10 because this is more occupational monitoring in real time. And then metals and asbestos samples that are taken and sent off to the lab for analysis. And the PM monitors are set in alarm mode. And we set them at 25 micrograms per meter cubed, which is half of the occupational screening level. And if there was an alarm, we could do a stop work and go and investigate where that dust came from. It might have been someone drove by on a dusty road that needed a little bit more water, or maybe there was a slash pile that was burning nearby and the particulate monitor picked up that. And whatever it was, it would be remediated before the work would start again. And just like the community samples, the contaminants of concern reflect what's in the ash. So asbestos, heavy metals, these are Title 22 metals from California Code of Regulations. But instead of being public health goals, we set these at the perimeter to be occupational levels. So you'll see a bunch of Cal-OSHA PELs, NIOSH RELs, ACGIH TLVs, etc. So these numbers are usually 1 to 2 orders of magnitude higher than the community-based samples. So the community-based sample is definitely more conservative. So what about some results? What's the life of a lined pit? Well, that is a question for Calorie Cycle. I do not know that question, but you can certainly reach out to Calorie Cycle and ask them. They have a really great website on fire debris. So just quickly do some, can I do a quick time check either with Katie or is it Jenny?
You have about a little less than 20 minutes for your conclusion and questions.
Okay, good, thanks. So on to some results. So for particulate matter, which, you know, that's the toughest thing because it's a reflection of how well your dust mitigation control is working, but it's also a reflection of daily life, like people driving, maybe if someone is smoking next to a monitor and you didn't want them to smoke. We had a funny incident where at the fire station number 35, they decided to have a barbecue and it was right next to our particulate monitor. And so they're really, really concerned about metals and asbestos, but firefighters at that fire station number 35 under CAL FIRE, they thought that barbecuing was okay, but it spiked our numbers. Funny things like that happen. But just to let you guys know that the community did not experience any detections of debris removal associated particulate matter throughout the Paradise area from March to December 2019, which was the height of the debris removal. Remember, we had to clean up over 19,000 structures, and it was a 10-month process. There was a handful of properties that were left over that the county had to go in and do basically kind of an eminent domain to get it cleaned up. And those happened from January through March of 2020, right before the pandemic hit. But I thought that this was a win. We did have a few particulate matter exceedances in the community, just a handful, but it was because of either equipment failure or smoke from other wildfires or slash burning. And in this picture underneath the solar array, you can see kind of a gray haziness out in those trees. That's a smoke from the Walker fire, which happened in September of 2019 nearby Paradise. And of course, just that smell of wildfire smoke got the community really concerned, and it did impact our monitors in the community, but it had nothing to do with the ash that was being removed from the burned buildings. And then at some of the perimeters and fixed facilities, again, we had limited PM exceedances that had to do with equipment failure. We had one monitor that actually fell over and landed in the dirt, or if there was improper dust control, as you can see in this picture, then work was stopped, everything was properly rewatered before work could resume. What about heavy metals in the air? Well, in the community, we had no exceedances above the screening levels, which again, were very conservative. The exception was barium. Barium's not even on my list of the top 6 bad actors in wildfire ash. You know, it's not, you know, zinc or copper or lead. but we did have a slight elevation. And the only thing we could think of was it might have been naturally occurring in the soil that was being scraped, or there was a nearby property undergoing debris removal. But other than that, it was just a one-time hit and it went away immediately after that. So it was kind of unusual. Might have also been laboratory error. But other than that, we didn't have any exceedances of heavy metals in air in the community during the entire cleanup phase. At the perimeter locations, there were some metals with detections, including antimony, arsenic, nickel, selenium, silver, and thallium. But they were all detected at levels well below the occupational health limits. And I'll stop and make a note here that our laboratory techniques have gotten so good that the limit of quantitation and limit of detection were in low parts per billion, parts per trillion range. So while we can detect it on a sample, it doesn't mean that there's actually a health risk. So I think it's important to keep that in mind, that we're looking at levels, again, that were well below either occupational or public health standards or advisory levels. At the recycling and sorting facilities, remember, these are places that are actually shredding tanks like propane tanks, water heater tanks, car frames, bicycles, getting it ready to be reused as metal and being hauled off to smelter facilities, et cetera. So we did see some total chrome, some copper, lead, and zinc. But again, these values are so low, 0.00048 milligrams per cubic meter of air versus 0.5 for the occupational level. So again, while we can see it, we can detect it, it doesn't mean that it was an issue. So again, I think a real win on the heavy metals. What about asbestos? So asbestos is a funny thing for any of you who might have opened or anyone who has worked with asbestos issues. The definition in federal law is very specific, that it's a particular fiber that has to be greater than 5 microns in length, and there's a certain aerodynamic diameter to it. So while we didn't see any asbestos fibers in the community at any of the screening locations, we did detect fibers, although not only was the fiber looked at under phase contrast microscopy, but then it went on for electron microscopy to be able to identify what that fiber was. And although 4 fibers were detected at 4 locations, none of them rose to the federal definition of asbestos. And they ranged from very, very low levels, but nothing at the screening level that we were looking at for the public. And the highest level we saw was at a transportation corridor where Skyway, which is the main road in and out of Paradise, met Highway 99. So it might not have even been related to fire debris. It might have been having to do with brake pads on a passing vehicle. So again, this was good news all around on the asbestos. How many fires do we collect all of this asbestos ash? At every fire that Cal Recycle and Cal EPA does the removal activities, the perimeter monitoring occurs. Community monitoring happens at all of those fires as well, but usually that's just PM. So this extra layer of asbestos and metal sampling in the community was extra because of the Camp Fire being the largest and most destructive wildfire in California history. But every fire that's cleaned up under the California State Consolidated Debris Removal Program has all of the sampling happening at perimeter of cleaned up properties, and then particulate monitoring at a minimum in the community. And then we did have some asbestos, not asbestos fibers, but fibers detected around the perimeter of the cleaned up properties. Again, nothing was detected as an asbestos fiber, but fibers were detected at a few properties. I will note that there were 2 Class 1 regulated asbestos containing material abatements that happened at Paradise, where the entire property had to be enclosed in plastic and put under negative pressure. Samples were taken there before and after the HEPA filters, where the air supply and air outlets were happening within the plastic tent. That's where we collected the fibers. It wasn't on the perimeter samples around the property. So, I mean, if you really want to find out if there's asbestos, you want to sample inside where the asbestos is being shoveled and put into bags. And we even had very few detection of asbestos fibers there. So that was good news. The depth of the soil removed, the first scrape, we call it the first scrape, is 6 inches. And then the soil is sampled in a random statistical pattern and tested for the Title 22 metals under the California Code of Regulations. If there's a hot spot detected above the limits in soil, then another 6 inches is taken off of that. The soil is resampled, and then it usually passes after that. So that's how much soil is generally removed.
You have about 10 minutes, Shelley.
Okay. So actually, that was this is my last couple of slides, and then I'm happy to answer some questions. So as I just mentioned, the Camp Fire remains the largest wildfire and wildfire recovery project in California history to date, with the number of structures and the properties destroyed. Our success was that we had the absence of air quality impacts to community, to the surrounding areas, and even to the workers on site. And we think it's a model of best management practices that we share with other states. But I will say that as much data that I crunched and as many samplers as I worked on for a year of my life, the fact remains that people's lives are affected. And I've been in enough of these situations, and probably you have too, to know that data is not going to help this couple feel better about losing everything that they owned. What the community needed was a sense of calm and reassurance to let them know that they didn't need to worry about one more thing. So as much data as we generated, volumes and volumes of sampling equipment gone through, and the number of extension cords that I had to haul around all the time, what it did is it gave this community and other communities a sense that we got this, we got their back, and we're going to get this stuff off of the ground so it doesn't go into the air, it doesn't go into the water any more than it already has. And it's not going to go into the soil, and we're going to make it so that they can come back and have a clean place to rebuild if that's what they want to do. And really, that's the essence of public health in this particular instance. It's really keeping in mind the public part and as much as the health part. So I want to acknowledge that I had a huge amount of help with my partners from the Butte County Air Quality Management District, Jim, Jason, David, and Steve. Also my partners at Tetra Tech, Dominic, Lauren, Chris, and Randy. And a huge thank you to all the many private businesses, churches, and homeowners that let us trample in their backyards, go through their gates, give treats to their dogs, set up equipment, move equipment, get on their roofs, set up more equipment. Through the whole process, and we couldn't have done it without that. And I will conclude there, and happy to answer questions. So what about from vehicle fires, say from Caltrain? Maybe Alicia could, I'm not sure if I understand Alicia's question. Something about vehicle fires. I'll move on to the next question, and then we could come back to that. Naturally occurring asbestos is found on the coast. Yeah, it's found everywhere. Where we were working, they actually had a dam cut into serpentine rock. So there's naturally occurring asbestos. How do you differentiate it? You actually you actually don't. That's the problem. So Oroville Dam had a massive spillway emergency just prior to this fire. And the Butte County Air Quality Management District set up a bunch of asbestos monitors because they were monitoring the naturally occurring asbestos. So you really can't tell the difference. And so that's problematic. And it comes down to messaging with the public about whether it's from serpentine or whether it's asbestos from building materials. But that's where your certified asbestos contractor comes in to help identify the asbestos containing materials and make sure that those are at least taken away and put into a hazardous waste landfill before the removal of the rest of the debris occurs. How many locations have soil been removed? Is that all business, all neighborhoods and business? Okay, so if it's a under the California program, every property that's burned has to be remediated. It's either remediated with the state or the county will do an eminent domain and go in and clean it. The private property owners typically agree, if they have a little part in their homeowner's insurance that goes to debris removal, they will forfeit that money for the state to come in and clean up their property for free. However, if there's no homeowner insurance, the state will do it for free regardless. If there are people who are holding out and will not clean it up or want to do a private contractor, they still have to meet the same soil cleanliness requirements of the state that the state requires. So if you do a private contractor, if you want to go in and shovel this stuff yourself, you are still subject to the same clearance levels. So it's probably best to have a professional do it. But in California, all these fires are required to be cleaned up. If there's a fire in the forest, that's a totally different situation. That's usually managed by a different kind of set of rules. And the businesses, so yeah, if it's a business, it's a gas station, a McDonald's. The Starbucks did not burn, but the McDonald's did. Starbucks came back online pretty quickly after they got a tank of clean water to run their operations. But all of those have to be cleaned, except that the clearance levels for the soil for businesses are different than residential neighborhoods and schools. So in the California Code of Regulations, there's a different level of screening that industrial areas have to meet, especially if it was previously used as an industrial facility, like a car repair place. Yes, there was similar activities conducted for the Woolsey and Hill fire. Absolutely. The main contractor was Arcadis. I had friends who worked down there at the same time that I was up on the Camp Fire. Exact same thing happened down there. Yeah, except that they only had 3,000 properties. How do you collect ashes, asbestos, or particulates from vehicle fires that happen up? That I don't know. That is so anything that happens on highway is the jurisdiction of Caltrans. So I don't know how they clean that up. I have absolutely no idea. But I imagine that anytime you have a car fire, it's a pretty nasty mix of stuff. But that probably is covered by Caltrans and then your private insurance company. So, oh, thanks, Professor Kleinman. Appreciate the kudos. Yeah, we need to get some publications out on this. Just when you're so busy cleaning up after wildfires, you don't have a lot of time to stop and publish work. So having a presentation like this really helps get the word out about the kind of model that we've developed in the state of California and how really protecting public health and the environment is priority number one when we go in and clean up after wildfires. How is the ash gathered? So you wet it and you go in with these big dozers, front end loaders, big equipment, and they scoop it up and then they put it in the trucks that's wrapped, the extra double wrapped with the plastic, and then it's hauled off site. That's how it's done. It's a grueling work. Sometimes you have to use hand shovels. It's just it's really hard work. And kudos to all the contractors throughout the state of California who help and are certified to be able to do this kind of work. If your property did not burn, are you required to? No, and you're not required to test your soil. if your property did not burn. But
Yeah.
you know, you might have ash or something come on your property and you might want to clean that up. There, a DTSC, Department of Toxic Substances Control, if you go on their website, has a great one-page flyer on how to clean up fire ash. So even if you don't have a burned property, if ash fell or blew onto your property and you want to know how to safely get rid of it, Department of Toxic Substances Control has a great one-page flyer for that. Any radiation from natural, no, we don't detect radiation during the debris removal cleanup phase. However, two things happen before this massive cleanup project happens. One is DTSC and US EPA, or one or the other, goes in and removes the visible household hazardous waste. Propane tanks and cylinders, they will note asbestos containing material with a big bright fuchsia pink X. And they'll also remove anything that might be like ammunition, firearms, gun safes. They'll look for things like grenades. People have things like that left over from their grandma who served in World War II. So all that stuff is removed by a hazardous waste contractor overseen by either DTSC or US EPA. Then an asbestos material, a certified asbestos contractor will come in and re-identify or do a better job of identifying asbestos containing material, which has to be removed before any of the rest of the fire debris is removed. Then cars are removed, and then prior to any of this other large bulk being removed, they will go in with radiation detectors and make sure that there isn't anything on site. We have a list of properties that have licensed radiation materials, whether it could have been maybe a clinic or a hospital or someone who has a meter, like if they're doing well depth meters. There's a list of those with the Department of Public Health. And we reached out to each one of those property owners to ask if they had their radiation containing device or if their property was destroyed. But
Shelley, we're going to have to
wrap it up. Okay, so
yeah,
they still go in and they will look at the ash footprint for radiation before having it cleaned up. So, wow, this was great comments. I'll try to answer some more, but thanks everybody. There's my contact information if you need to reach out. And again, I thank you for the opportunity.
Thank you so much. A lot of interest in your topic, so that was great. And thank you for your diligence in maintaining those community health standards and worker health standards. So, all right, so we're going to hear a little bit more about occupational health now. We're going to hear from Derek Urwin with the LA County Fire Department. He did his doctoral research work on the firefighter cancer cohort. Let me just tell you a little bit about Derek. I have your outdated bio here, Derek. So he has filed his dissertation in December, right? In the Department of Chemistry at UCLA. He's also a firefighter. He's been with LA County Fire for 15 years. And he'll be discussing a collaboration with the University of Arizona, the University of Miami, and NIOSH on the firefighter cancer cohort study, looking at the wildland-urban interface expansion. So Derek is also a member of the California State Fire Training's Behavioral Health and Cancer Awareness Curriculum Development Cadre. Sounds like important work. And his doctoral research is in the area of applied math and physical chemistry with a focus on developing computational models to examine structural and thermodynamic features of PAH DNA adducts, those combustion markers of combustion byproduct exposure.
All right. Thank you, Dr. McNamara. Just a quick audio check. Make sure you can hear me okay.
We can barely hear you.
Let's see. Is that any better?
That is a tiny bit better. Can you speak any louder?
Yeah, let me just turn up the gain on my microphone here. How's that?
That is much better. Thank you.
Okay, apologize for the technical difficulties there. And just as a clarification, I finished my thesis defense in December, but I'm still in the process of making sure all the margins in my thesis are 1 inch. So I won't have my degree conferred until June. But thank you for the introduction, Dr. McNamara. So what I'll be talking to you about today is the firefighter cancer cohort study. And just before we get into that, just to give you some objectives for the presentation today, I'll start off by summarizing the background science behind cancer in the fire service, and then we'll move on to explaining how wildland urban interface, or WUI fires, how research is conducted in partnership with fire departments. And then we'll work towards understanding the implementation of research-based policy changes in the fire service, which is kind of the entire point of us in the fire service working collaboratively with academic researchers. So when it comes to cancer in the fire service, I remember when I first started off as a firefighter about 15 years ago, we were keenly aware of cardiovascular health and the need, to maintain heart health because of the physical demands of our line of work. But we weren't very aware of the incidence of cancer in the fire service. And it was only recently that, based off of data collected by the International Association of Firefighters and also a lot of good epidemiological research, that we came to be aware that a lot of the deaths of firefighters who are actively serving are actually caused by cancer. So many of you out there may or may not be familiar with some of the epidemiological work that's been done when it comes to cancer in the fire service. But long story short, firefighters have an elevated incidence of cancer and also cancer mortality as compared to the general public. So as a firefighter, I'm often asked by my colleagues, well, why is that? Why do we have this elevated incidence of cancer as compared to the general public? So I usually start out by just explaining to them that IARC, the International Agency for Research on Cancer, actually classifies firefighting as Group 2B, possibly carcinogenic occupation. And then you can kind of delve a little more into that, right? In the fire service, we are constantly working 24-hour shifts, always responding to emergencies whenever they arise. And as a result, we experience a lot of shift work with circadian sleep disruption, which is a group 2A probable human carcinogen. And while I put this picture up there just kind of as an entertaining bit, I would just make the point that when we're on duty, we respond to an emergency no matter how we're feeling, no matter how tired we are. And our line of work can be absolutely exhausting, but we always put our duty first, no matter how tired we are, to respond to emergencies. And then if you get further into it, we get into these details of firefighters being regularly exposed to chemical carcinogens in our line of work. And there's a number of sources of those chemical carcinogen exposures, that being on the fire ground or in diesel exhaust from the apparatus that we rely on to respond to emergencies. And then also just carcinogens in our environment, right? We bring a lot of these contaminants back to the firehouse despite our best efforts to do exposure and contamination reduction in the field. So when you put all these things together, that's likely what results in our elevated incidence of cancer in the fire service. And just to reemphasize the point, we as firefighters perform our duty without a moment's hesitation. We'll always put the public's well-being ahead of our own. And as a result, many of our exposures to carcinogenic agents are unavoidable. So for us in the fire service, again, we'll always perform our duty, but we do want to make it to retirement. We do want to get to spend time with our families and see our children grow up. And so we really have to make every effort as firefighters to understand and minimize the exposures that we suffer in the line of duty. And this is where research projects like the Firefighter Cancer Cohort Study come into play. So if you're not familiar, the Firefighter Cancer Cohort Study is a really great collaboration between fire service partners and academic research partners at the University of Arizona, University of Miami, and NIOSH. And you see here just a few of the fire department logos for departments involved. Tucson, my own department, the LA County Fire Department, Orange County Fire Authority, but there's a few dozen others throughout the United States. So a little bit of background, the Firefighter Cancer Cohort Study is currently the only multi-center fire service cancer study where, again, it's a project done in partnership with a number of fire departments throughout the country with the overall goal of studying 10,000 firefighters over 30 years in order to identify the mechanisms that cause firefighter cancer. It's a pretty unique study insofar as firefighters steering research directions. There's an oversight and planning board that's composed of a few dozen firefighters from around the country that bring forth ideas and input on research directions. And this is something that we in the fire service are very grateful for, having the opportunity to engage with academic research partners so that we can get the questions that we're most concerned about answered by experts like everybody out there listening right now. One of the other unique features about the FFCCS is there's actually the opportunity for firefighters to engage in research activities. This is really community engaged research, or fire service community engaged research, I should say, where a number of us in the fire service have completed the necessary IRB training to work as, quote unquote, firefighter research assistants on the firefighter cancer cohort study. And then the ultimate goal, based off of the research work that we do, is to develop preventative interventions for firefighter health and safety. Excuse me. So outcomes of the firefighter cancer cohort study are evaluating biomarkers of both exposure and cancer risks, with the long-term goal of identifying cancers early and hopefully improving treatment outcomes. So one of the most important aspects of firefighter cancer research is studying biomarkers. You're all well aware that the fire ground is full of a number of chemical carcinogens from everything you've been hearing about today, and that these compounds cause cancer-promoting genetic and epigenetic changes such as DNA mutations and changes in gene expression that contribute to our elevated incidence of cancer in the fire service. And in order to gather information about those cancer-promoting genetic and epigenetic changes, we need to collect and analyze biological samples from firefighters. So to quantify what a firefighter's been exposed to after a fire, we measure biomarkers of exposure such as hydroxylated pHs in urine. This quantifies some of the chemicals that have gotten into our body, but it's only a part of the picture, as we typically quantify lower molecular weight pHs in urine, while many of the higher molecular weight pHs that are highly genotoxic are actually preferentially eliminated in feces and thus not quantified. And what you're seeing here, I'll just pause for a moment to explain, is some work done previously out of the University of Arizona in collaboration with the Tucson Fire Department, where they collected urine samples at baseline at the time of enrollment from a number of firefighters, which you see in blue, and then subsequently collected urine samples after structure fire responses, which you see in red in the absence of any post-fire interventions. And then go a little bit further down the line, and urine samples were then collected after implementing contamination reduction measures or other interventions, such as a post-incident washdown, shower within the hour, which you see in yellow. And the takeaway from this is that, excuse me, measures like post-fire decontamination actually can reduce exposures post-fire. But also the takeaway is we never get back to baseline as firefighters, right? So this is important information for us insofar as understanding that we're never necessarily going to be able to eliminate our exposure to chemical carcinogens on the fire ground. And as a result, we have to take whatever measures we can in order to minimize those exposures over the duration of our careers. So one of the most important things when it comes to determining our cancer risk in the fire service is measuring what the chemicals we're exposed to are actually doing to our bodies by measuring biomarkers of effect. So to do this, we have to draw biological samples from firefighters and look for things like DNA mutagenesis or changes in microRNA expression or DNA methylation. And these are cancer-promoting cellular changes that can be measured. And the hope is in the long term that we can use these to develop cancer risk factor assessments for firefighters, which we don't currently have. And this is an area of focus for the firefighter cancer cohort study, and a big reason why we have a lot of enthusiastic participation from departments around the country. And again, what you're looking at here is data from publications out of the University of Arizona in collaboration with the Tucson Fire Department, where they looked at changes in microRNA expression on the left in veteran firefighters versus new recruits, where you see that oncogenes are overexpressed and tumor suppressors are underexpressed. And on the right, you're actually seeing changes in firefighter microRNA expression over 2 years, where those new recruits were compared to themselves as 2 years later. And again, you're seeing oncogenes overexpressed and tumor suppressors underexpressed when it comes to changes in microRNA expression. So one of the ways we're able to effectively conduct this type of research, again, is with the fire service community engaged research approach, where we make use of firefighter field researchers who've completed the necessary IRB training to be able to consent firefighters into the firefighter cancer cohort study, and also collect biological samples. Phlebotomy is within the paramedic scope of practice in the state of California. And as a result, with the blessing of a department's medical director, firefighters are actually able to do the phlebotomy that's needed in order to conduct this type of research. And this was something that was actually really important during the pandemic, because at the very beginning, we had a number of time-sensitive follow-ups that were coming up. Unfortunately, our research partners from around the country weren't able to travel. So in partnership with Captain Jamie Gabriel from the LA County Fire Department, who's also joining us here on Zoom today, we were able to go to our medical director, go to our command staff, and with their full support, implement a program to be able to do this biological sample collection at the beginning of the pandemic, again, because our academic research partners weren't able to travel. So because we had this community engaged research, we were able to keep things going and not let the clock expire, so to speak. So one of the other things we do is we pre-equip our apparatus and training facilities with the equipment that's necessary in order to collect biological samples, whether those be urine samples or blood samples, again, so that we in the fire service are able to facilitate this research and then ship samples off to our research partners. So a number of us work in this collaborative approach with working groups at different fire departments, where firefighters, again, work in this badge to badge model to facilitate firefighter cancer research. So if any of you out there are firefighters, or if you're familiar with the fire service, you know never to show up at an incident without equipment in hand and ready to work. So that's me on the left there carrying a hose pack, meeting up with another firefighter research assistant in order to facilitate some of our research activities, but I wouldn't dare show up without a bit of equipment. And again, what's going on here is facilitating post-exposure biological sample collection in the field because of the challenges that we face on these large wildfires. So the ultimate outcome is selection, again, of biological samples by those firefighter research assistants, which are ultimately shipped back to our academic research partners for subsequent analysis. And then the goal is to develop interventions and policy changes based off of the data derived from that research. And this is where, for example, the importance of showering within an hour after a fire exposure comes into play, right? We can actually quantify this to firefighters to explain, hey, if you take the time to get that shower in, do that post-incident decontamination, you're actually going to be taking steps to reduce the likelihood of a future cancer diagnosis. And that's the overriding goal of the firefighter cancer cohort study. So we'll move on now specifically to talk about wildland-urban interface fires, which, when it comes to exposure science, pose a number of unique challenges as compared to structure fires, let's say. So if you're to ask the question, what makes a WUI fire unique from an exposure science point of view, we would start off with the diversity of fuels. So the simplest way to put it is everything's burning on these large scale incidents that we're seeing more and more frequently here in the Western United States and around the world, where there's vegetation. And because of development into the wildland-urban interface, there are structures that are burning, there are vehicles burning. And then in the bottom right corner here, I just put other with question mark, because anything that anybody has stored in a shed or their home is likely to be burning once these communities are impacted. The resulting products of combustion pose a unique challenge as well. And if you'll bear with me for a second, rather than trying to play these videos here, I'll play them through here. So what you're seeing here is what's called a pump and roll operation, where firefighters are putting out hot spots where there's vegetation burning along the side of the road. This is a lot of, just smoldering fire after the head of the fire has burned through this area. Now that's in contrast to what you might see if we're on structure protection. Now I say this anecdotally, but as a firefighter who's worked in both of these types of job assignments, the exposures look different, they feel different. And that's kind of the goal here of studying this, is to quantify what the differences are in these types of exposures, because what we do is collect a urine sample after a crew has been, say, assigned to structure protection, as opposed to a crew who's been assigned to conducting a progressive hose lay where they're primarily working in vegetation. PPE is another big difference. So in structural firefighting, we wear a pretty robust set of PPE as compared to when we're working in the brush or in the wildland urban interface. It's very different, as you can see on the right. So to quantify this, in structural firefighting PPE, we're wearing a self-contained breathing apparatus and full turnout gear, which consists of an outer shell, moisture barrier, and thermal liner, in addition to gloves, boots, helmet, and a hood. That's in contrast to wildland urban interface firefighting or brush firefighting in general, where we're not utilizing respiratory protection. We're using very often a single layer of personal protective clothing, which results in us being highly susceptible to exposures via inhalation and absorption. And I'll pause here for a second, because I know a number of you out there are probably wondering, well, why do we not use respiratory protection in brush fires and on wildland urban interface fires? I'll tell you that it's not because we don't want to. It's a matter of, again, our job and our duty coming first. So for example, we can't make use of a self-contained breathing apparatus out in the brush on a wildfire where we're assigned for multiple days, because we don't necessarily have the capacity to refill our bottles, which, under heavy cardiovascular strain are not likely to last us much more than the 20 to 30 minute range. When you're working on a hillside, obviously you can't wear a self-contained breathing apparatus and perform your job from the cardiovascular strain point of view. And then we're often asked about PAPPers or also wearing a respirator of some sort. And again, with the right type of PPE that we could use, we certainly, I think, would make use of those. But when it comes down to it, I'll tell you a story from when I was a brand new firefighter doing overhaul and wearing an N95 mask. It got so badly clogged up with sweat after wearing it for some period of time, but I, kept it on because, I was told to wear it, and I, not shy to tell you, I ended up pretty much collapsing just because of the fact that I really couldn't breathe because of the cardiovascular strain. So when I say no respiratory protection, again, this isn't something that firefighters are resistant to. It's just we need the right type of equipment in order to be able to do that. And that's actually an area of research right now that we're all very interested in. So geography and job assignment, this is something that's a really important one to understand. So if you look on the left, when it comes to structure fires, you're really dealing with, you're really dealing with a localized event, right? Where you see the products of combustion, they're circled in white or gray. And then in the yellow circles, you'll see those firefighters all working around the same structure that's burning, largely exposed to the same plume of smoke. That's as compared to a massive wildland urban interface fire, where there's a number of different job assignments going on over a just massive area, where firefighters might be engaged in rescue operations, engaged in structure protection, mop up, or performing a progressive hose lay. And there's a whole plethora of additional job assignments that would likely be taking place, again, over this very massive area. So again, this poses challenges when it comes to quantifying exposures. Duration of exposure is something that's also very different. So when it comes to structure fires, we're typically there for minutes to hours when it comes to handling a structure fire, as opposed to these large wildland urban interface fires that we're fighting more and more frequently here in California, where we're out there working, on the order of days to weeks. And in some parts of the state, there's crews that are assigned for months on end, continuously being exposed, continuously doing their job. And then the resulting exposures. So when it comes to structure fires, right, the fuels are quantifiable. Again, because we know what structure was burning, we can go take a look inside. We might not be able to get all the details, but we can get an idea of, say it was a one-room fire, what the contents were. For example, if it was a living room versus a kitchen versus a bedroom versus a garage. It's more straightforward to measure products of combustion. And again, we know that firefighters are utilizing robust PPE with respiratory protection, and those exposures are much shorter. With these wildland urban interface fires, it's difficult to quantify the fuels. It's difficult to measure the products of combustion. And we're wearing light PPE without respiratory protection over long periods of time. So again, just for emphasis, when you talk about firefighter cancer research, it's important to recognize that there's a big difference between studying our exposures on structure fires versus studying our exposures on these large-scale wildland urban interface fires. So the key here, when it comes to the wildland urban interface expansion study for the firefighter cancer cohort study, is studying these wildland urban interface fires, because whereas some of this has been quantified in structure fires, it hasn't really been done yet for those of us in the municipal fire service that deploy to these large fires. So how do we go about studying firefighter WUI exposures? So step one is buy-in from firefighters. This was our first foray into firefighter cancer research when we got started here. And I was worried we were going to run into a great deal of resistance from the point of view of firefighters saying, hey, it's not going to happen to me, or I just have a job to do, or just, the point of view of I'm going to get cancer anyway, so let me just focus on doing my job. But we combat this with education and awareness, where we take the time to educate firefighters about toxicology, epidemiology, industrial hygiene, and medicine, so that they have awareness. Step two is study enrollment, obviously. So when we started off, our goal was to enroll approximately 150 firefighters into the WUI expansion study, and we're cautiously optimistic and hoping for maybe 75 to 100. But firefighters always, rise to a challenge, and in response to our education and awareness efforts that the department put forth, we're actually able to enroll over 200 firefighters in just 4 days. And since then, in the 2 years since then, we've actually enrolled many hundreds more firefighters into other sub-studies in the firefighter cancer cohort study. And again, I would emphasize that's in response to our department's education and awareness campaign, helping firefighters to understand the nature of our exposures and the impact of those exposures. Because again, we'll always put our duty first, but when it comes down to it, we do want to stay healthy as well. And then just study enrollment consists of consent process. Again, where firefighter research assistants have had their IRB training and can conduct this process, filling out a survey, taking cheek swabs, a baseline urine sample, and a baseline blood sample. And again, at this time of enrollment, we're drawing these biological samples to establish baseline insofar as biomarkers of exposure, so baseline urine sample, and also establish baseline insofar as biomarkers of effect, for example, looking at microRNA expression or DNA methylation. So the hard part is the field work, right, when it comes to actually trying to assess these exposures in the field. So the goal is to collect post-job assignment or post-exposure urine samples within 3 to 4 hours of the job assignment ending, and then subsequently process and freeze urine samples as soon as possible in order to analyze biomarkers of exposure. So our first foray, or first plan, I should say, was to have a team of research assistants carrying sampling kits that would rendezvous with study participants in the field and bring the equipment needed to do field sampling. But unfortunately, this plan didn't work out so great because a number of our research team assistants were deployed during the wildfire season to fight fires. And also there were the challenges of researchers, the academic researchers, not being able to enter the area of emergency operations. And this is where we ran into the challenges of geography and timing, where with all those research assistants being unavailable because they were fighting fire, my first foray here on the Saddle Ridge fire was kind of going out there trying to do this all myself, trying to catch up to strike teams of engines all around the perimeter of the fire or at base camp. And the outcome was a number of missed opportunities to collect samples. So again, this is where this research project kind of developed further into a community-based research project where, again, we recognize the best research assistants are the firefighters themselves because they want to see this type of research happen. They want to facilitate it because it's answering questions about their own health, things that are important to us and making it home to our families at the end of the day. So that's where we moved on to Plan B, which I mentioned to you a little bit earlier, where we built robust and portable sampling kits where we basically packaged up everything we would need for field collection of urine samples into kits that could be used to keep these samples on ice, and then place the kits in the care of firefighters on their own apparatus with instructions on how to appropriately collect these biological samples so that we didn't miss the opportunity to collect those timely samples in that 3 to 4 hour post-exposure window. And the outcome of it was no matter what unit was deployed on a given fire, they were equipped for any incident at any time, as opposed to us research assistants trying to rendezvous with these apparatus in the field. So the outcome of sort of the community engaged research approach was pretty successful in the 2019 brush season. We were able to collect about 130 post-exposure samples, which again are then shipped off subsequently to our academic research partners for analysis. And then step 4, which is in progress, like so many of you have mentioned, we've been hampered a bit by the pandemic. But the goal ultimately will be to quantify post-incident biomarkers of exposure. And then what we did at roughly the 1 year mark after the 2019 brush season was collect follow-up blood samples in order to look for post-season biomarkers, changes in biomarkers of effect. And here's now step 5, which is really for us in the fire service, what's really one of the most important ones. So while again, keeping public safety is our highest priority, figure out how to implement research-based interventions and policy changes for firefighter health. So, there's a number of approaches here, and this is where I'll start to wind down the talk, where, we need to develop these interventions, whether that be the development of new PPE, new technologies to use in our PPE, such as usable respiratory protection, the use of skin wipes in the field. And then I always put here, anytime I talk to a group of researchers, what ideas do you have? Because we in the fire service, we do our best, but we're always grateful for any help that we can get from the academic research community when it comes to one, figuring out how to conduct this research because it's complicated, because it's work that needs to be done in an emergency environment. But then 2, what solutions are out there? And kind of the best way to come up with those solutions is to really put our heads together. So again, I'll just finish here just by highlighting the fact that, we in the fire service listen to you as academic researchers. When you're publishing those works insofar as exposure science, medicine, et cetera, we're paying attention. After those publications are out there, we do the reading, and then we do our best to implement, again, research-based interventions and policy changes in the hopes of keeping ourselves and our friends and colleagues healthy so that 1, we can perform our duty, and then 2, make it home to our families. And I'll wind it down there to see if anybody has any questions.
There are some questions for you in the Q&A.
Okay. see if I can bring that up here. And then also, I believe my colleague Captain Gabriel might be on here as well if she wants to chime in as I start taking a look at the Q&A here. Yeah, so the first question there's how often are firefighters tested for any kind of cancer after possible exposure to carcinogens, and about how many members of their how about any members of their household. So when it comes to cancer screenings, there's the NFPA standard for firefighter physicals, which largely follows the USPSTF cancer screening guidelines. So I would refer you to those with a few small modifications that are there. And then when it comes to members of the household, that's not something that's done currently. But again, awareness when it comes to cancer in the fire service has increased a great deal. And we're really trying to make whatever strides are necessary to keep both ourselves and our families healthy. Let's see, next question here. How did gender, age, ethnicity, etc. affect them after exposure to possible carcinogens? So yeah, I'd refer you to a number of those epidemiological studies that have been done that actually have shown differences in the incidence of cancers among different ethnic groups and different genders. But off the top of my head, I'm not able to answer those, or is not able to answer that question right off the top of my head. Let's see. When will we resume our research cohort? We're still currently enrolling firefighters into the cancer cohort study. We're up to a good, I think about 700 or so from the LA County Fire Department and several hundred from other firefighters, or excuse me, I think we're up to nearly 2,500 or 3,000 overall in the firefighter cancer cohort study around the country. And again, you know, that's from, you know, applying this badge to badge model where you know, firefighters are eager to look into these questions and answer them. As a question, are the cancer incidents among firefighters limited to lung cancer or other cancers as well? What percentage is attributed to different cancers? Yeah, so the elevated incidence of cancer is not just limited to lung cancer. There is an elevated incidence of lymphomas, prostate cancer, colon cancer, breast cancer, bladder cancer, testicular cancer. Really, the list goes on. It's really quite striking if you take the time to take a look at that. Let's see. Are the toxicological insults of firefighters greater than the general population near these wildfire areas? Yeah, so when it comes to the exposures that firefighters suffer as compared to the general population, so, you know, if an area has been evacuated and the firefighters are working in that area, I would certainly say their exposures are more severe than people, you know, outside the generally affected area. But I would point out that, you know, unfortunately, with how quickly a lot of these fires develop and move these days, we're encountering the general public suffering the same exposures as us in the fire service working in the area of operations. So there is likely to be some similarity there when, again, we have members of the public who have not evacuated ahead of our arrival. Scrolling down here. So we have plans to expand to other health outcomes like cardiovascular and CVA. Yeah, that's certainly something that has been proposed, not necessarily as part of the firefighter cancer cohort study, but I've certainly heard of other researchers proposing that, because there certainly are other health outcomes that would result from, you know, the slew of carcinogenic agents that we're exposed to, resulting in other adverse health outcomes. Are we only sampling firefighters fighting wildfires or also house commercial fires? Yeah, so we're also looking at exposures from a number of other subgroups in the firefighters. Again, the wildland-urban interface sub-study was our first subgroup. Since then, we've expanded to look at live fire training instructors, new recruits, women in the fire service, There's also work being done with fire investigators. And all along the way, there has also been work done that started in Tucson, looking at firefighters responding to your standard structure fires in your typical 24-hour municipal shift for a firefighter. Let's see here. Somebody's asking here, I want to make sure they heard this correctly. Did you mention disruption of circadian rhythm is considered a carcinogen among firefighters? Well, so to be clear, IARC considers shift work with circadian sleep disruption a probable human carcinogen. It's classified as a group 2A probable human carcinogen. But that's just shift work with circadian sleep disruption in general. Let's see, PFAS has been identified in the material composition of some PPE used by first responders. Do you have any comments on the risk of exposure to first responders to such compound and their chronic exposure and cancer? Yeah, so there's been a great deal of research done when it comes to PFAS exposure in general, in the general public. We know that there's associated health impacts, and just in general, the general public and the fire service, would like to avoid PFAS exposures wherever possible because of the adverse health outcomes, no matter what the source is. Do I think there should be a different set of PPE for firefighters who work in the WUI zone versus wildland firefighters in the brush? Yeah, so that's some interesting research work that's going on right now. So long story short, look forward to the outcome or the results of that research, but that's not research we're conducting ourselves. Where again, we are eager to make appropriate changes when supported by good research, good sets of data. Let's see here. And I think that about wraps it up for questions in the Q&A.
Thank you so much, Derek. And thank you for all this good and difficult work. Sounds like very challenging field sampling conditions. So can you tell me, is cancer already a presumption among firefighters?
California does have cancer presumptive laws. But throughout the rest of the country, it's actually something that's a bit of a challenge. And that's one of the goals of the firefighter cancer cohort study is to, provide the appropriate data that's necessary to support presumptive claims. Great.
Okay, well, this allows us to have another quick bathroom break before we reconvene at 10 after 3. I just want to thank Derek again. And we're going to be hearing more from NIOSH on the wildland firefighter exposures at 3:10. Okay. We're going to try to stay on schedule. So our next speaker is Dr. Kathleen Navarro. I just lost my notes. Here she is. She's a research industrial hygienist. I wanted to get her title right. At the National Institute for Occupational Safety and Health, NIOSH, in the Western States Division. Her research focuses on examining the wildland firefighter exposure to smoke and understanding acute health impacts and evaluating biomarkers of exposure and effect in the wildland-urban interface. Before joining NIOSH, she worked for the U.S. Forest Service conducting wildland firefighter health and smoke research, and spent the 2019 fire season as a crew member on a Type 1 interagency hotshot crew. walking the walk. This is an elite team of highly trained wildland firefighters. Her time as a researcher and wildland firefighter allowed her to obtain high quality personal and area exposure data and better understand risks in the complex firework environment. Dr. Navarro received her PhD in environmental health science from UC Berkeley. Welcome.
Thank you. Can you hear me?
Yes.
Can you also see my slides?
Yes.
Great. No, I'm happy to be here today and give people kind of an overview of wildland firefighting and then some preview of some of the work that we have going on at NIOSH. So I wanted to kind of give a overview of wildland firefighting itself. I think I kind of did the opposite of Derek. I was a researcher first and then became a firefighter. So kind of just want to get everyone into an introduction of wildland firefighting in that world, give an overview of past research work that has been conducted by the U.S. Forest Service, and then give a preview of what we have going on at NIOSH. So like many speakers have talked about today, wildfires can produce many different air contaminants. Those include volatile organic compounds, polycyclic aromatic hydrocarbons, nitric oxide, particulate matter. Mostly what we see from wildfires is particulate matter in that smaller size fraction, carbon monoxide and carbon dioxide. And this is emitted all throughout the different combustion phases on a wildfire. So when talking about wildland firefighters and exposure, they do perform work on two different types of fires. So wildfires, which are these unplanned events, either caused by lightning or human, but firefighters can be exposed to smoke while conducting controlled burns, so prescribed fires. These are intentionally set fires that are done under controlled conditions generally for resource benefit. So the photo here I took, it was in the San Joaquin Delta, and they were burning to get rid of cheatgrass, which is an invasive species, and really letting those native grasses come back. So for a firefighter, a typical day will generally start with a hike out to their work site, a hike on the line. This can either be, if you're really lucky, you get to park right next to it, or it can be sometimes up to 3 miles, and you're carrying everything you need for that day to be not only self-sufficient for you, but to be your entire crew to be self-sufficient. So that includes carrying possibly extra water. It includes carrying fuel for your chainsaws for the whole day. So you're carrying around 35 up to 55 pounds. And the next speaker will go into all of the physicality that it takes to being a firefighter. But really it's about being self-sufficient and being a good crew member so that you can support your crew throughout the day. So I think, when I first got into this, we see the news, we see airplanes dropping fire retardant, we see helicopters dropping water, but really what stops fire is a very simple thing, which is to remove the unburnable fuel between the fire and you. And this is done a lot by crews on the ground, starting with chainsaws coming in, removing any big brush, any flammable material, and then having folks with hand tools come in and digging down into that bare mineral soil. So just creating that fire break. And this is a video of a firing operation. So oftentimes we hear the term fighting fire with fire. So people who are acting as lighters have torches in their hands that have a mixture of diesel and gasoline, and they're going through in a very coordinated fashion under good, favorable conditions, putting fire on the ground to really remove that burnable material between the line that they've determined that they want to control at. In this video, it's a road that we were working off of, and you're bringing fire from that road out to that main fire. So you're taking away that burnable material. At the same time, there's firefighters walking up and down that line who are holding. So they're making sure that the fire doesn't cross that containment line. So no ash or any kind of embers move onto that other side and start burning. And then after the fire has come through, firefighters will engage in mop up. And so this is to put out any burning material, any smoldering material that's left over, anything that has that potential to reignite the fire, either on that side or on what's called your green side, so outside of your containment area. So this is done just by smothering the fire, either with dirt, with water, Afterwards, if you're really concerned about the conditions as well, firefighters will come in and cold trail, and that was really just putting your bare hands into the ash and feeling for any warm material that's left over, anything that has that potential to ignite. So the previous work that has been done with wildland firefighters, much of the exposures that have been measured are PM, either 2.5 or 4 micron size range, as well as carbon monoxide. The past health outcomes that we've seen have really looked at both exposure either during a shift and then looking at health outcomes across a single shift or across a single fire season. So across shifts, we've seen an increase in urinary mutagenicity, increases in oxidative stress, urinary PAH, so markers of exposure, increases in inflammatory markers, and then a decrease in lung function over the course of a work shift as well. And then the first study to really try to look at and understand what were long-term health impacts was the Simmons et al. Survey of wildland firefighters. So they had a little under 500 firefighters and looked at, this is all self-reported, so the years of wildland firefighting and then various health outcomes. So they found within that study that the years of wildland firefighting was associated with increase of high blood pressure, increase of heart arrhythmia, and increase of having knee surgery, which at first I thought was very odd, but then when you put on a 35-pound pack and hiked out a steep hill, it makes a lot of sense. And then looking again across an entire fire season, and these are single fire seasons, studies have found an increase in airway responsiveness, again, a decrease in lung function, increases in upper and lower respiratory symptom scores, and then again, an increase in inflammation as well. And then from the National Wildfire Coordinating Group, the last 10-year fatality report that came out, we found that heart attacks were the leading cause of death for wildland firefighters, as opposed to the previous 10 years where aircraft and vehicle accidents were the leading cause of death. So some of the work that I've done with Dr. Kleinman here today was really trying to get at estimating, putting a number to what is the lifetime risk of lung cancer and cardiovascular disease from exposure to PM from smoke. So to do this work, we utilized exposure response relationships from Arden Pope that aggregated cigarette smoke, PM exposure, as well as secondhand smoke and community exposure, and looked at relative risk of lung cancer and cardiovascular disease. So we paired that with the field measurements that Josel actually helped take as well with PM4, and then heart rate, which we use to estimate breathing rate. So by putting all of that together and assessing risk, and so what we did for this study, because we don't really have a good sense of how long firefighters stay in their career, how long they work, and how many even days per season they have. So we varied this across 2 different exposure scenarios, what I called a short season firefighter and a long season firefighter. And a short season firefighter equates to a 500-hour overtime season, and a long season firefighter equates to an 1,000-hour overtime fire season, which sounds like a lot of overtime, but when often we have a seasonal workforce and many people are using this as their sole income for a year, working 1,000 hours, is really going to get you through a winter. So when we go looking at the kind of the most conservative measure, which is the short season firefighter of a career duration of 5 years, we calculated an excess risk of lung cancer of 8% and an excess risk of cardiovascular disease of 16%. And then when we go all the way to the highest level, so that long season firefighter that has a 25-year career duration, which I really equate to, a captain or a hotshot superintendent, someone who's been in this for their entire adult career, we see an excess risk of lung cancer of 43% and an excess risk of cardiovascular disease by 30%. So building off of a little of that exposure work that I just talked about in the last risk assessment study, we went in between 2015 and 17 and did kind of a reevaluation of firefighter exposure to smoke to see after that original assessment that was done in 2009 to 12, if anything had changed after recommendations had been made. So for this work, much like Derek's work, actually, we have a team of mostly firefighters and kind of one technical person, myself, went out there and we did direct observations and measurements across we went to, I think, about 30 different wildfires, and we measured shift PM4 exposures across various crew types and with firefighters performing various job tasks. And then to see if we could, estimate other exposures, we paired our PM data with some emission ratios that were developed by the Western Wildfire Experiment for cloud chemistry, aerial absorption, and nitrogen. So they had real-time PM and measured VOCs. And for this study, we decided to focus on acrolein, benzene, and formaldehyde. And so we used their ratios, their PM1 ratio to VOCs with our PM4 concentrations. And the way that we were able to do this is under the assumption that most of the PM found in wildfire smoke is in that smaller size fraction, as has been measured by previous studies that allowed us to use this VOC to PM ratio to then estimate VOC exposure for the firefighters that participated in this exposure assessment. So when we compare the full shift occupational exposures to common occupational exposure limits, we found that none of the exposures exceeded the OSHA permissible exposure limit. We did compare these to a National Wildfire Coordinating Group recommendation of an exposure limit of 0.7 milligram per meter cubed. So during that first assessment in 2009 to 12, we see that 22% of the time it was this occupational exposure limit was exceeded. And then for our samples, we found that 19% exceeded this occupational exposure limit. And for the VOCs that we estimated, only formaldehyde exceeded the NIOSH REL of 16 ppm, and that was for 83% of all wildland firefighters measured. And then when comparing against the ACGIH TLV, we found that 6% of firefighters were above that occupational exposure limit. So when comparing kind of against the two exposure samples that we have, we do see that they're generally still the same. So leading us to believe that not much has changed from that first exposure assessment that was done in 2009 to 12. But when looking across crew types, we see that hand crews, they're generally suppressing fires by constructing fire line, which may lead them to be closer to the fire's edge, which could lead to that higher exposure, especially for type 1 crews. So those are going to be your hotshot crews. And often to be a type 1 hotshot crew, you have to have higher qualifications held by leadership positions. Most of your crew has to have at least 1 year of experience, which leads them to be assigned the more complex operations on a fire. And then looking across job tasks, we see that firefighters performing direct suppression as their main job task had the highest mean PM4 concentration. Again, and then for firing, we also see higher concentrations. But I should note that we only had 2 people who performed that throughout our entire study, but did find that they had some of the higher exposures. And then holding and mop up also had some higher ranges of exposure that we measured out there. And then one thing I'm actually very interested by this study is after every single day that we measured, we asked the firefighter to self-assess what they thought their smoke exposure was for that day. So none, very little, low, moderate, or high. And a lot of times this was asked and everyone joked, everyone laughed. But when we compare this to what their actual measured exposure were, we did find a statistically significant trend with that, which is really, I find kind of exciting to see that firefighters are a really great measure of their own exposure, and this type of work could be used to understand firefighter exposure at a greater level instead of actually going out and measuring, if we could use this as a more qualitative tool. So just some conclusions from this study. It got published last year. Our exposures were consistent with previous exposure studies. Firefighter assessment of smoke can be a useful tool We found higher exposures for those type 1 crews, as well as firefighters performing direct suppression, holding, and mop up. So initial recommendations that were made both from this study, but also from that 2009 to 12 study, is to minimize mop up. Off in previous operations, sometimes you'll have kind of just a general statement of you're going to mop up 300 feet from the fire line, but really trying to create a mop up specification for that day, for that fire, for the kind of weather conditions that you have going on, that is really going to put firefighters in a place where they're only mopping up to secure the line. Other recommendations include reducing exposure by limiting shift length and rotating crews in and out of areas of high smoke, improving overall health by developing a medical surveillance program, creating fire-specific occupational exposure limits, really trying to take into account the time difference. If you're working a 16-hour day, how does that compare to an 8-hour occupational exposure limit? Create training for firefighters on hazards of smoke, and then locating fire camps. So those incident command posts out of historically smoky areas. So oftentimes on fires, you have to organize a lot of people, and you have these fire camps that are logistical support areas. So you want them to be close to the fire, but they can be impacted by inversions that can set up overnight that can lead to exposure, not only on the line for firefighters, but you're also exposed off the line as well. So I just kind of want to give an overview of some of the work that we have going on at NIOSH. And one of the big studies that we have going on right now is the Wildland Firefighter Exposure and Health Effects Study. So this is in partnership with the U.S. Forest Service and Department of the Interior. It was started in 2017 by my predecessor, Corey Butler, and is really trying to get at what are firefighters exposed to and how is health affected, and how is health affected over multiple seasons. We have these studies that have looked at across shift exposures and health outcomes, and then across season, but what happens in the off season? Do firefighters recover? Is what we really want to know. So we planned for a 3-year study. We ended up with a 2 due to COVID. But the purpose of this is to assess changes in lung function, cardiovascular function, kidney function, noise-induced hearing loss. And so for this study, we interacted with fire crews and participants 2 to 3 times per year for 2 years. So the first year, we recruited folks, we did a pre-season study assessment, a post-fire season study assessment. So that pre-season is around April, May, the post-season is around September, October. And then in 2019, we did that again, as well as going out to a wildfire incident for 3 days and did pre and post shift measurements. So the study components that we collected, we had questionnaires that asked about risk factors, demographics, previous occupations, medical conditions. For cardiovascular function, we looked at blood biomarkers, so looking at cholesterol, looking at platelet function, looking at pulse wave velocity, so arterial stiffness. For kidney function, we're looking at markers within their urine and blood of kidney injury, as well as markers for rhabdomyolysis, and then looking at markers of dehydration. For our pulmonary function and inflammation, we collected spirometry, fractional exhaled nitric oxide, which is a measurement of acute inflammation, as well as inflammatory markers in their blood, and then have noise-induced hearing loss, looking at tempometry and pure tone audiometry. So we have a lot of data that we're currently working through. So we have at around, up to plus of 95 participants in each of our study intervals, and then participating in each of the study components as well. So we have a very robust set of data that the research team that I work with here at NIOSH is currently working through. We've published a manuscript on the methods of this, which is what I'm really presenting on today, and hope to be presenting and publishing on the rest of the health outcomes later on this year. So my focus on this project has really been the exposure study component. So we did personal air monitoring for BTEX, aldehydes, including formaldehyde, as well as carbon monoxide. And then we sampled the urine for PAH metabolites, as well as wood smoke metabolites. So looking at levoglucosan, and then looking at a job task assessment. So firefighters or the crews were asked to complete a daily diary over the course of both fire seasons, where they listed if they were working on a prescribed fire or wildfire and the types of job tasks that they performed each day and the hours per day that they performed. So hoping to use that to create a job exposure matrix and more kind of cumulative exposure metrics as well for the entire study. So as a preview of what we've measured so far per day, so we went out for our mid-season study interval for 3 days, and our crew did a variety of job tasks. So the first day, they were prepping indirect fire line, so fire line that was pretty far away from the direct main fire. Day 2, they actually did a firing operation from their area, and then day 3 mopped up that area. So as we kind of look at exposures over time, we see that formaldehyde peaked on that day that they did the burn operation, and then BTEX was kind of highest on day 1 and day 3. And day 1 and the morning of day 2, when they were doing this indirect line prep, they also had quite a bit of exposure to any off-gas emissions from all of the chainsaws that they were using as well. So with carbon monoxide, we see that increase in day 2. And then for levoglucosan, we see this increase on our post-shift exposures on day 3. So really trying to look at if it was just the mop up that they were doing, or if possibly there was any kind of cumulative way to look at that as well across all 3 days. So our study strengths and limitations, we have over 150 wildland firefighters who participated over 2 seasons. It was a comprehensive design to assess exposure and health outcomes. Unfortunately, due to the fact that we just went to crews that were already existing, we'd have no true baseline samples, so we weren't recruiting incumbents versus new firefighters. The timing of our post-season samples leads to a little bit of problematic interpretation, as some crews came straight off a fire to come to our postseason samples. Some crews had a few days off. And then the representativeness of the study sample, we did decide to focus on looking at type 1 or interagency hotshot crews for this study, mostly due to typical crew turnover. We wanted to limit that as much as possible. And anecdotally, we know that hotshot crews tend to stay together over the course of multiple seasons. So it will lead to some representativeness study limitations. But overall, we learned a lot. I think Derek kind of touched on all of this too, is, recruiting study participant and incident access can be really difficult. Doing research, doing complex real field research in these remote locations, many of the tools and equipment that we use were not designed to work in a tent like this. As well as doing it safely, not only for our participants, but keeping all of the researchers safe as well. And then we had our fortunate abrupt study end in 2020, so we weren't able to complete all 3 years of data collection. So overall, we'll be looking to assess health and exposures, hoping to increase the knowledge about firefighter health status and risk factors. And like Derek said with the FFCCS, is really to provide evidence-based recommendations to reduce exposure and protect health. And I kind of just wanted to leave everyone with my kind of thoughts on doing research within this population and the challenges that come with it. Like Derek talked about, it's this dynamic environment. And so how do you assess exposure when every single day is so different? Every minute almost is variable too. In the photo in the background here, it was clear skies until that wind shifted, and then you can't barely see your coworkers who are only 20 feet in front of you. Access to incidents and study subjects can be really difficult. For myself, I became qualified as a firefighter, and that really opened doors to be able to access participants and go out to fires to collect this data. And so, like I talked about before, really including better training for firefighters on the hazards of smoke. Right now, most firefighters don't learn that smoke is a hazard occupationally until they take a class called RX 410, which is smoke management, and that's not taken until you're becoming a prescribed fire burn boss. And that's not generally taken about 10 to 15 years into your career. So, and then Derek talked about as well, no approved respirator. And I really kind of think about, you know, within the hierarchy of controls, PPE is the last one, but above that is administrative controls and really changing how people work. Research gaps I see are dermal exposures for wildland firefighters. It is not uncommon to go 10, 14 days without showering. And so we don't really know, even within wildland firefighters, what that can do for internal exposures and exposures to things like PAHs. Creating an occupational exposure limit based on long-term risk, really trying to account for cumulative risk and exposures, as well as kind of the tempo of work and their shift durations. Thinking about mitigations and how they can change exposure levels as well. Of those that I talked about, you know, we didn't see a big difference between 2009 to 2015, and really trying to look at, as we move forward, are these recommendations being implemented and how do they affect exposure levels, hopefully decreasing. And then for me, thinking about firefighter versus public exposure. And, you know, when as a firefighter, you hear, you know, you need to mop up 100%, you need to put out all that smoke because the community doesn't want to see that. But for me, it's trying to think about, well, what is that risk transfer? What are those exposure differences? So with that, I would like to thank all of the participating firefighters and all of the studies that I've worked on and acknowledge our research partners at DOI, Forest Service, Skidmore College, the over 50 researchers across 5 divisions here at NIOSH, and then NIOSH for funding the study, as well as NWCG. So with that, I'm happy to take any questions.
Thank you. Okay, so there's a Q&A bubble next to the chat bubble.
So the first question, are ultrafine particles taken into account when conducting wildland exposure assessment? For the assessments that I've done as part of my work for the U.S. Forest Service, we focused on looking at PM4, since that's what the occupational standard is set for. But there have been a few studies that have looked at the size distribution of wildfire smoke. And so we do know that they do exist in that ultrafine particle phase. The study about how fires affect firefighters or the effects of fires on firefighters. I'm not sure I completely understand that question. But this study is to look at kind of the occupational hazards within the fire environment and how that can affect health for wildland firefighters. And then the last question, I didn't see respiratory protection listed as a recommendation. Is it worn for some tasks and not others? Are the health effects different from those who diligently wear respiratory protection as required, or those don't and are different from those who perform certain tasks and others? So one thing about respiratory protection in the wildfire environment, the National Wildfire Coordinating Group they kind of set the standards for wildland fire, and within their standards, they say that you are not allowed to use any respirator that is not NIOSH approved, as well as meets the NFPA 1984 standard. And within the 1984 standard for respiratory protection for wildland fire, no respirator has been made that meets the requirement of that. But I do know that recently that standard was updated to really create a tiered system of exposures. And so we'll see if that creates any new products on the market for respiratory protection for wildland firefighters. Is it difficult to bring showering units in the camps? I don't think there are showering units in the camps, but as someone who has worked 16 hours a day and you get 8 hours a day to yourself, I chose to sleep instead of shower. That kind of decontamination process is not built into a wildland firefighter's day currently.
Okay. Could I ask a follow-up question about respirators? So is it possible, like during mop-up, could an air purifying respirator be a benefit? And is there an avenue for that?
I think it would be better in a situation like that, but it's still I have found to be an arduous task. When you're moving heavy logs, when you're digging, you're still at an increased respiratory rate. So I think it would still be difficult to do. I also, in my experiences as well, I talked to so many firefighters who, especially in the wildland space, don't see smoke as a hazard. And so I think a lot of it is around training about smoke as a hazard, so that when there is respiratory protection that could possibly be recommended, there's more compliance with it too.
Do you ever see like disposable N95s or dust masks in the field, or is that not the culture?
That's definitely not the culture. And it also doesn't protect against carbon monoxide.
Right.
So a worry is that it would lead to kind of an overconfidence to be in areas where they shouldn't stay.
Okay. Thank you. All right. And thank you for all your good work on this issue. We're a tiny bit ahead of schedule. Would people like to keep going? And we can finish up the day. Joe, are you there?
Yes, I am.
All right. So this has been so interesting. Thank you, everybody. I'm going to introduce Joe Soul. Am I saying your name right, Joe Soul?
It's Saul, but Soul's kind of a nickname too. So.
Saul.
Yes.
Is that better? Okay, thanks. Joe is an exercise physiologist with the U.S. Forest Service in the National Technology and Development Program. He began his Forest Service career in 2008 at the 9 Mile Remount Depot and Historic Ranger Station outside of Missoula, Montana. While studying exercise science at the University of Montana, he worked on several hand crews in Region 1. And after earning his master's degree in exercise physiology in 2014, he began working full-time at the National Technology and Development Program as an exercise physiologist. Since then, he's worked on numerous projects that incorporate heat stress, nutrition, physical fitness, and smoke exposure for agency employees, including teaching the Human Performance Optimization course at the Wildland Firefighter Apprenticeship Program since 2013. So he has a certification as a tactical strength and conditioning facilitator from the National Strength and Conditioning Association. And he's currently working on a doctoral degree at University of Montana with research that focuses on the impacts of exercise and smoke exposure on the cardiovascular health of wildland firefighters. Welcome, Joe.
Thank you. I guess with that, just a little bit of a conflict of interest and some other statements before I get going. I do kind of wear two hats currently. I am working as an exercise physiologist at the NTDP, or formerly known as MTDC, which really is kind of the Mythbusters of the Forest Service in a lot of ways. We just kind of go and look at equipment and other issues that may be occurring with wildland firefighters and see if we can develop a research question and study to answer those and then propose those solutions to fire and aviation management. So we are in engineering, but our kind of little niche is more into the health and wellness of firefighters, be it exercise science and nutrition and whatnot. So with that too, though, I am currently a doc student at University of Montana, so we have that affiliation with that university. So with that, my topic here today is heat stress and fatigue among wildland firefighters. And if we start looking at that, it's actually a pretty good situation that Kat got to go before me. Me and her have worked together quite a bit in the past, and she really kind of put the ball on the tee for me. for a lot of my work, so it makes it easy. But kind of where I operate right now is looking at concepts that we see in laboratory settings, and then see if those same concepts apply and how much they apply in a field setting. So the photo on the left here is actually the study we're currently doing. We have individuals come in either on normal sleep, 7 to 8 hours, versus coming in sleep deprived and only sleeping for 4 hours. And then they come in and ride a bike for an hour. And this tube here, this mouthpiece they're connected to, is actually coming off a wood burning stove that's outside the building. So they're getting filtered smoke particulate coming in through that tube, and we have that dose while they exercise. So then we look at how the body responds by looking at pre and post measurements to kind of get a short-term idea of what's going on in the body with smoke exposure and exercise. But the key thing being is we can start looking at short-term exposures like that, and then see if we actually see that in a lot of ideas that Kat was talking about, as far as long-term duration, and then also from season to season, which really, that's where the big gap is. We know a lot what happens acutely in the body, but we don't know what happens over the career of a firefighter in a lot of ways. So along those lines, if we kind of want to start looking at heat stress and fatigue and how that's been evaluated in wildland firefighting, there's really about 3 time points that we've done this. And some of these studies, MTDC or NTDP, has been doing firefighter research since the 1960s. So they were walking around with big bags of air that was getting breathed out by firefighters out on the line back then, to some super heavy computers that they were trying to document heart rate while out there as well, to now where we can have small little monitors on them and have 10, 12 sensors on these individuals while they're doing their job with little detriment to their performance. But with that, when we start looking at things, the main bodies of literature that you're going to see are looking at a starting point of the season just to see baseline fitness levels. Sorry, I have a motion sensor here in my office, so if you see me clicking on and off, that's why. And then we do have snapshots of what's going on during the season. That's kind of difficult in a lot of ways because we do get an idea of what's going on the job, but a lot of times you don't have baseline parameters for that individual, so you have no idea how much they've changed due to that exposure. And then we do have some postseason. So the study that Kat was talking about that we co-opted with NIOSH was really one of the first to start looking at multiple seasons and having multiple time points with the same individuals. And so we're really excited to see what we can gain from that and develop moving forward. Other than that, there's just been a few here and there, and most of those are looking at lung function and things like that, whereas more into my wheelhouse as far as fitness levels and demands of the job are less so documented from year to year. So the biggest thing with us, and it's kind of a spoiler alert in a lot of ways, is when we start looking at heat stress and fatigue and managing that, it kind of comes down to aerobic fitness levels and training status. And so a lot of our work has been going through to look at how can we maintain aerobic fitness in these individuals, both during the season, and then how can we build that in the off season as well. So kind of just with the main overview, I have one study here to start off. If we look at it here on the left, we have seasonal adaptations, and we're looking at that aerobic fitness levels of 4 different crews. So Kat was talking about interagency hotshot crews, and we had 3 of those, which are kind of more of our elite crews qualification-wise, but they tend to have higher levels of fitness as well. And then we had 1 type 2 crew, which is more of the general militia. With this group, we had 55 males and 10 females, which if you look at the general population of firefighters, we typically on the crews themselves, it's about 10% female, but that proportion has been going up. We've seen a lot more female wildland firefighters in recent years. But if we go and look at this column here, if we're looking at column A, this is a VO2 peak, which is just really their peak aerobic fitness. If you were to put someone on a treadmill and have them run on it as long as you can until they fell off the back, that would be really their peak intensity. And then we can get a measure of how well they're performing with that measure. But what we can see with this is if we look at there, really all these lines just go straight across the graph. So their peak aerobic fitness doesn't really change across the season. We do see some kind of trend. Some people go up a little bit, things like that. But for the 3 hotshot crews, it's all about the same. And they have a pretty high level of fitness compared to the general population in the US. The type 2 crew was pretty similar to what you'd see in the general population, but you do have some higher level fitness there. But the key thing with the peak fitness is when we start comparing it to the ventilatory threshold, which that's kind of the tipping point between an intensity of an activity being sustainable and not sustainable. So with that, we can go through and look, and kind of the best way to compare these two is if we say this individual here is 65 and then their VT was 55, you can say that they can really sustain about 85% of their max for long durations of time. So that individual is super fit. You're almost looking some kind of like semi-pro athlete, something along those lines, definitely. But when we start looking at this sustainable fitness, what's really unique is we see kind of a funneling effect of this across the fire season in the fitness levels. And really, if you look at it, all these individuals are signing on to the crew and doing the same training program of going out and fighting fire for 3 to 4 months. So right there, they have about a 16-week training program, which you'd see for most marathons or anything like that. But so the sustainable fitness level is all kind of honing in on the same value for a lot of the hotshot crews, and then just slightly lower for the type 2 crews. And kind of as we jump forward and things like that, we've actually been able to document the specific demands of tasks that occur out on the fire line. And all these individuals are adapting to being able to do those job tasks all season long. So that part's pretty neat. In a lot of ways, though, what was valuable is having a midpoint so that we can see that really a lot of these changes happen in the first 8 weeks of the season, which is pretty comparable to kind of aerobic and anaerobic kind of adaptations to a workout program or something like that. But what we really don't know at this point, what we want to start looking at more, is it more advantageous for these individuals to be detraining for the first 8 weeks of the season, or if they want to be down here below what the demand was. Because you can argue, if we're starting to talk about fatigue and stress and things like that, that it would be a lot easier to be detraining. But all these individuals did see gains. So they weren't at a status where we'd suspect that they're overtrained or anything like that. So they're still seeing positive adaptation, and we're not seeing this group as being flagged as kind of a problematic group by any means. It's just something that we're starting to watch in our workforce currently. But it is just neat to see that they do go through and do that. And then what happens too is we want to start looking from season to season if these individuals, if the variability is primarily in the off season, how can we start making that so they stay at a more optimal level, which we really don't know at this point either too. So the key thing is we need to start having long-term tracking, but it is very difficult, as Kat mentioned. But what we were able to see, once again, is sustainable aerobic fitness decreased in the fit individuals, and those less fit individuals saw an increase in their sustainable fitness levels. When we go to body composition and how that changes over a season, we didn't see differences in the change in body composition between genders. So by that, I mean, we did have some variation, but in general, both males and females lost about 2 to 7 pounds over the season. Body fat percentage decreased about 2 to 4%. And really the main kind of loss throughout the season is this lean body mass. So if you look at losing 2 to 7 pounds, about 1 to 6 of that was that lean body mass or muscle mass that they lose throughout the season. And then also with that, the fat mass was primarily neutral. Some people actually gain fat mass throughout the season, things like that. And that's where we start looking at diet, stress, activity, how does that all stack up across the season and being highly variable. But if we go through, and that prior slide was talking about the preseason point, mid and postseason, we can kind of focus in on more the first 2 weeks of that season and start looking at this piece by piece and kind of just spell out the story. So another study we did just recently was a critical training study. So for all the interagency hotshot crews that Kat kind of just defined earlier in her presentation, they're all required to do 2 weeks or 80 hours, so a 40-hour work week of both operational training and physical fitness training prior to being able to go out on a fire assignment and kind of be nationally available, as they call it. But during this 2 weeks of training, there's quite a bit of complexities that go into it. A lot of unknowns, and there's some kind of cultural influences too. First off, all these individuals, this is their first day in pay status for a lot of their seasonals at least. And so they're expected to show up day one and be ready to do the job. But in a lot of ways, they've had no financial support to get there prior to this date. So you have some individuals that come in all across the board, and we kind of see that in that adaptations to fitness, that prior slide there I showed with the fitness levels are all across the board. But when they do come into this, the cultural thing is these 2 weeks are very hard and strenuous. And sometimes there's the notion that these individuals are supposed to get kind of beat down a little bit in here just to see what they can handle so that they know what's going on during the fire season. But also, I think that kind of culture is changing in a lot of ways because one, there's not much benefit in kind of breaking someone down for 2 weeks and then expecting them to go out and perform for another 2, 3, 4 months. But we're also getting away from the point that they think that hard training can get them better in 2 weeks either. So in this regard, we're starting to get to the point where this is just a 2-week assessment of what they can handle. And then the crew boss can kind of use that to reflect what they can do out in the fire line. So I think our culture's adapting and we're getting better at kind of our programming with this critical training. Certainly we have a lot more people on crews that actually have health science degrees. There's nutritionists, athletic trainers, personal trainers. It's amazing kind of the qualifications that are on these crews that go into all their health and wellness programs. They're putting in their own efforts, which is pretty neat to see. But this critical training study, what we want to do, this was part of our evaluation because we actually saw a lot of cases of rhabdomyolysis or severe overtraining to the point of severe muscle damage that was happening during this 2 weeks of training. So we want to see if it was because of that wide variety of fitness levels or if it was just the stimulus of the training itself. And in a lot of ways, we didn't see too much. We only looked at one crew. We are replicating this exact study here with an Arizona crew and a California crew here later this spring. Arizona actually starts in a month and California will be in May. But what we saw with this Montana crew itself was we could see that we had fitness improves the ability to handle the stresses of this training. So we looked at specific markers in the blood and we could see decreased muscle damage, soreness, and markers of overreaching and stress for those individuals that were higher level of fitness, which kind of builds off of that study as far as maybe it is better to be in that higher level of fitness coming into the season. And we saw decreased cortisol levels after 5 days of the prescribed burns. Some of the other things we did see here is we could see some kind of some novel soreness going on with this scale. What we had here, this was just subjective, just self-report muscle soreness in the upper body and lower body of these individuals. And so with that first day being a very hard day, we actually saw delayed onset muscle soreness with these individuals across the board for those first 2 days to the point where they were very sore on day 3 going through. And that kind of helps us in working with the crew boss in trying to kind of schedule a lot of their training and their programming to account for this and kind of help them build a better schedule. And then also we could see after 5 days of doing the prescribed burns, they were actually starting to recover a little bit. And then with some training hikes and some fitness testing, their legs were actually the things that were getting worked the most. And that's where they really had to manage a lot of the soreness and potential muscle damage in a lot of ways. But just as Kat said too, it's just using a qualitative scale, just having self-report on this muscle soreness, we're actually getting pretty good comparisons to what we saw as far as blood markers when we had blood draws 4 times throughout the training. So it kind of goes to say that if we're just listening to a lot of those crew members and having some flexibility in the training, we can manage a lot of the demand that's going on here. It's just avoiding a culture where we're not listening is the big thing in a lot of ways. And just kind of that last point, this training is expected to be difficult, but what we're trying to avoid is a crew coming out of this training and going nationally available and being really only at 50% of capacity or effectiveness or anything like that. And kind of the next step that we're looking to do with a lot of with the Arizona and the California crew is we're actually looking at hormones in the blood and looking at testosterone and how that's sustained over the fire season and other measures of more chronic fatigue and kind of maladaptation to stress. So going away from that starting point, kind of moving away from those first 2 weeks of the season, when that crew goes out on assignment, we've actually built up quite a large data set as far as the variability in what can happen during a work shift. At this point, between our heat stress study, smoke exposure, we've done a nutrition study, job demands, and everything. We've studied about over 1,000 firefighters at this point in a lot of ways. Most of that doesn't have baseline testing, but we do have a snapshot of what can happen out on the fire line and start to establish some population norms as far as what we can expect as far as occupational demands. As Kat referenced, a lot of these long duration shifts, we're not just doing an 8-hour work shift, and a lot of occupational kind of recommendations are built off an 8-hour work shift. That does apply mainly to smoke, but when we start looking at nutrition and also exertion levels and rest, a 12 to 16-hour shift is really our norm in a lot of ways. If I go up here on this top, I'll hit that in just a second. If I go up here on this top line here, what we want to go through is from that first graph that I showed that had that funnel of fitness levels. This was that average ventilatory threshold, or that level of kind of sustainable activity in the crews at the start of the season. What we currently have is just kind of for kind of showing the lay of the land is the work capacity test, or the PAC test. The demand's right there at 22.5, so it's quite a bit lower. But what we do see is a lot of the training hikes that are performed by the crews themselves are right at that ventilatory threshold. We're starting to train at that with a pretty high variation in that as well. But then as soon as we move to the intensity of hikes that occur when they're actually on a wildfire, we see that ingress hike into the unit as being much more dialed back, which is encouraging in a lot of ways. We don't want people to be exhausted on the first hour into the work shift if they've still got 8 to 12 more to go. But there is still quite a bit of variation in that. And that's where we put a lot of emphasis on our work, is seeing if we can mitigate that demand there so that we do have more opportunities and more leeway throughout the work shift. Once we switch to tool work, we can see some variation in demand there. Chainsaw work tends to be a little bit less. Really with that, what we've seen with our studies is muscular strength does not correlate well with chainsaw performance. It's primarily technique. If you're trying to muscle around a chainsaw, you just wear yourself out real quick and you can't really keep that demand up. So long-term duration chainsaw work is actually pretty efficient, except for when you're hiking and you're just carrying that on your back. That's just contributing to load carriage in a lot of ways, as well as lifting logs. All these are kind of documented over longer duration tasks, so kind of sustainable levels. When we do talk about hiking, a simulation of the highest end of hiking that we've seen online is when they actually had hike simulations for a fatality fire. Being the Man Gulch fire, they had individuals just do basically hike sprints out to simulate running away from a flame front. And so just looking at the max capacity of what we could see for hiking as far as energy expenditure or oxygen consumption is this kind of higher end here. But altogether, we can see we just have variation across this ventilatory threshold. So it's showing a pretty even mix of high and low intensity activities that really keep our ventilatory threshold, that average for the crew, pretty level across the season. So with that, we do kind of get an idea of what a target goal should be for a lot of these training programs. We can say there and say we want to keep this ventilatory threshold high because these individuals are doing tasks for long durations of time. It's just how do we program so that these individuals can keep that? And everybody responds to a training program different. So how can we offer opportunities and modifications for injuries and other components that are happening? With all these different energy expenditures that are occurring, the energy expenditure values are really high. Some of the highest energy expenditures we've seen in just a 24-hour window was 6,200 calories, which is pretty comparable to Ironman competitions and some of those longer duration endurance races, which is kind of unique in the fact that most of those comparable energy expenditures are done with just body weight alone. These individuals are doing that kind of long duration activity with load carriage. And that's where we are looking a lot at athletic training opportunities so that we can manage posture to kind of account for muscular fatigue and things like that. But we're also working with a lot of equipment companies just to have biomechanical advantage to some of these devices we're using just to kind of prevent some muscular fatigue and things like that. Little things as far as like even evaluating whether a mountaineering boot or a logging boot is better, which really hasn't been done, even though it's just kind of culturally accepted. But with some of these calorie expenditures, we can look, and we actually kind of look at another measure that we evaluate fatigue in, which is muscle glycogen. So all these values were taken looking at muscle biopsies. So you can see the amount of energy that's really available in the thigh for these individuals on assignment. So if you're kind of just getting a lay of land on the graph on this, a value up here would be someone that's trying to do that carbo loading technique. They're just trying to have overcompensation or a ton of glycogen or a ton of energy in their body, getting ready for a big event. What we see here is just kind of a rested normal muscle in a lot of ways. And then if you come down here, what we see is someone that's kind of fatigued or just really spent. They're not going to have much energy. They're going to have kind of just tiredness in those legs, no bounce. But what we can see here is in this crew that was documented here, just over 5 days of assignment out on a spike camp. So this is kind of a remote assignment. We saw this muscle glycogen deplete each day with a little bit of recovery, but they're kind of circling the drain in a lot of ways. And this is only on a 5-day assignment, getting to a point where they're not getting to adequate recovery at all. But after just 5 days, they took 2 days off. They left that assignment and traveled to a new location. With 2 days in the truck traveling to the new one, they saw pretty good recovery back to their starting point in a lot of ways. But then once again on a 5-day assignment, this time in a large camp that had quite a bit of supplies, we saw a lot better maintenance of this energy status of the muscle. And then also leading into 2 days of going back home, they saw they were, by the time they were available for the next assignment, they're back up to even before where they were at. What this comes down to is we currently do have a 14-day on and 2-day off kind of work cycle that these crews are expected to do. There's really not a body of research to support this in a lot of ways. In a lot of ways, it just aligns with a good pay cycle. But what we've done is try to evaluate and see if that 2 days off is adequate. There's going to be situations where 2 days off may not be adequate for this. And we've actually even trialed out this last summer having 3 days off to promote more recovery, both from a physical and a mental standpoint. And we're still deciding on that. This season, that's well above my pay grade as far as what that happens. But we didn't really have any exploratory research to evaluate that this last season, unfortunately. So we want to continue to look at that more. I haven't talked about heat stress yet. So here's this was all built up to that. So really in a lot of ways, if you look at heat stress, you look at the energy used in a muscle contraction. So if you look at all that energy, really the energy going into the muscle, only 30% of that energy gets used as in the force of the contraction. If I'm flexing my bicep or flexing my quad or anything like that, 70% of that energy used in that contraction actually gets released as heat. So that's why we shiver when we're cold. It's beneficial from an evolutionary standpoint, especially being human beings without a whole lot of body hair for most of us at least. But so it's beneficial in that way because it does warm up our body to a good temperature, so we have good blood flow, and it's a positive adaptation that's happened with us. But in the occupation of wildland firefighting, we're looking at long sleeves, full-length pants, sometimes chaps over top of that are very thick, a hard hat, which is really equivalent to wearing a beanie in a lot of ways, and then having a pack on our back really encapsulates us quite a bit to the point where we have a lot of challenges offloading that body heat that we're generating. To that regard, we can see that when we went through from 2013 to 2016, we had firefighters from all across the west half of the United States swallow a core temperature capsule before their work shift. So before breakfast, they'd swallow this, then they'd eat their breakfast, and that pushes it down into their intestines, and we actually get a pretty good idea of what their core body temperature is throughout the work shift. To that regard, what we saw was some pretty high peak temperatures that occurred throughout the work shift in these individuals all across the board. If you look at this scale here, about a 37 is about your kind of normal body temperature. 98.6 Fahrenheit, 37 degrees Celsius is kind of our starting point. But this is just the peak value or the highest value that we got from everybody. When you start looking at heat stress literature during exercise, typically about 38.5 is the tipping point where they say individuals are at risk for heat-related illness. So in that regard, this graphic is showing that over half of the firefighters we watched were at risk for going down for heat stress throughout their shift. If you look at it, we typically have about 30,000 firefighters that are in, out, on, or around fire each summer. So that's quite a bit when we start looking at 300, we had 150, we had 50% of ours. We don't know how that applies to the general population because we were kind of more focused on hotshot crews here. But we can speak to hotshot crews more directly with this exposure. But to that regard, we do see incidences of really high body temperatures, sometimes to values that were pretty critical for a lot of people. If you start looking at 40 here, that's over 104 degrees Fahrenheit in a lot of ways. So exertional heat stress levels are pretty high here. Okay. To that regard, though, with all 300 individuals that we had in the study, nobody went down or suffered from a heat-related injury. So on those lines, you can say that, hey, if you're in a heat stress study, you don't want to be the person that goes down from heat stress or anything like that. So they might have kind of held back a little bit. But at the same time, we can say that they went out there and did the job in hot environments, got hot, and successfully went home each night too. So there's a way to perform in these environments. And that's just one of our discussion points on that. But even though we had some high peak values, our average values throughout the shift are pretty benign in a lot of ways. You can see just doing exertion and moving around, it's not too bad in a lot of ways. It's really what you would expect. We did have one individual that just was out there, but there's always one person. So, but if you start looking at that normal distribution there, it's not too bad in a lot of ways. It's what you'd expect, and it's manageable, and it's showing some level of self-regulation. The other component to this too is these values are from 6 a.m. to typically 8 or 10 p.m. So there's going to be cooler portions of the day, sedentary portions of the day that bring the shift average down. Okay, but really this is all influenced and supported by kind of the equipment weight studies that we've done. We've begun to look at personal protective equipment. We're trying to reduce the amount of load carriage so that we don't see those dramatic spikes in core temperature. We've reduced the weight of the chaps so that they still have the same protective ability, but all the straps and buckling on it are much less, and we reduced that almost in half. And then we're trying to increase awareness on these activity rates and these ambient conditions. More so on the activity rates. We can see through a lot of that heat stress study that we're performing activity in all ambient conditions. If these individuals are on this fire assignment, the fire is actively burning and there's going to be work required. So whether it is on the colder end of things, or if it's more on the hot end of things, if we're down in outside of Phoenix, Arizona, these individuals still have to do the work. And what we can see, and Kat kind of described a lot of these activities in her presentation, but mopping up, we did see some elevations of temperature, and really that's a pretty passive activity. That's just speaking to kind of exposure to the elements, because they're in that burned out area and there's no shade and you're exposed to the elements. We still have heat stress situations there, but also during ignition operations with some effects from radiant heat. Chainsaw operations, we saw that does get laborious. Line construction, which is with hand tools, and then hiking continues to be our main elevation of body temperature in a lot of ways. To that regard, we actually have some body temperature profiles that we start to look at with this. And what you can see here is this is an individual's core body temperature from that pill that they swallowed throughout the shift. So that pill is just a electronic thermometer and a Bluetooth sensor that was just transmitting to a heart rate harness that they were wearing throughout the work shift. So we had heart rate, respiration rate, this core temperature, and then we also had skin temperature on this. And then we had GPS sensors on them. Sometimes we had the smoke monitors that were involved in Kat Navarro's research and other things along the way. But we got a good profile, and we were able to document minute by minute what these individuals were doing and seeing the physiological response. So with this readout here, we have their body temperature, and then over time, we can see that most of the time they're waking up at 5 or 6 in the morning. Briefing starts about 7, and they spent a couple hours just getting things ready for the shift. Probably a good duration of time driving out to the line to the point where it's about 10 o'clock in the morning, and then they start about an hour-long hike to get into the fire or the work unit for the day for this one. With that regard, their body temperature goes from baseline all the way up to 102 in a lot of 102 degrees in relatively short amount of time. And that's where we are seeing this peak value. Most of the time, though, we do see a recovery down, but it's almost to the point where we had a significant raise where we see a reset in baseline. And these individuals stay elevated for quite a while, and it's pretty activity dependent beyond that. Because especially if you do acknowledge ambient conditions in these settings, we have this period of the day where the sun's rising, and so we have ambient temperatures are increasing, and those high humidity values from overnight are just starting to decrease. So you kind of have a weird window of the day there, but these individuals are also carrying all the weight of the equipment they need for the day, all the water, gas, tools, and things like that. So this is a hard hike in a lot of regards, but once they get on scene, they can kind of get a rest break and manage that a little bit better. What we do see though is almost in all 300 of these readouts, we see that same ingress hike spike in there to the point where this is manageable, but as I'll show on the next slide, there are instances where this is not manageable. What we do see though is still activity dependent after that hike in there, but it can stay long duration where we are going to have individuals with an average above 38, 38.5. So they're staying about 102 for most of the day as far as body temperature. And a lot of times this is during a window of the day where you're well over 80 degrees, well over 100 degrees, depending on where you're at. And you're also introducing environmental extremes of altitude, smoke, and things like that. And so this activity really needs to be regulated and going through there. And in this last regard, we have this same spike in here, but this one is the only documented heat-related illness that we've seen where someone actually had one of those core temperature capsules ingested and they went down with the heat-related illness. So with this wildland firefighter, they had their same kind of general profile. They were up in Washington for the day. They saw the hike into the unit, and this individual was just outworking everybody else on the crew at that point, and they justified it by drinking 6 liters of water in 7 hours. So essentially they drank a day's worth of water probably by about midday in a lot of ways, and to the point where they hit a critical temperature of 40, which we have had individuals hit 40 and not go down, but this individual collapsed with heat exhaustion. Just was kind of outpacing himself work rate wise in ambient conditions. Because of the study design, we were monitoring 3 people. Well, wasn't me, I wasn't on site, but our lab was monitoring this, and they had 3 individuals. So he had 2 people side by side with him that were operating in the same ambient conditions and leveled out about 38, 38.5. They just stayed in here. So this individual chose to kind of have an activity work rate that exceeded those others, and we kind of saw some cause and effect in a lot of ways. And this, in a lot of ways, is justifying why we are putting this attention on work rate, not so much these ambient temperatures. And also kind of putting the notion that you can't outdrink a heat-related illness in a lot of ways. You need adequate hydration to be able to sweat and kind of offload some of that heat to your environment, but you're not going to reduce body temperature by drinking water in a lot of ways. So up to this point, I've talked a lot about outputs of the job as far as what we're doing as far as work outputs, and then really the heat output that we have during this. And so when we start talking about fatigue in a lot of ways, we're trying to support the firefighter with inputs as far as how they can best manage this occupational environment that we're starting to define pretty well. You know, Bob Ross in a lot of ways would kind of support what we've done as far as painting this picture. With what NIOSH has done, with what NTDP has done, we're starting to get a good idea of the demand, at least on a day-to-day basis. The long term is really what's starting to become more and more needed, especially when we do start looking at long-term health effects. We're getting more and more researchers involved in this, and I think there can be a concentrated effort. But in the meantime, we are trying to handle more day-to-day and more just month-to-month and handling the season itself, as far as strategies to give to the firefighter. So in that regard, we actually recently revised the whole food contract to try and put better food quality items into the hands of firefighters while they're doing all this output in the environment. So in that regard, In the past versions of the contract, everyone noted the energy expenditure values and said that we just need to get calories to these individuals, to the point where they'd have a sandwich, a bag of chips, and then six snack items that just need to be 300, 400, 500 calories each. And what that equated to, because essentially you're trying to feed a couple hundred people up on some hill in a rural environment, a lot of times that was candy bars and just cheap processed foods. And we're looking at some high-end athletes that are trying to perform day in and day out, that are running on a pretty kind of low-level diet in a lot of ways. So we went through and revised his contract and actually stratified it by macronutrients, trying to look at carbs, fats, proteins, and try and hit a lot of the sports and nutrition needs that these individuals need. And with that, we started to document some actual losses of sodium, potassium, and things that we need, some kind of components of micronutrients that we need to address during the work shift. How we got this was not the glorious part of my job, but we actually watched people eat, and we'd weigh their food before. And when they were done, if there was any scraps or leftovers, we got to weigh all those. We had exact calculations of what they were eating. So not the funnest part of my job. I've collected spit, urine, and all that. Sometimes it's not glorious, but the numbers are really cool to kind of look at in a lot of ways. If we didn't have them, we'd just be guessing in a lot of ways. So with this, we do have a pretty good breakdown of breakfast, shift provisions, or food that they eat during the shift. So a lot of times they'll get almost 1,000 calories just on a plate that's handed to them in the morning. And then they'll get a sack lunch that's supposed to give them enough nutrients to last from 6:30 in the morning to sometimes 6 o'clock at night. So 1,500 calories sometimes is enough, sometimes it's a lot, sometimes it's not enough at all. One of the things we do run into is the same sack lunch is given to firefighters that go and burn a couple thousand calories a day, and it's also given to individuals that just stay in camp all day too. So we have some disparity there as far as who that's counted to. And then the dinner, it's typically about 1,000 calories as well, but there's a salad bar where they can get additional calories. So on average, when the studies we've looked at, most of these individuals are eating anywhere between 2,000 and 5,000 calories a day, getting plenty of carbs, fats, protein, and sodium and potassium levels that are pretty high in a lot of ways. And as we start doing more of these long-term health studies, we're starting to look at metabolic panels. We have seen in some studies with some crews where we see some maladaptive adaptations with cholesterol and things like that with these individuals over a season, to the point where we have levels where this is a high level aerobic fitness crew that really does not have a very good metabolic panel. And that's where we're trying to expand on that research, because it's only on one crew, but start looking at if there's geographic regions too, how diet influences that as well. Moving on to hydration, we've actually done quite a bit with this. This was a fun one. We just followed people around with urinals and watched them work all day. But once again, it got us numbers. It really, when we start looking at the amount of commercially available supplements that are there to support hydration, we needed to have a good idea of, are there moments throughout the shift where we have problematic states of hydration? The key thing being is we can look at urine levels in the morning and in the evening, but are there spikes due to the high sweat rates, or kind of valleys due to the sweat rates where someone is in a bad hydration status? So we followed them throughout the shift, and we were analyzing urine throughout the shift. And we also had them do blood draws pre and post shift to look at some of these serum levels that indicate hydration. To that regard, without supplementation with the diets we had with that new food contract, they were actually carrying pretty well as far as hydration. So we're looking at individuals that are turning over anywhere from 6 to 10 liters of water in a 24-hour window. And despite that high level of water turnover, we're actually staying pretty good on a lot of these metrics. Because one of our main concerns with the amount of water we're pushing in these individuals is both hyper and hyponatremia with that. So we wanted to kind of assess that as this becomes more and more of a prevalent issue. Once you start talking about heat stress, a lot of people start talking about hydration, and we needed to have a twofold approach with that. I'm going to do it on time. Perfect. So along those lines, just kind of wrapping up, and then I'll make sure and touch some of the points on the chat and then the Q&A. Where we're at right now is looking at aerobic fitness levels. There's several efforts going right now to have actual kind of equivalents of personal training qualifications for individuals on crew, both having kind of a 100 or basic level course, and then also looking to have almost a crew level training coach certification. Starting to look at how we can build individuals in a good, safe way, and looking at both on season, in season, and then trying to address the off season component of that as well. As we've seen, as I kind of showed earlier, we have a wide range of aerobic fitness going in there, and we're still trying to paint that picture as far as what is a successful model to handle this. Odds are it is going to be the higher level of fitness is going to be better in a lot of ways, but we can't really set a baseline or a minimum value that's needed right now. The PAC test does do a good job of replicating work tasks that occur during the line, but there's certainly more intense activities that occur that the PAC test is not representative of. We see that most of the time the work is at about 50% of our max, and that's where sustainable fitness needs to be. So we look at a lot of our training programs and things like that, focus on kind of building up that sustainable fitness is going to be a positive influencer on handling some kind of short-term physical metrics of fatigue. If we start looking at that, and also there's adaptations from aerobic fitness that help you perform in the heat. More vascular, things like that, lower body weight is going to help you perform in the heat a lot better. So we are definitely taking that tactic, but as kind of the theme of your day I'm seeing here is there's a multitude of stressors associated with this occupation. Physical fitness is just one kind of cog in the wheel in a lot of the ways. We're looking at sleep, smoke, stress. As I mentioned, my current dissertation study right now, we're looking at people that are sleep deprived and seeing how that affects their immune response to that bout of exercise with smoke exposure. There's still a lot we need to figure out, and that's just in a short 45-minute exposure. We don't know how it goes in a long ways. So this balance of this aerobic conditioning, we do have some PPE that is beneficial, but as Kat alluded to too, we're definitely looking for administrative tactics that we can take. Is there better ways to reduce that ingress height so that these individuals don't have to have that big of a physical stress each day and that much of a thermal load? Can we put individuals and just have them sleep out on the fire line to reduce that time? They can start work earlier in the morning in a better environment and kind of keep that core temperature average down. But as Kat also said, that's kind of risk transfer in a lot of ways. We're trying to reduce that kind of immediate demand on the individuals, but does that put more stress on logistic vehicles, having to drive up meals, things like that? Does that affect food quality? What happens when we have people sleeping out in the woods each night? There's transfer in every single decision that's trying to be assessed right now. The biggest thing we're talking about is those inputs, just having a daily approach to yesterday, today, and tomorrow. And hopefully we start painting that picture more as far as what a season looks like and what a career looks like. We still really struggle. We have a lot of college students that come in and do the job for 4 years and then leave, and we just have no real monitoring on them. And then we have individuals that stay in 8 to 20 years or more. So it's just such a diverse work population that there's not a lot of control in long-term studies. And as I kind of alluded to earlier, we do have a lot of qualifications on the crew. When I'm teaching a lot of this material to crews, there's a lot of individuals that have sports science degrees that are already teaching this to their crew with some of these specific guidelines and values. And so we are promoting higher carbs just to support that. We're trying to keep these individuals to have carbs throughout the day to keep blood sugar up and support immune function as well. Kat was talking about the showers. That's tough in a lot of ways. You can only get a couple shower units that have 5-6 stalls in there. Some people are going to prioritize sleep. And two, there's the notion that you have 1,000 people that are all trying to use 6 stalls on a daily basis. Yeah, they clean them a couple times a day, but it's just a big bottleneck and not an option in a lot of ways. And then just to kind of wrap up a little bit, and then I'll make sure and hit these Q&As. This is just some of the numbers on the new revised food contract. So putting an emphasis on those input, what we're trying to do and get as far as nutrients to these individuals. We went up from 2 fruits and veggies to 3 fruits and veggies, and actually had a discussion with the caterer as far as what's available. Because in a lot of ways, we're looking at a school's food system delivery like Food Services of America and trying to get ideal menu from those, which is really tough in a lot of ways with the amount of diets that are going on And so diets do change quite a bit for individuals from off season to in season, but it just comes down to logistics and contracting issues. And then I'll kind of just wrap up on this, kind of already showed it as well, but just the breakdown of those nutrients that we're going through. So with that, that's all I had. I'll go through. We don't have mine.
Thank you, Joe.
Yeah, of course. Stop share. Just make
Do you
sure.
see the Q&A?
Yeah, I got it right here. So muscle soreness is related to lactic acid levels. Was there a reason why it was preferred that participants report muscle soreness? And just because we were looking for some kind of subjective measure in a lot of ways, we can do some lactic acid testing, which you're exactly right there. That's that kind of lactate threshold is pretty similar to a ventilatory threshold in a lot of ways. It's at that point that we're not sustainable and you're going to start having issues with what's produced during that activity. But to that regard, we were looking at something that we could use on a day-to-day monitoring where we didn't have to be on site to do a lot of this testing and our research with that. So trying to give crew bosses tools to do the job and promote a culture where people are talking back and forth as far as what is their status to go on a daily basis. 6,200 calories is a lot of food. Yeah, it is. Some of these individuals are eating, they'll get a plate of 1,000 calories on a plate, and then there's also always a breakfast bar there too, where they can get upwards of another 800 calories there at breakfast. We've seen individuals eat quite a bit. I think the most we've ever seen was about 8,200 calories that was eaten by an individual. That individual is just a unique one as far as just constantly chewing on something. We've also seen individuals drink about the equivalent of 30 cups of coffee during a day with energy pills, energy drinks, 5-hour energies. And so there's a lot of unique situations that are occurring with this large workforce that really can be outliers to what we're seeing. And it makes documenting this workforce pretty interesting. So the second part of your question, does the study look at nutrition in terms of what type of calories are addressed? Yeah, that's what I kind of tried to finish with there at the end. We looked at both what was consumed ideally and then what we're trying to provide. So we've been hitting a lot of that to try and just match what's going on and not just have a sports science perspective on, hey, you are an endurance athlete, you need to have carbs. We actually had a study done by the University of Idaho that just looked at food preferences, just looking at what kind of meats we want to have, how much meat, how much cheese, things like that. In a sandwich, what should an entree have, and things like that. And that's why we actually had that breakdown of just a salty item as far as like a chips or salty mix, things like that. Just because some people do want healthy items and non-healthy items. Kind of my joke is with a sack lunch, the best tactic is if you know you have 2,000 calories in it and you don't know what your day is going to look like, just dump the sack lunch out on the table and order it from healthy to unhealthy. And then if it's a slow day, you're only going through your fruits and vegetables and your sandwich. But then if it's a really bad day and you have burned 5,000 calories and it's 5 o'clock, a Snickers bar tastes pretty good. And at that point, you just need calories too. You've already kind of hit that basic kind of macronutrient profile you need and gotten a lot of vitamins and minerals because you do have so many food items. The key thing we were trying to balance through all that is if you get that many food items, especially if they start to be processed, you really have to be cognizant of what's in there as far as sodium, potassium, and things like that. Saturated fats is one of the things we're looking at too. With regards to hard hats used by the crews, did you look into whether using ventilated hard hats could help release heat? Yeah, we've actually had a study done here at the University of Montana that looked at a vented kind of arborist helmet and then also looked at a couple ski helmets. So MTDC has actually looked at helmets for smoke jumpers for years and years, and that's actually kind of a ski racing helmet, but they have football helmets and things like that they've tested over the years, and it's kind of interesting to look at the testing profile. But with the hard hat specifically, it's not a wildland firefighter helmet. It's a hard hat helmet. It's a construction hard hat. And to that regard, some of the testing, one of the tests they actually do is there's an electrical conductivity or conductiveness test, and they have to be able to put water in it to do the test. So they haven't allowed the helmet to have venting in it because it wouldn't hold water to hit that kind of that construction bollard standard. So we started to work into the policy on that, and I'm starting to get out of my wheelhouse as far as how the actual technical with some of the engineering and the drawings go on that. But what we did see when we going back to the my exercise science side of things, when we looked at having a vented hard hat, we saw a much better improvement in both kind of skin temperature on the head and then also body temperature. Just showing that a non-vented hard hat is pretty similar to wearing a beanie. And once you put venting in there and you offload heat, it's pretty beneficial, especially when you look at about 50% of your body heat is kind of released from kind of your head area in a lot of ways. It's beneficial to be able to do that. And anecdotally too, we see that with crews. The first thing they do when they get onto the top of a mountain or something like that is take their hard hat off and do that. And they're letting off body heat doing that. But we just want to create an environment where they can keep it on. The other flip side of that is due to safety constraints with a lot of our tree strikes and fatalities, people wanted to put a chin strap on the hard hat. And with that, we wanted to look at venting, because if we're putting that chin strap on, that hard hat might stay on longer and keep things on there. So that was part of our evaluation of kind of revising that heat stresses, looking at options with the chin strap, and then also looking at venting, and also adopting a new certification standard so we could have that venting in the helmet. Nice. And then, yeah,
Okay.
It is a lot of caffeine. And that individual, I started documenting his dietary log and just had him hold out his hand for me, and he was steady. He's about a 35-year-old individual, and he just built up that tolerance over time, which is amazing and kind of frightening in a lot of ways. So.
Thank you so much. I have a quick question for you. Are you looking at acclimatization at all?
Yeah, we've actually done a few studies looking at trying to tinker with acclimatization quite a bit. So we've actually looked at acclimatization, and some people actually try and dehydrate during their acclimatization to see if they can acclimate better. And they didn't see any adaptation to that. But most of the time we're looking at just small doses of exposure to the heat, kind of light, moderate activity in that heat, and then being able to remove yourself from that heat. That's really when you kind of recover, is getting into a cool environment afterwards. Because we've had all sorts of strategies. People say no AC all the way driving down to Arizona and just kind of suffer all the way down, and they're just stressy, miserable, and smelly. But if they just kind of drive all day, stay in that AC, and then get a small light workout in the heat while they're driving down there, they can start to see adaptation in anywhere from 4 to 9 days is what they've seen kind of consistently in the literature.
Thanks. There's one more question about cooling vests.
Yeah, so any thoughts on any other cooling devices such as cooling vests, etc.? The biggest thing we've dealt with those is they could potentially be beneficial during training environments. But also the point of training too is to kind of have some of that thermal exposure and then be able to come back and recover. So our one concern with having cooling vests out on the fire line is how long are you going to see that advantage? Does the ice in the vest potentially just diminish, and then you're just wearing another layer of clothing for that long duration, body weight, and then also just kind of thermal protection. Everything that those individuals wear have to be flame resistant in a lot of ways. So it usually comes up to a big barrier right off the bat as far as putting any kind of like special equipment. But in training environments, there have been some studies with that. It's just what's available to these individuals on a given basis. Yeah, of course.
Okay. All right, well, thank you, Joe. That's really interesting. So much work. It's incredible.
It was a collaboration. There's been a lot of people that have done that over the years. So.
All right, well, I think that is going to wrap up our program today. I feel like I've learned so much from all of our speakers, and so much of this work is going on in the public sector. So thank you to all our agency scientists that have been working on all these complex and challenging issues. I'm very impressed with the work that's going on. And I think it's particularly meaningful because climate change and the wildfire seasons is one of the things that people feel powerless about. And so it's encouraging to me that we have talented people working on understanding the toxic mechanisms and disease endpoints better. I was really encouraged to hear that the air quality index was better than I thought it was. So that was a huge improvement to my former understanding of the monitoring data that makes up those health advisories. And just being aware of some of the environmental impacts to our local watersheds and the coastal water quality, and minimizing community exposures to the recovery effort. That was very interesting. And so, yeah, thank you in particular to all the occupational health specialists that are working for the fire service, who are doing that important and dangerous and also, life-threatening for other reasons, the work that they do. Hopefully this evidence-based interventions will continue to benefit that workforce and minimize injury and improve their overall health. That was all I had to say. Ty, do you want to make any closing comments? We had a question about the
Yes, somebody was asking if we can go back to the previous slide. So Jenny, can you back up? There you go.
There you go. Yeah.
Thank you.
And I want to thank Jenny so much for her support throughout this, planning this event and all day, making it run so smoothly. Thank you.
Jen, do you have any comments about the survey? There you go.
The survey is required in order to get your continuing education form. I will also email everyone and send the survey link through email. So if you miss it here, don't worry, I'll be sending an email as well. Thank you.
Thank you. I just want to say thank you to all the speakers. It was very good, interesting topics, a timely topic that is not going to go away. It's just going to keep growing over the years as we go through all these different changes. Also, I want to say thank you to all of you for attending this technical symposium. I call it COVID style because it's Zoom instead of being in person. So hopefully next year we all get to be in person. And if you have any ideas or any suggestions for topics, just let us know. Perhaps we can pick up on and start working on that for next year.
That's right. And then just to reiterate, the recording will be available, but not immediately. So stay tuned for an email with the links to the recording.
And I believe too, the presentation materials will be available as well, correct?
I think if we have the permission from the presenters, we'll share it.
Exactly.
Yeah. All right.
All right. Now, other than that, I'm good. Again, thank you.
All right. That concludes our program. Thanks everyone for coming, and hopefully we'll be able to get together in person next year.